ask you guys to be honest, all right? Give me a 1 when you hear about working with neural networks. Give me a 1 if you feel intimidated by it, or give me a 0 if you're not intimidated by it. I'm not going to call on anybody, right? But like, aren't neural networks kind of intimidating, right? Like if you're just starting out, if you're just kind of, like working your way through data science, like it's kind of intimidating to talk about neural networks, right? It sounds scary, right? Okay, so I'm already seeing some votes, right? Give me a 1 if you find neural networks intimidating, or give me a 0 if you're not intimidated by neural networks, right? I'm already seeing some ones, which I totally get, right? Like I'm admitting to you guys that when I was learning, I thought like learning about neural networks was like learning like a whole other thing, right? So I want us to take the time to think about these things, because by doing that, I think we're going to try to take some of that intimidation factor out of it, right? And also, you guys know how big I am about being able to talk to people like the non-math guy, right? And how can you talk to a business stakeholder in a way that they can understand neural networks if you yourself don't understand it in that way, right? Like, you just won't be able to do that, right? If your first class on neural networks is, hey, let's talk about PyTorch, and this is what a PyTorch, neural network snippet looks like that doesn't make you an effective talker to business stakeholders, right? So Vidor says sometimes seems like an otherworld thing. Yeah, absolutely. So, okay, guys, so I'm seeing basically a lot of 1s in the chat, right? So, okay, so let's agree that they're intimidating. I totally get that. So let's just talk. Let's just take a step back, and we're just going to talk like human beings, right? No math, no crazy nonsense, right? We're not going to, be focused on PyTorch or Keras or anything else. Let's just talk. All right? So, what's a neural network? Give me your answers in the chat. What's a neural network? Let's just start there. Right? Super intimidating word. But what is it? A business, you're sitting in a meeting, you're presenting your solution, and one of the business stakeholders says, okay, yeah, you're telling us this great solution, but I don't know what a neural network is. What is that? What are you going to answer? What do you guys think? There's no wrong answers here, guys, right? This is all an exercise in all of us working things out to kind of take that intimidation factor out of it, right? So that's all we're doing. There's no wrong answers. I'm not going to call on anybody. You're going to be okay. Just, what's a neural network? Okay, so Enos is saying, let me know if it's Enos or Enos. I'm going to go with Enos. Connected neurons, maybe? Okay. Alberto says, a network of neurons to make a prediction. Okay. Anybody else? I'm going to give you guys another minute here. Rosendo says, shows the probability of how variables are connected. Okay. Lanry says, a computer system that tries to learn like a human brain. Okay, Lanry. I think I'll give you guys a hint. Lanry is headed in the direction of an answer that I would give. Vidor says, I think in some attempts to imitate a human being neural network with neurons and stuff. Okay, Vitor. Vitor and Lanry are on the right track. Not that the other answers are wrong, by the way. I'm just trying to help you guys understand how I would present this to like a business stakeholder, right? So I believe I left it with Kago. Kago, am I saying that right? Kago says a layered approach to predict the output where the weights are updated at each layer. Okay. Yassine says it's like a little kid learning from the things we show. Okay, nice. I love Yassine's usage of like non-technical terms, right? I like that. Okay, Enos. Okay, thank you so much, Enos. Starry Vibe says learn patterns from data inspired by how the human brain processes information. All right, cool. All very good answers. Yeah. So I think all of you guys are on the right track, right? So here's what I'm going to propose. And this is what I've used in actual like business meetings, right? And that's just to say a neural network is a mathematical representation of how the human brain works. That's it. This is a definition that I've used with, high level executives, and they understand it, right? So you don't have to quite get into, the neurons and all that aspect of it, but it's just a mathematical way to simulate how the brain works. That's all it is. Denelson says a system of linear algebra algorithms that trigger each other, mimicking a human's neural network of exploring and learning and correcting itself. Okay, cool. Thank you so much for that, Denelson. So this is the kind of definition, what you're seeing up on the screen, that I would give to a business stakeholder, right? Because again, nobody is wrong in the chat, but we're going to keep things simple. We're going to keep things simple and not intimidating. Because if you're intimidated by it, then your stakeholders are also going to be intimidated by it, right? And you'll never be able to successfully explain it in a confident way, right? But that's all a neural network is, right? Once you understand that really all you're doing is math to simulate the brain, to me, it becomes a lot less intimidating. But of course, we're going to take it steps further to keep on like deconstructing it and learning more about it, right? Okay, so if we're talking about the human brain, then we kind of have to also start here, right? Like, let's look at what this is. So this here is a nerve in our bodies, right? And we have millions and millions of these nerves throughout our bodies. And you can see that there's a direction being indicated, right? The signal, the electrical pulse, right? The electrical signal goes from left to right in this scenario. So over here on these dendrites, you have a bunch of different possible inputs, right? Because inputs can come from any number of places in your body. Based on that input or the lack of an input, there is a firing of the electrical impulse, right? Along the body or the axon of the cell. And then it goes on to these terminals to do other things, right? In most cases, they're connected to other cells, right? Because these millions and millions of cells are interconnected all with each other, right? So if I'm sitting here and my brain is telling my hand to move, right? Then my brain is firing all throughout down my brain, my neck, down my arm and up my hand and causing it to move, right? And it's causing my other hand to not move, right? So there's firing going on in these nodes or these cells, but there's no firing going on over on this side, right? Because I'm not asking this hand to move, I'm asking this hand to move. But the point being is that there is like a flow or an order to that, right? Where the signal to want to do something starts in my brain. An electrical impulse is initiated and then run through the relevant cells to say, oh, okay, I need to move the muscles in this shoulder, but this shoulder over here stays still, right? So there's electrical impulses and connections being made on this side of my body, but not on this side because that's not where the inputs are telling it to go, right? So that's basically all that is. We are going to take this cell and that process that I just explained to you, and we're going to represent that in a mathematical way. We're going to have mathematical representations of this nerve, and we're going to decide which nerves should move and which nerves shouldn't move, right? Which ones should fire and which ones shouldn't fire, right? Everybody with me on that? So Abiola says a neural network is a model that mimics how the brain neurons work. Yeah, sure. Yeah, very much like that. Very much like that. All right. So I'm going to guess that most of you have seen something similar to the chart that's over here on the right-hand side, right? This is our basic representation of what a neural network is from like a data science side, right? A neural network, as some of you pointed out, is made up of a series of layers. But again, those layers is just a continued representation of what we talked about, right? Because just like in the human body where we have millions and millions of cells, we can have large neural networks that have a lot of different nodes. And you can think of those nodes, each node as being very similar to the cell that we saw earlier, right? So this cell, if you're bought into this idea, this cell is represented by a node. And you can have multiple inputs, right? Because there's multiple things that can cause me to move my arm or have a need to move my arm. There's different layers and nodes because there's different cells that go into moving my arm, right? I have to have some nodes that fire in my shoulder, some in my elbow, some in my wrist if I want to move my wrist at the same time, right? So there's multiple layers and multiple cells that can function, that can fire at any given time, right? And then there's multiple outputs that can happen, right? I can have my hand go up, have it go down, have it go to the side, whatever you need, right? So, but that's really all we're doing. We're just creating a way that simulates the manner in which a human brain works. So Leo says, it's really important to stick with these details of how data is transformed to information. Love how Dennis approached an intuitive way. I appreciate that, Leo. Thank you. Yeah, guys. I mean, I love Leo's point here, right? Because you guys know that I'm not just trying to teach you data science just for the sake of it, just to say you did it or just to pass some interview. I want you to think about this from like, how am I actually going to use this in the real world, right? And being able to explain this to other people is super critical in the real world, right? Because otherwise you just become a person nobody wants to talk to because they don't understand the word you're saying, right? So thank you for that, Leo. Appreciate you saying that. All right. So we're going to have our input layers, we're going to have our hidden layers, and we're going to have our output layers. And each one of those is basically just a series of cells very similar to this. Right? You can have any number of nodes and you can have any number of layers. That's one of the beauties and also potentially one of the downsides of neural networks. That you can construct neural networks in whichever way you want. They're much more flexible than most other models, right? Most other models are fairly prescriptive on what they have to look like. You're really just kind of changing the weights, right? In many ways. But neural networks can be designed in however way you want them to. Nobody can tell you, like, if you say, well, I want my next neural network to have 20 layers, no one can really give you like a rational reason why you shouldn't do that. Your neural network can be whatever you want. You can have however many layers and nodes that you want. There's very, very few hard and fast rules to what you can do with them. So it can be a little bit of a challenge because you don't know what the final form of your neural network is going to look like. You have to run the experiments, right? And that's okay. But you have a lot less guidance than you would in most other models. There's a lot more to choose from when you compare neural networks to other models. But the bottom line I'm trying to impress upon you is a network can be anything you want it to be. There's no real prescription for it. And I think that's a good thing, right? All right. I want to also kind of show you this chart because I don't want you to think that you can just have one layer in your neural network. I think that's a common mistake that a lot of people make, where I see people, give me these very small neural networks, but that's because that's all they've ever really seen, right? I mean, unless you've done a lot of work with other networks that are out there, you've never really seen something with 15 layers, 20 layers, 30 layers, something like that, right? But just keep in mind that you can do whatever you want. You can have as many input layers, as many input nodes. You can only have one input layer. You can have as many hidden layers as you want, and really just design it any way you want. Okay? What you should also be aware of, though, is that if you look at these arrows are not randomly drawn. You have to look closely to realize that every single node is connected to everybody else. So from this node here, you're going to find 4 connections because of the 4 hidden nodes. This one also has 4 arrows, and this one also has 4 arrows. They kind of get lost in the mix, because it's just the way the graphic is laid out. But all nodes are connected to each other in some way. Again, similar to your body, right? There's you can feel things throughout your body, but that's only possible because essentially all nodes are connected to each other. You only have one central nervous system that does all those electrical impulses and connections throughout your body, right? Us as humans have a lot of those electrical things coursing through our body, but it's all just one single central nervous system, right? So everything is connected to each other. That's the network part of it, right? Because somebody's going to ask you, like, what do you mean there's a network? Well, that's the network. All of the nodes are connected to each other. It's possible for you to be able to trace back through and say, well, how is this node connected to that? Oh, because of this path here, right? That's the network side of it. So the question is, how do those nodes all communicate with each other? Right? I just finished telling you that you can have as many nodes as you want. You can have as many layers as you want. But how do they communicate with each other? Now, in the human body, they communicate with each other via electricity, right? And what and how is decided the things that need to fire? Well, that's kind of like, one of the wonders of the human body, right? Like that's like your human consciousness decides that, right? But how does that happen in a neural network? So give me your thoughts in the chat, guys. If we just said that all the nodes are connected, then how do they communicate with each other? If we said that this is a mathematical representation of how the brain works, how do we represent that in a neural network? Like, how do we transfer that over in a neural network? Let me know. Start putting your answers in the chat, guys. Rosendu says, it looks like a cross join in SQL. Yeah, sure, absolutely, right? It does have a little bit of that relationship feeling in SQL, right? The difference is that in a neural network, there's kind of a many-to-many relationship, right? So one node can have many connections, and one node can be connected back by many nodes, right? Did I say that right? Yeah. Yeah, one node can have many outgoing connections, but it can also have many incoming connections, right? But yeah, Rosendo, you're on the right track there. You're on the right track. So let's think about those connections, though, right? If there is all this network connectivity, right? That's the network part of the name. How are they connecting? Like, how are they communicating? Rosendo says by desired outcome. Yeah. Rosendo, take that one step further. Oh, Leo says, oh, thank you, Leo. I think I missed this question. Thank you. So Vidor says, but then the choice of neural numbers is just it's initially just a shot. Vitor, not always. And we're going to get to that. Okay. We're going to get to that. Is it initially just a shot? It can be, but there is some guidance available, and we'll talk about that. Okay, we're going to talk about that. Vitor, if I don't give you a satisfactory answer, let me know, because you're asking an important question. Okay, so Yassine says using the weights. Okay, Yassine says represented as matrices. Okay, Yassine's on the right track here, guys. So how do they communicate with each other? These nodes have to talk to each other and decide whether to fire or not, right? Like how does your neural network decide like what path it's going to take to get to that output layer, right? Okay. So Bimala says Relu helps to fire the neutrons or decides to not fire. Okay. Osama says via weighted connections. Okay. Yeah. Yeah. Um I love how you guys are being creative in the answers. Um but sometimes it helps to be a little bit more formal, right? Because giving just a little bit of formality helps you also establish yourself as an expert, right? And Yassine, I just saw you put in the right answer. Well, I shouldn't say the right answer, but the answer that I had in mind. So Yassine is right. It's using activation function. That is what we should be looking at, right? Alberto says by mathematical representation, function weights, maybe. Yeah, so you guys are on the right track, right? You're on the right track in the sense that well, wait a minute. I know that I have different inputs and I know I'm going to assign weights to those inputs. That's every algorithm out there, right? That's y equals mx plus b, right? So you guys are on the right track. All of you gave great answers. But Yassine here has it. Yassine has it. Using activation functions. And that's really what I'm looking for there, right? They communicate or don't, right? Because there are situations where you're going to have nodes that don't do anything with activation functions. Nodes essentially exist to compute activation functions. That's it. That's what a node does. That's the whole purpose of a node. That's how we are representing the human consciousness of making decisions by having activation functions that take in a weight, right? Taking a weight and a factor, one of your inputs. It does some processing, whatever the algorithm is for that activation function, and moves on. It sends a value out, right? And that's the firing or not firing of the neural network, right? So Bimala mentioned Relu, right? Relu helps to fire the neuron or decides to not fire. Are there other activation functions? Put it in the chat. Give me some other activation functions. Because Bimala is correct that Relu is one of the activation functions. But what else is there? Rosendu says, what's an activation function? Yeah, Rosendo, good question. So an activation function is basically a math formula. That's all it is. It's a math formula that usually, in most cases, takes in a factor, a value of some kind, and it takes in some sort of weight that in most cases is previously assigned from a previous node or a previous layer. And then this layer says, okay, I now have this function, I now have this factor, and I now have this weight. Those are the two parts that are then given to your activation function. And your activation function takes that, it acts as a math formula and does its computations, and it basically says yes or no at the end. I'm simplifying that, right? It's not always a binary output, but that's all it does. It basically takes in a factor and a weight. It does its own computation according to what kind of activation function it is, because there are many activation functions, and spits out an answer. But that's all it is, okay? Okay, so Kago is coming up with sigmoid, Yassine, sigmoid. Yep. Softmax from Landry. Softmax again. Yep. Osama says Relu. Yeah. So let me ask you guys something. Can you come up with your own activation function? Do you have to stick with these activation functions? Give me a yes or no on that. Are there are you allowed to have your own custom activation functions? Okay, Yabba Dabba Doo, great name by the way. I love the name. Over on Instagram says like independent variables and their coefficients and regression. Yes, yes, I love it. I love the way you're putting this. Yes, absolutely. I did mention y equals mx plus b, right? Which is your standard regression. And the mx part of that is exactly that, right? The m is the weight, the x is the factor, right? The feature. So yes. And and perhaps I shouldn't overlook that so quickly because that helps you. I think that also helps to take the intimidation factor out of neural networks when you start to realize that, wait a minute, all I'm doing is taking a feature and a value, and all I'm doing is a feature and some weight that I want to attach to it. That's it. Like that's all we're doing. We're doing it a lot, and there's a lot of nodes and there's a lot of layers, but that's all we're doing. Y equals mx plus b. That's all you're doing. So Yabba Dabba Doo, thank you so much for bringing that up. Yes, you are absolutely on the right track when you think about that. What is the factor that you want me to consider, and what weight do you want me to assign to it? That's it. That when you see these like complicated charts and these nodes, that's all you're doing. You're just passing on those weights and features, right? Each one of these arrows, that's like the little transport packet, right? Here's the feature, here's the weight, go do your own calculation. That calculation finishes, it gives it a new weight. Here's the factor, here's the weight, go do your own. That's all you're doing. Because in turn, that's what your body's doing, right? If my brain wants to move my hand up and down, the cell here is telling the same thing to the cell here. That's the cell here. Move your hand up and down. It's the same message, right? It's just different ways of doing it. So that's all you're doing, right? You're just passing along the same message. So Yabba Dabba Doo, thanks so much for that. Yeah. Okay, yep. So everybody is saying yes to the custom activation functions. Here's the thing, guys. The reason I'm asking about the custom activation functions is because I also want to put that as a little bit of a warning. I think sometimes people get too caught up in the need for custom activation functions. Unless you're doing something truly, truly special, you probably are overusing any custom functions that you have, right? Because there's plenty of activation functions to choose from. There's really no lack of them, right? So keep that in mind before you go down a road or before you come across a tutorial or a snippet or something that talks about, using custom activation functions. Because with all the neural networks that I've worked with and whatnot, very, very rarely would you ever need some sort of custom function. But the reason I ask that is just to kind of illustrate that the activation functions have a fancy name and all that, but it's just a math formula. You can do whatever you want. It's just a weight and a feature, and you can just sit there and say, well, if the weight is more than 0.5, I want to say yes, and if it's less than 0.5, I want to say no. It can be that simple, right? It can be whatever you want it to be. All right. Leo says keywords so far. If you want to study independently after the class, nodes, layers, weights, and activation functions. Thank you so much, Leo. I appreciate that. Kago says I should actually be able to justify why I am using a certain activation function. Sure. Kago, I don't know if that's a question or whatnot, but is that a question or a statement? Landry says it's just a mathematical rule. You define that transforms a number. Yeah, absolutely, Landry. Yeah. Thank you for posting it, Landry. Maybe I should have read your comment, but yeah, but similar to what I just said, right? It can be whatever you want. You can define the function yourself. But again, you'd have to be doing something really, really special to not use the ones that are already out there. Leo says, agree, Kago, certain models are going to require different functions. Sure. So Kago says it was a statement. I should actually be able to justify why I'm using a certain activation function. Um, sure, sure, Kago, but also realize that some of those activation functions are going to be defined for you, right? Um, it depends on what you're trying to solve. Are you trying to solve a binary problem? That's one kind of activation function, right? Are you trying to solve an NLP problem? There's some activation functions that lend themselves better to that, right? So you will be able to justify it in many cases just by what you're trying to solve, okay? So keep that in mind. We'll definitely be exploring that later weeks in this series. I don't think we'll be exploring that too heavily today, but, you know, just keep that in mind going forward. But you're on the right track. Thank you for that, Kago. All right, guys. So we just agreed that there can be a lot of nodes, that there can be a lot of layers, and all those nodes and all those layers are interconnected in some way. That's the network side of neural networks, right? Does that come at a cost? What are some of the problems that you guys can anticipate with that? Does that come at a cost? Are there any pitfalls there we should think about? What do you guys think? Let me know in the chat. What do you guys think? Everything's connected. It can be whatever we want it to be. It can be as big or as small as you want it to be. And we know that there's a lot of math going on in each one of these nodes, right? Because each one of these nodes, we're basically saying that each one of these nodes has their own little computation going on, right? What do you guys think? Does that complexity come at a cost? Okay, so Yassine says computation. Tell me more, Yassine. Kago says if it's too big, the model might struggle to generalize the unseen data. Overfitting. Okay. Vidor says basically cost time. All right. Osama says GPU. But why, Osama? You're giving me a conclusion, and I don't disagree with your conclusion, but why? Why GPU? Bimala, nice. Interpretability, yeah. Yeah, I mean, does this sound very interpretable to you guys? If I'm telling you that I have 30 layers and 100 nodes per layer, and I'm doing mathematical computations at each one of those, does that sound very explainable? Probably not, right? So Bimala is hitting on a very important point. Right? Explainability in neural networks isn't great. I know. There's been tools that have been developed since then. They have become more explainable. I get it. But, we're building from the ground up here, right? And in traditional, in traditional neural network education or understanding, neural networks don't have a great reputation for interpretability. So that's one of the complexities, right? It's really math based. So it's just not very friendly to be able to tell business people, hey, this is our conclusion and we think it's because of X, Y, and Z that you're doing. Neural networks are not great for that. Rosendo says the more pathways, the longer it takes to get to an outcome. Yeah, that's exactly right, Rosendo. That's exactly right. Yassine says it requires parallel calculations. Doesn't require it, Yassine. It's highly beneficial if you can do them in parallel, right? And that's one of the reasons why GPU is popular. But it doesn't require it. It just makes it more convenient, right? So keep that in mind too, guys. Landry says, at Leo, a math rule that changes a number, the neuron's output before sending it to the next layer. Yeah. Yeah, Landry. Landry, you're getting pretty close to another thought I had in mind. But we'll keep going here. Osama says, huge number of mathematical operations, especially matrix multiplications. Yeah, absolutely, Osama. And that's definitely one of the reasons why GPU is beneficial for neural networks. So guys, I want you to also pay attention to Osama's answer, because Osama is also bringing up something really important. He says, especially matrix multiplications. And he's right. A lot of these things are handled as matrix computations and matrix multiplication. And we'll get to that in later weeks, right? But this does set itself up nicely for matrix multiplications. But the key word in there isn't matrix, it's multiplication. What do you guys think? Does that bring additional complexities? What do you think? What other complexities could there be because of multiplications? And this one's important, guys, because when you're working in business, right? People are going to ask you, okay, Yassine, I'm bought into your solution. Are there any risks here with your solution? And these are some of the risks, right? I'm kind of asking you. I say complexity, but I'm really asking you, what are the risks here, right? These neural networks sound great. You're telling me I can represent a brain? That's awesome. But are there any risks? Like, should I know about any downsides? Everything good has downsides, right? More layers and nodes equals more calculations, more time and money. Yep, Landry is absolutely right. Neural networks are usually not very fast to train, right? And you see that now in generative AI, right? Because generative AI, we'll get to this later, is based on neural networks. I mean, Sam Altman has said that in interviews, right? That they have models that are taking months to train, right? They are GPU and they are time constrained. That they know that they can't release models for months from now that they presume are going to be much more powerful, but literally take weeks and weeks to process, right? Even with their resources and their multiple data centers and distributed computing and all that, right? Some models just take a really long time, right? Yes. Well, let me come back to you. See, Leo says, well, sometimes I don't trust my own brain, so it's understandable asking this question. Yeah, absolutely, Leo. And you're going to be asked this question, guys, right? A smart boss or one of your smart leaders isn't just going to say, okay, great, I don't want to hear anything else. Just go ahead and go for it. They're going to want to hear the downsides, right? And honestly, if you want to be a responsible data scientist, you also want to be proactive about presenting the downsides, right? So so Yassine has hit the answer I had in mind. Yassine says vanishing/exploding gradients. Yeah. So you should know that in neural networks there's something known as the vanishing gradient problem, right? Going with Leo's previous theme, if you want to Google something, Google the vanishing gradient problem. What happens when you multiply a number times a number, guys? And more specifically, what happens when you multiply a decimal times a decimal? Because most weights and stuff, we're talking about decimal values, right? We're usually talking about whole number values. You're usually talking about decimal values, right? What happens when you multiply a decimal times a decimal? So put your answer in the chat. What happens when you multiply a decimal times a decimal? Rosendo has the right answer right off the bat. It gets closer to 0. That's exactly right. A decimal times a decimal results in a smaller number, right? And that's exactly the vanishing gradient problem, or the exploding gradient problem, as Yassine put it, right? So going back to our charts, if you take zero point 0.5 times 0.5 here, okay, and now you're taking 0.25 times 0.25 here, okay, and now you're taking that number and that number. Next thing you know, by the time you get to your 10th layer, you've got zeros. And if you're doing that for all of your nodes across multiple layers, you basically have nothing, right? So that's known as the vanishing gradient problem. And that's something that you absolutely need to be aware of in when working with neural networks. Because all of those activation functions are great until you realize that, wait a minute, all I'm doing is moving decimals around. And if I keep on multiplying those, I eventually get nothing. Right? Or, it's always going to be some value, but it'll be some ridiculously small value that's approaching zero. Right? So we're going to talk about different ways to battle that. But I thought I'd include it here in the first one because this is one of my interview questions. I think this is a fairly common question that you would come across in an interview that's asking you about neural networks, which is basically the same most like data scientist interviews, right? It'd be really hard for you to get through a data science interview hiring cycle and not ask about neural networks, right? But that's something you need to be aware of from the very beginning. Neural networks sound awesome on paper, but the reality is that they do have some downsides. And that's one of them. That if you don't track it closely, you can get to a situation where you basically end up with zero on the back end. Leo says, that's a great question. Thank you, Leo. Kago says, so does this mean a network with fewer layers is basically better than a deep network? Not always, Kago. Not always. Because depending on the problem, you're going to need a deep network. And there's ways for you as a data scientist to combat the vanishing gradient problem. I won't say some of those today because we can kind of leave that as a little bit of a homework. Like I said, if you guys want to go out and Google the vanishing gradient problem, and maybe you'll come across some of those answers. So yeah, Kago, you shouldn't take it to mean that. You should just take it to mean that it's something you need to be aware of and you need to be kind of vigilant about. Okay? Landry says complex models can memorize the training data instead of learning patterns, which is another issue. Sure. Yeah, I mean, all models can have that issue, right? In the sense that it could be like an overfitting issue by, I want to say like by mistake or like by casual usage, right? But yes, Landry's right that neural networks can be overfit in a very significant way. It's a lot easier to do that than you would think it is, right? All right. So I think we've covered some of that complexity. And again, these are all things for you to think about because if you want to be responsible and present a balanced view of your work, you would always bring up the complexities, or you're going to be asked these things, right? Before somebody gives you a green light, before they fund your project, before they give you the budget, they're going to want to know the risks, right? So we ourselves should be aware of the risks, right? Okay, so let's talk about this. What are the requirements of an input layer? Right, let's keep going with the with kind of like the risks and complexities, right? So in the chat, let me know what are the requirements of an input layer? Anybody want to just kind of list off a couple things? Let me know. Also, what is the maximum value of input layers that we can have? If you guys want another question, try that one. Leo says, if you're interested in going deeper and in between classes, Make your own neural network by Tariq Rashid. It's great. Yeah, yeah, guys. And I recommend it at the end of this deck, Leo, but thank you for the reminder. Must have a factor weight. Max value is 1. Okay. Okay, Rosendo's on the right track there. Lanry says correct number of inputs. Yeah, Lanry. So what is the maximum number of inputs we can have in our input layer? Yassine says to have as many nodes as features. Okay. Yassine, can you think of any situations where you wouldn't know the number of features? Because your statement presumes that you know that ahead of time, right? Starry Vibe says input should match the shape of the data. Okay, but Starry Vibes, what if you don't know the shape? Yassine says yes. Okay. Yassine says NLP. That's exactly right, guys. You don't always know how many inputs you're going to have, right? You don't. So, you know, kind of by proxy, you can draw the conclusion that there are no rules to how many input layers, how many nodes you can have in your input layer, right? The only thing you know is you can only have one input layer. But nobody can tell you, oh, you can only have 100 max, or you have to have a minimum of 5. You don't know. And as Yassine correctly points out, NLP is a situation where you don't always know the number of features. So Starry Vibes, I'm sure you would have gotten to the same answer, but you know, same question is what I would have told you, right? What if you can't match the shape of your data? There's plenty of situations where that's going to happen, right? Okay, so Osama, I love your comment. Osama says neural networks can't process text or images directly. Okay, so Osama, you took the words out of my mouth because I want to build on what Yassine said about NLP. Because guys, we just said how neural networks are a mathematical representation. But what if you're dealing with non-math data? NLP is not math data, right? So what then? What are you going to do in that situation, guys? Text is not mathematical data. You can't assign a weight to the word dog. Right? They literally don't compute together, right? So Osama and Yassine, let's build on that. Rosendo, when we talk about NLP, we're referring to natural language processing. So basically, we're referring to working with text data. Okay. Alberto says numerical input in assigned weights. Yeah, but Alberto, but not everything's a number. The input I have is my cat is white. How is that? That's not a numerical input, right? The sentence "my cat is white." What am I going to do with that? Suborno, welcome. Suborno says transferring it into numerical data based on its color gradient if it's an image. Okay. Leo says tokenization. Yeah. Okay, both of you guys are on the right track. Leo's on the right track for NLP, and Suborno's on the right track for computer vision, image processing, however you want to refer to it. Right? Chet Jones says binary. Help me understand that, Chet. Because in NLP, you'd have a hard time using binary inputs, right? Like almost impossible, right? But Leo is on the right track with tokenization, right? This is another question I ask in my interviews, by the way. You would find this in my interview series on Instagram. What's tokenization? What's the role of tokenization in NLP? Manoj, so good to see you, Manoj. How are you, my friend? Manoj says, agree with Leo. Yeah, Manoj, you and Leo are correct, right? So for those of you guys that don't know, write this down. If you're new to NLP, right? Write this down. Token, because I asked this on interviews, and I've seen other people ask this. What is tokenization? Tokenization is the process of taking words and converting them to a numeric value that can then be understood by models, right? Because you can't put in the word dog into a model that we just agreed is mathematical representation of the brain. So you have to go through a tokenization step to take the word dog, assign it a numerical value, and then you put that into your model. Right? That's really important. And what we're really talking about is we're talking about data pre-processing. Not cleaning, but data pre-processing. Where sometimes, even after cleaning and all that preparation, you have to work with your data to get it ready for neural networks. So who was it? Soborno. So Soborno is talking about the same thing. Except in image processing, you don't need to do that, right? Because image processing does have numerical values, but in most cases, it's going to have more than one numerical value per pixel, right? Each pixel, in most cases, has an RGB value. And an RGB value is composed of 3 numbers. Or sometimes 4, right? If it's RGBA, I think it is, right? But the whole point is that you have to go through that pre-processing in order to be able to use it in neural networks. Because again, you can't multiply the word dog by a value, by a numerical factor, like, or a numerical weight, right? Yabadabadoo says, like dummy variables for categorical variables. Yes. Yabadabadoo, that's not a bad parallel, except that you can have so many more of them, right? Because, like, for example, tokenization involves using what's known as a dictionary in NLP. And a dictionary would kind of be like the same lookup as dummy variables, except there's a lot of them, right? In the English language, it's accepted that there's about 20,000 words that are commonly used. So that's about the size of most dictionaries you're going to find out there, right? 20,000, 30,000 words, something like this. So yes, you're on the right track, but it's just a lot more than what you would use in any sort of categorical variable situation. Okay? Rosendo says, learn tokenization in my current class, but makes a lot of sense talking it out. I appreciate that, Rosendo. Yeah, this is why I do these things, right? Because nobody else does this, right? Every neural network tutorial you're gonna find on YouTube starts with, so open up your Python editor and let's talk about PyTorch. Well, that's stupid, right? Because that's not teaching you neural networks, right? So, that's kind of why I want to do this in this session today. We're just talking things out, guys. We're just talking things out, right? And we're taking some of that mystery out too. Okay. But thank you for that feedback, Rosenda. I appreciate it. Leo says, don't keep these things with yourself. Yeah, absolutely. Landry says, so set text to tokens and tokens to numbers. Yes. The tokens essentially are your numbers. Right, Landry? But then it gets a little bit more complex than that. And I don't mean this to be an NLP discussion, right? And so I'm going to give you a little bit of what I mean by how it gets a little more complex than that. And then we'll come back to some we'll go deeper in future discussions. But let's come back to the comments by Starry Vibes and Yassine earlier, right? What happens if we decide to do an NLP model? And let's just take this as an example where we're going to have 5 inputs into our model. So we just discovered tokenization, as Leo correctly pointed out. And let's say we've tokenized our dictionary. So now we can take a sentence like my cat is white and sick, and we can tokenize that, and we can put it into an input layer here. And we have this model with 5 different inputs. But what happens when now you have this model with 5 inputs, but you have a word that has less than 5 words? Like, my dog is white. That's only 4 words, but we have 5 inputs. What do you think about that? What are you guys going to do then? I mean, you can't have a model just like you can't develop a separate model for separate words, right? Like you can't say, "Oh, well, for this model, I'm going to develop this whole separate model for just 3 words, and then I'm going to have this other model for 10 words, and I'm going to have another model for blah blah." Right? That doesn't make sense, right? What are you guys going to do in that situation? But while you guys are thinking about that, Manoj, thank you so much. Really good to see you, my friend. I know you've been a big supporter. Guys, if you see an icon next to Manoj's name, that means that he is a paid member of the channel on YouTube. Really appreciate support by people like him. I believe it's $2.99 USD a month. It helps me out. So if you want to buy a membership, I sincerely appreciate that. So something for you to consider. But Manoj, thank you so much for your support. Really glad to see you, my friend. And we're back streaming. We're gonna be doing this every Sunday now. But what do you guys think? What's gonna happen when you have a model that takes in 20 words as inputs, but your sentence only has 5 words? What are you gonna do? Nobody in the chat so far? What are you gonna do? Think about everything we've talked about, right? Yassine says we need different architecture. Yassine, I love you, my friend. You know that, but no, we can't do that, right? We can't have a different neural network just because there's different letters or different words, right? Manoj says, glad that you are back, Go. I appreciate that. Thank you so much, guys. I'm feeling a lot of love today. You guys are spoiling me. I sincerely appreciate that, guys. It's been a nice little welcome. I mean, obviously I was nervous because, it takes a lot for me to put these things together. And I don't know if you guys are going to like this. I'm just talking to myself, but really appreciate that. Thank you for the welcome, Manoj. Okay, so Vitor says, repeat the question, please. Okay, so Vitor, I'm proposing that we've built the neural network that you see here. And this neural network is designed for 5 inputs, which could be like 5 words, right? But what happens if you have a sentence that only has 3 words? What are you going to do then? Are you going to have a different model just for 3 words? But then you'd have to have a model for 10 words and 20 words, right? Yassine says, I meant neural network architecture like RNN. No, Yassine, because you'd still have the same problem on the input layer no matter what you're doing, right? No matter what type of neural network you build, you'd still have the problem on the input layers. Okay, so Rosendo says turn off some networks. I think you meant to say nodes, Rosendo. Turn off some of the nodes? Because it's 5 nodes, but you only need 3 of them, right? So Rosendo's on the right track, and then Lanry gives us the right answer. The answer is called padding. And padding is an NLP process where you can basically take your text, represent it into tokens. So now you got your text that's represented as digits, right? Because each token corresponds to a digit. And if that number of tokens is shorter than your input layer, you pad it. And we just said that we're multiplying, right? So you turn off the nodes by setting it to 0. Yeah, so Landry is exactly right. It's padded with 0, so the shape matches. Yeah, that's exactly right. And that comes back to Rosendo's answer. We are effectively shutting off those nodes by setting it to 0. Right? That padding nullifies those nodes, and you can essentially turn off that section from your calculations. Now, again, my purpose in me telling you that is not to have this deep NLP discussion. My purpose for you is to help you realize that neural networks have those little extra pre-processing steps that are super important. So if you want to become an expert with neural networks or with NLP or with CV, you're going to have to know all those tricks of the trade that correspond just to that. Right? So keep that in mind, that neural networks do require pre-processing. So let's build on that. If I'm telling you that it requires pre-processing while we're building this neural network and we're still running because we haven't run any tests at this point, right? We're still building our neural network, but I'm telling you about this pre-processing we need to do. What happens when you go to make a prediction? What happens when you actually have a built neural network and you want to make a prediction? Do you need pre-processing then too? Give me a 1 in the chat if you think you do, or give me a 0 if you think you don't need pre-processing. Give me a 1. Now remember, we're talking at prediction time, at runtime, right? Give me a 1 if you think we still need pre-processing, or give me a 0 if we don't need pre-processing. Put it in the chat, guys. What do you guys think? All right, we got a few ones coming up. Yeah, that's exactly right. So keep that in mind, because that's also unique to neural networks. Not every algorithm out there requires pre-processing, but neural networks do. So now take that a step further. We talked about tokenization. I mentioned dictionaries. You might be applying different transforms to like your image data, the way you're handling the RGB values. It's super, super important to keep version control on those items. Because let's say during your training, you use one tokenization method, but on your runtime and your prediction side, you're using a different tokenization method. Are good things going to happen or bad things going to happen? If you're not using consistent dictionaries and consistent tokenization methods, are good things going to happen or bad things going to happen? Like, obviously bad things, right? I've seen teams go wrong here, where you get things lost in the mix, right? There's not enough communication among teams, or you lose, version control or whatever the case may be. Really, really bad things are going to happen in that scenario, right? So you have to be consistent on the pre-processing you do for training and what you do at runtime. Super, super important, guys. Rosenda says pre-processing in this context where you refer to tokenizing your data. Yeah, for NLP, yes, Rosenda. I'm talking about things like that. There's more to it than that, right? Because NLP can have multiple pre-processing steps. But yes, for the purposes of our discussion today, I'm referring to things like that. So if you're tokenizing one way in training and another in production or runtime, it's going to be a bad day. It's going to be a bad day. Leo says, that's funny. Yeah, but I've seen it happen, Leo. It happens. So that's, I think I've made my point there. But my point to you there is, think about that input layer, because it's unique to neural networks that you might not have at other ones. Because think about this, guys. I know some of you have been with me from these series from the beginning. Is like when we talked about regression. In regression, you don't have to worry about that, right? Regression, you kind of just like build the model and you're done. But in neural networks, it's kind of unique that you have to do that. Okay, so what are the requirements of a hidden layer? Let's move on. Let's move beyond the input, right? What do you think about the hidden layers? Give me some thoughts in the chat. What are the requirements there? Landry says, my teacher said pre-processing is like brushing your data's teeth before coming to his. That's funny. That's funny. I think he's trying to send a message to the class there, Landry. That's funny. Okay, but let's leave the inputs for now. What about the hidden layers? Hi, Dennis. Alicia from Phoenix. Great topic. Thank you. Alicia, so good to see you. Glad you're here. Hope you're doing well on this Sunday. Thank you so much, my friend. So, Alicia, we're talking about neural networks. Feel free to share your thoughts. But what are the requirements of a hidden layer? Let me know in the chat, guys. Obviously, the question's open to everyone. What do you guys think? What are the requirements of a hidden layer? And then if you want to think ahead, you can probably guess that I'm going to ask you what are the requirements of an output layer, right? But what are the rules around hidden layers? What do you guys think? Rosendo says should not be 0. Yeah, Rosendo. That's a good one, right? You have to have at least one hidden layer, right? You can't go from your input layer to your output layer. So yeah, I'm on board with that. What else, guys? Go ahead and put them in the chat. What else is there? Anybody else? Last call. What are the requirements of a hidden layer? Leo says, let's think intuitively. Osama says regularization. Landry says number of neurons, activation function. Rosenda says I was referring to the weight can't be 0. Rosendo, but you were right the first time. Don't correct yourself if you were right the first time. You should have said, "Yup, that's what I meant." The weight can't be 0. Okay. Starry Vibe says layer type choose based on the task. Yep. Well, look, guys, the fact that I thought all of you were quiet was kind of like the right answer by proxy, right? Because the answer is that there are no rules. I mean, we kind of cover that a little bit, right? You can have as many hidden layers as you want. You can have as many nodes as you want. There's no rules to it. Now, all of you are still correct in the sense that you have to declare how big the layer is, right? And you have to declare what activation function you want to use for those nodes. So I'm looking at Landry's answer, and he's right. But otherwise, there are no other rules. You can say this network has 5 layers or it has 500 layers. You can say there's 10 nodes or there's 500 nodes. It can literally be whatever you want it to be. So keep that in mind, that when it comes to the hidden layers, you're the architect. You're deciding. There's really no hard and fast rules. There's not a lot of protocol to follow. I mean, what you guys are mentioning is correct, but those are more just the requirements of kind of like the framework, right? That you have to declare the number of nodes, or it can't be a dynamic value, right? But otherwise, it can be whatever you want it to be. So, coming back to some of the questions that were asked earlier, right? Think of it. Let me ask you guys something. If we can design it any way we want, then can we consider the number of layers and the number of nodes to be a hyperparameter? And for those of you who don't remember, when I'm talking about hyperparameters, I'm talking about things that we can tune and we can adjust during our experiments. So Yassine is already saying yes, and he's right. I know that some people would debate my usage of the word hyperparameter there, if you really want to be strict about it, but the design of your network itself can be an experiment. Like you can say, hey, this data is working okay, but you know what? I want to try doubling the number of layers I have. I want to experiment with that. I want to reduce the number of nodes I have. I want to experiment. You can do that. Those are valid experimentation functions. Or I shouldn't say functions, just to not confuse people. But it's valid experimentation methods. You can do that. You can say, hey, I'm feeling really good about my data. I'm feeling really good about my pre-processing. I think I just need more layers. You can do that. That's valid. It takes a long time. It might take a lot of processing power, but it's totally valid to say, I'm going to mess around with the structure of my algorithm. I like where all my other parameters are at. I'm going to run 10 experiments with 10 different sizes of networks and see where I end up. That's one of the beauties of neural networks. Because you couldn't say that for like a regression algorithm, right? Because you can't come up with more features, right? I keep on picking on regression, but you guys should know that it applies to everything else. But it's totally valid for you to say, let me just try a different architecture. I don't need to go back to my stakeholders for more data. I don't need to mess around with the functions. Let me just try a different layout of layers and nodes. So keep that in mind. Very unique to neural networks. The fact that there are no rules to a hidden layer is kind of like one of the strengths of neural networks. Okay? All right, let's move on. What are the requirements of an output layer? What do you guys think? Now remember, ultimately we're using these things to, we're using all algorithms to get to an answer, right? So what are the requirements of an output layer? Yeah, Yassine is on top of it today. You're fast today, my friend. I love that. So Yassine says to match the number of prediction classes, activation functions to match problem type. Yeah. So what Yassine is basically saying there is you're going to have a node for all of your possible results. Excuse me, sorry. So if you're going to have a binary problem, a yes, no, true, false problem, guess what? You're going to have two outputs. Right? That determines your output layer. But let's say you have let me illustrate that a little bit more, right? So if you're writing like a spam filter where you're taking in the contents of an email and deciding whether it's spam, what's your output layer? It's 2, right? It can be spam or no spam, right? There's no in between, right? So your output layer is defined for you because of that problem. Let's say you're taking in customer calls and you want to classify the customer calls according to 5 different departments that your company has. You're going to have 5 output layers, right? Because each one of those, not 5 output layers, you're going to have one output layer with 5 nodes. Excuse me, I'm glad I caught myself. You're going to have 5 nodes, right? Because you're going to have 5 possible answers, 5 possible company departments that phone call, that information was about, and you're going to give an answer accordingly. Okay? But Yassine is right. So your output layer is probably your most prescribed layer because it really does relate to what it is that you're outputting. Rosendo says, do you define the outputs or does that come from the algorithm used? It comes from the problem you're trying to solve, Rosendo. So it's more defined by the number of possible answers in your problem. And I mean your business problem, not like a math problem. Right? So like I said, if you're trying to classify the phone calls, the customer service calls to one of 5 departments in your company, then you would have 5 outputs. Right? So that's not a function of the algorithm. You're going to design an algorithm for that. You're going to design a neural network for that. But the fact that there's 5, that number 5 comes from the business problem you're trying to solve. Okay, you guys with me on that? So let me skip ahead here. Yeah, okay, cool. Okay, so we've already hit on some of these. But now that we've kind of broken down these layers and everything else, what are some of the challenges with neural networks? Yassine says also for activation functions, for example, if we have a regression problem, we have to use linear. Yeah, yeah. Yassine, I love where you're going with that. We're going to hit more on that in later weeks, but Yassine is correct on that because your output layers still do an activation function, right? But again, based on the business problem you're trying to solve, the activation function kind of be like prescribed for you. Okay. But yeah, thank you for that, Yassine. We're going to cover that more as we get deeper into the topic. So Rosendo, so again, guys, the question is, what are some of the challenges with neural networks? Rosendo says, I would think they take a long time to build. Yeah, absolutely. Yeah, because guys, I mean, I was very flippant in telling you that, oh, I'm going to try 10 new architectures for my neural network. Well, if each one of those neural networks takes you a couple days to build, you just extended your experimentation by like a couple of weeks, right? If you're saying I want to fool around and do like, 10 new architectures that I've never tried before, yeah, great idea, but what does it do to your timeline? Do you have the time for that? So yeah, Rosendo's on the right track with that. Vitor says, I think one challenge is to explain the construction for other sectors, people in a company. Yeah, absolutely. Absolutely, Vitor. This is one of those things where you can decide what it looks like, but it's not always going to make sense to everybody else, right? Landry says needs a lot of data. Yeah, absolutely. That's another potential challenge with neural networks. But Landry, at the same time, I would challenge you though, right? What is a lot? A lot is a relative term, right? So it's really just kind of dependent on what you're trying to solve and the problem, right? But what is a lot? For some problems, a lot of data is 1,000 records. For other problems, 1,000 records is nothing, right? So keep that in mind. Keep that in mind. Okay? Leo says that's why soft skills are also valuable. Yeah, absolutely. Thank you for that, Leo. Kago says one challenge could be we sometimes don't fully understand how the model arrives to its predictions. Yeah. Yeah. Yeah, Kago and Beecher, you're giving very similar answers, which is absolutely correct. Starry Vibes, it says local minima and saddle points. Yeah, absolutely. So we'll get to this a little bit later, but what Starry Vibes here is referring to is the process that a neural network goes to converge on an answer, right? The learning pattern, as we'll see later, of a neural network it's not linear, or it's not continuous. Is a better way to explain it. Just because it did good here doesn't mean it's always going to do well. It kind of goes in cycles, right? So the minimas and saddles that Starry Vibes is referring to is that until you do a lot of experiments over and over again, you never know if that network still has the possibility to increase its learning and its accuracy and all its metrics or not. You could just be in a saddle. You never know when you're actually at the network's final possible strength or minima until you do a lot of experiments, right? And in some cases, not all neural networks recover from those saddles. They kind of just stay there, right? And that's when you would have to play with more data or different types of nodes, different layers, so on and so forth. But it can be a little bit frustrating in that regard, that you never really know when you're at the network's highest potential. But we're going to get to that a little bit later in the series. But thank you for that, Starry Vibes. Osama says it has a mathematical basis, linear algebra and calculus. But Osama, all algorithms do, right? Maybe not linear algebra specifically, but all algorithms are based in math, right? I mean, that's kind of unavoidable, right? Landry says need GPUs, which can be expensive. Not always, Landry. Not always. So guys, I realize I may have misstated this earlier, and I just want to make sure of this. GPUs are definitely beneficial for neural networks because of the parallel computing, but they are not, I repeat, not a requirement for neural network development. I have done and deployed many, many networks on CPU alone. So it helps, GPU helps, but it is not a requirement for neural networks, okay? And I also say that because I don't want to discourage any of you from working at home on this. I don't want you guys to be saying, oh, I'd like to learn neural networks, but I don't have a GPU, or I can't afford to pay for a GPU on Amazon. You don't have to do that. You can do plenty on CPU, okay? Osama says high cost in time and compute. Yep, absolutely, Osama. Landry says choosing the right setup, basically everything you just covered, number of neurons, layer next. Yeah, Landry, you're absolutely right. And it kind of ties back to Starry Vibes comment also. You just never know. You just never know when you're at that best model, right? So doing that setup and kind of starting from the ground up and saying, I guess I can do 5 layers. I guess I can do, like, there's no guide, right? So yeah, Landry, you're right about that. The fact that there is no like prescribed structure can kind of like, make you feel like you're stumbling along at first with neural networks, right? So yeah, that's definitely another concern there. Leo says, especially if you're working under 20 gigabytes. Maybe? I don't know, Leo. I have a hard time in any problem, in any data science problem, just giving like a file size or a data size, because are we talking about data that has 5 fields or 500 fields? Because if you have 500 fields, then 20 gigabytes might not be a lot of data, right? That might not be a lot of records. But if it's only 5 fields, then 20 gigabytes might be more than enough records, right? So I don't know, Leo. I'm tempted to say that's problem dependent, not necessarily. Like I don't think there's like a heuristic number, right? So yeah, I don't know if I'm comfortable saying 20 gigabytes or any number of gigabytes. Osama says difficult to explain decisions. Yep, not very explainable. Manoj says only when training large data we need GPUs. Yeah, Manoj, absolutely. But again, I would encourage you guys that number is a lot bigger than most people think. Because again, same question that I asked Landry, what is large data? Like, what is large? In one problem, large will be much different large will be much different than another problem, right? So yeah, so it's all relative. But again, my point here is not to debate that with you guys. My point is that I don't want to discourage you guys from continuing your learning, from developing your skills, without, because you're saying, I heard it's complex and I need GPU. No, you don't. You'll be fine with CPU. Keep learning, keep working, keep developing your skills. You'll be fine. So that's really why I'm saying this, right? That yes, you do need GPU, or it does. GPU does help, but it's not an absolute requirement. Okay, so definitely don't be at home sitting on your hands just because you don't have GPU. Do it on CPU. You'll be fine. You'll be fine. Okay, I want to make sure. Let me just read through one of these a little bit more. Give me a second here, guys. Give me just a second, because I thought I had one more item I wanted to cover with. All right, I think it'll come back to me, but I thought there was one more item I wanted to cover on the challenges. Thank you, Leo, for the updated keyword list. Appreciate that. All right, let's keep going. If it comes to me, I'm going to stop mid-sentence, but I thought there was one more thing I wanted to cover. All right, so I'm pretty sure this is my last slide. Yeah. So one thing I want to leave you guys with: where does neural networks fit in the grand scheme of things, right? So if we think about data science as a collection of like these big study items, I think it's fair to start with statistics, right? Like just understanding numbers. The second level would be like analytics, right? How do you make those numbers mean something, and like, get insights from your, like, initial form of numbers, right? And then from there, you're getting into like machine learning, right? Like modeling, essentially, right? Because analytics aren't always models. Analytics aren't always forward looking, right? They usually don't do great outside of their established range. But that's where machine learning comes in, right? And is able to make predictions and whatnot, right? And then after that, it's kind of like neural networks, right? Like neural networks is still modeling, but it's like massively bigger and more capable than most machine learning models out there. Again, not trying to poo-poo machine learning models, and we should always keep an open mind to it. But this is the progression that I think is fairly standard for most people to follow, as far as like how they develop as data scientists. I'm not proposing this as a study roadmap. I'm just saying that in all the skills you could develop, this is, I think, a fairly standard stack for most data scientists. And the reason I kind of wanted to close out with this for you guys is because kind of sharing my own experience. This is basically like kind of like the learning progression that I followed, but I felt that like in my own understanding, in my own like usage of data science in general, it really took a step forward when I started understanding neural networks. Like, because if you don't know anything about neural networks and you're at the machine learning phase, you're basically learning like that, like the ISL book, right? Like the Introduction to Statistical Learning book. That's essentially a machine learning book, right? And it's like, yeah, okay, I kind of get that, and I understand why you need clustering, and why you need to do dimension reductionality and stuff. Like you like I kind of like understood it, But once I got to understand, but once I understood neural networks and the inputs and the layers, and it can be whatever you want, and it represents the human brain, that's when I was like, whoa, like mind blown. Okay, now I get why people are so hyped up about data science. So that's why I wanted to kind of share this with you guys, because I want to get you guys excited about it. Because for me, that's really when, like, I really felt like I was taking steps and like leaps and bounds forward, right? Because like when you're studying like the other stuff, don't get me wrong, obviously it's powerful and I still use it and it's very interesting. But I was like, okay, yeah, like I guess this is feeling like innovative, right? But not really, right? But when you start learning about neural networks and the different nodes and the different functions and and um, just the way they're used, then it was like, oh, okay, I get it. Like I understand why people think that data science is going to be the future. Because remember, for me, this is like 10 years ago, right? 10, 12 years ago. But I'm hoping that the same thing will happen for some of you, because it's kind of like, okay, yeah, like neural networks are pretty powerful, right? Like you start seeing that. And I think you'll start seeing that as we dig more and more into these, right? Where you can start saying, okay, yeah, like I'm getting it. Like I'm understanding the power of data science. I'm understanding why NVIDIA makes so much money and why these models take so much time to train and things like that, right? So I'm hoping to be able to kind of pass that on to you guys, because it was really transformative for me to learn about neural networks. Like I was already excited about data science. I was already passionate about it, but neural networks was like, machine learning is like level 7, neural networks was like level 20, right? As far as like my excitement level, my understanding of the power, my understanding of what I could do with data science, right? Because you can take a problem, you can understand like why you would need clustering and things like that. But neural networks, I think, feels a little bit more real world, right? Like you can see how you would use neural networks for like any number of things in your life, with fairly little effort, right? So that's why I wanted to share this slide with you guys, so you guys understand that I think that that's really kind of my goal here, to help you guys understand the power of them and why they're so different than regression or nearest neighbors or something like that. Okay. So based along those lines, and just like Leo recommended it earlier, this is the book. If you've seen my content before, you guys know that I'm really huge on this book. To me, this has been one of the most influential books that I've read in my career, like as far as understanding neural networks, right? And I'll give you guys the same advice I've given every time I display this book. If you want to know neural networks, well, first of all, keep on coming back, because your good buddy Dennis is going to teach you neural networks. But if you really want to do neural networks, do the same thing that I did. I went through this book and I did every single code example. He shows you how to do neural networks without any frameworks. He actually shows you like the math behind neural networks. And it's not overly complex, there's a couple sections, but it's not too bad. But that's what I did. I went through and I did every single example that he has. And then when you finish the whole book, turn around and do the entire book again, but this time do it with a neural network framework like Keras. Because that's how you'll actually be doing it, right? Nobody actually does the math in neural network anymore. It's unnecessary. You're going to use a framework. But if you really want to understand neural networks, do that. You're going to go through the book twice. The first time, do it just as he wrote it. Do every single Python example and all that. Get the code to work for yourself. Make your own changes, do your own experiments, blah, blah, blah. Understand what that code looks like. And then turn around, start from page 1, and do every single example, but this time using Keras. Because that simulates the real world, right? If you can do that, go through that book twice like that, you'll be well on your way to understanding neural networks. But of course, keep on coming back to this series, right? I think we're going to have like 3 or 4 more in this series. I don't know yet. But this book to me was really helpful. I mean, I'll keep on recommending this book until the day I die. It was a really good book. So something for you guys to keep in mind, okay? So Kago says, in what situation would a traditional machine learning model perform better than a neural network, especially when it comes to accuracy? You don't know. You don't know, right? That's why you do the experiments, right? Yeah. So guys, obviously, I'm hyping up neural networks right now, but I am in no way trying to poo-poo machine learning or anything else, right? Um, So Kago, you don't know. That's why you run the experiments. But then again, as I tell people, that's the job of being a data scientist. Like that is your job. Your job is to conduct experiments on data, right? So there shouldn't be a hard and fast answer, Kago. Like you don't know. Every problem is I can't talk all of a sudden. Every problem is unique. Every data set for every problem is unique, right? So you don't know the answer, Kago. But that's part of the beauty. That's why we're hired. We're hired to run experiments exactly like that. So Vitor says, so then data science can be a natural step to data analysts, or is a different path at all? It can be a natural step, Vitor. So Vitor, I know you're kind of new here, but as I always tell people who ask for career advice, a data analyst is basically the biggest step up between a data analyst and a data scientist is modeling, right? Most data analysts aren't good at modeling, but data scientists are. That's kind of the job, right? So yeah, so Vitor, you're on the right track in the sense that a data analyst can be a natural step, and the biggest part they need to add to their toolbox is the modeling side, right? Because most of your traditional like business analysts, data analysts, financial analysts, they only know the basics of modeling, not the deep stuff, right? Rosendo says, "Thank you for sharing. I would like to have I would like to have my mind be blown. I would like to have my mind be blown like that." Yeah, so I'm hoping it'll happen for you guys. I would love to inspire that in you guys. I don't know if it will or won't. I'm just sharing my experience. But yeah, but to me, it was really like transformative to learn about neural networks because it was like, oh, I get it. Like I totally get it now. Okay, like that was one of those moments for me. Yeah, Leo, that's exactly right. It's all under the data science umbrella. You won't model as a data. Yeah, that's exactly right. Yeah, so Vidar, Leo's giving you the same answer, right? That the difference is the modeling side. Yassine says, situations where we need interpretability and where the problem could simply be solved using statistical methods, no need for complicating what is simply solved. Yeah, yeah, absolutely. Now keep in mind, Yassine, that doesn't mean that other models or machine learning models are more easily explained. There's plenty of machine learning models that are terrible at explainability, right? Yeah, so let's make sure we leave that clearly, guys. Neural networks are hard to explain, but the problem of explainability is not exclusive to neural networks. There's plenty of models that are terrible at explanations, right? So yeah, so it's not exclusive to neural networks, but it's definitely more common in neural networks. Just want to make sure we're all on the same track with that. Leo says this book is great. Yeah. Thank you, Leo. And I love this book. I mean, Leo is a longtime member, so he's heard me say plenty of good things about this book. But I mean, I recommended this book in my content plenty of times because it really helped me. So I hope it'll do the same for you. The guy has a great writing style. To me, maybe if you don't know anything about data science, the book isn't consumable. But if you're at least reasonably involved in data science, the book is very easy to understand and very reasonable to consume. So I hope you guys find it helpful too. Leo says, for the new people, join the Discord and feel free to keep the discussion there. Yeah, absolutely. Thank you, Leo. So I do run a Discord, because some people want to chat during the week, right? I'm only live on Sundays, but some people want to chat during the week. So feel free to join the Discord. Landry says, so you recommend I should learn how to build an NN at least once. Landry, I'm assuming that you're referring to building a neural network without a framework, like just with code. Yes, and we're going to be doing that in next week's session. That's where we're going to pick up next Sunday. We're already at 2 hours, but that's where we're going to pick up next Sunday. We're going to do it on our own, no frameworks. So yes, Landry, if that's what you're referring to, yes, everyone should do that once, right? do a neural network with just the pure code, no frameworks. And the Tariq Rashid book, it's up on the screen, does do that. So do that once, go through the entire book, no frameworks, just follow the examples he does. And experiment along the way, right? Make your own changes, make your own enhancements. And then turn around and do it with frameworks. If you can do that twice, you're going to be well on your way. Chet says, how often do you need to do data engineering tasks before doing your modeling? It depends. It depends, Chet. Because data engineering is a big topic, right? But it depends on any number of factors, right? How big is your data? How often do you need it? How often is it updated? But if you meant more about the data processing, because we talked about the data, pre-processing that's needed for neural networks, that can also be dependent. Are you doing a NLP problem? Are you doing a computer vision problem? With NLP, there's different ways you can tokenize. There's different ways you can do lemming and stemming. The tokenization is only one pre-processing step. There's another pre-processing step that comes around the sequencing and the vectors. So it kind of depends, chat. There's really no end to that. Generally speaking, you want to kind of lock down your dictionary and your tokens. That's something that you typically wouldn't change. You typically wouldn't experiment with that. But you would experiment with other portions of the pre-processing. So unfortunately, there's no hard and fast answers there. And guys, keep in mind, this kind of reminded me of another thing. One of the downsides to kind of working with neural networks or with these like business projects is that a lot of these questions that you guys are asking about, like, Chet's asking about the data engineering, or somebody else mentioned about how you don't know how many layers to start with. Unfortunately, a lot of that's going to be dictated to you just by the time that your project in the workplace is allotted. Like sometimes you might just have to say, hey, look, I've been doing experiments. This is the best model I can get, but you're giving me a deadline of today. So this is the best model I have today. If you gave me another month, I could probably come up with a much better model. But if we have to ship today, then this is the best model today. So yeah, keep in mind, guys, that a lot of the stuff we're talking about, just because I'm giving you examples of these experiments, doesn't mean you're actually going to be given the time to do them. Sometimes you're just going to ship whatever is available at that time, like because you only had X number of weeks, right? So I kind of hate saying that because it's kind of stinks from a scientific perspective, but that's just like the reality of you got to ship something, right? And not every project is going to give you infinite time, right? So keep that in mind too, guys. Narena, is it Narena, or maybe just Naren? I'm a data scientist, as my role says now, but I don't feel like one. That's a common thing I get. I get a lot of clients that come to me for imposter syndrome. So if you want to, schedule a coaching session, I'd be happy to talk to you about that, because I'm guessing you don't want to talk about that publicly. But yeah, guys, if there's something I can help you with in private, you want to talk to me one-on-one, I also offer coaching sessions. I've been building up that side of my business. I have some really, really great clients right now, really people that I appreciate working with. So if you'd like to be one of those clients, feel free to contact me and we can get in touch. But Narena, what you're writing about here is very common. I have a lot of clients that come to me for imposter syndrome, or to build up their data scientist skills, or maybe it's their first time like in a formal data scientist role. So what you're feeling is totally common. Let me know, I can help you. Lallman says, if I work on building an LLM from scratch, is that a neural network project too? Yes, Lallman. So guys, this is another reason why I was kind of like really interested in neural networks, is because there are some advanced problems in data science that are kind of hard to do without neural networks, right? Like I had another client who came to me recently, and they said, well, I want to become an NLP expert. Well, when somebody asks me that, my immediate question to them is, how do you feel about neural networks? Where are your neural network skills at? Because, in the modern NLP approaches, it's very, very hard to be an NLP expert unless you're pretty well versed on neural networks. Like that's just a reality, right? You can't be a regression expert and expect to be hired on the NLP side, right? Like you can't really effectively do NLP with regression, right? So yeah, I mean, that's not a bad way to go about it, Lawman, or excuse me, Landry. No, who asked that question? Um, who asked that question? Did I delete that question? Weird. That question disappeared from my chat. Um, but yeah, I mean, if you're working on an LLM, neural networks, it'd be hard to do that without a neural network, right? Yeah, Leo is bringing up the competitions. There are definitely some competitions that we could all be making more use of. So Leo is heading up that side on the Discord. So definitely feel free to join the Discord and start up conversation there. See if you guys want to participate. Is it Matare? Matare says, hello, Sir Dennis, and hi, everyone. I really benefited from the lesson as a first-year data science student. I'm really benefiting from your work. Oh, thank you so much. I appreciate that. Thank you so much. Appreciate that. Appreciate that feedback. Keep on coming back. Every Sunday, guys. Every Sunday at the same time. Whatever this time was for you 2 hours ago, right? Because we've been going for 2 hours. I usually stream on Sundays, 1500 GMT. So keep on coming back. Leo says, last year, Yassine and I did a short study on gold and BTC that ended up being right. Let's keep learning and community working together. Leo, I love that spirit. Love that spirit. Yeah, and guys, it's a good time to be holding gold. If you guys know, I'm a big fan of gold. We've done some streams on it. So yeah, glad that you guys are doing those gold studies because it's a good time to be a gold holder. Yeah, Leo, thanks so much for all the cheerleading you're doing in the chat. Definitely come to the Discord, guys, as Leo is suggesting. Plenty of opportunities for collaboration there if you guys would like. But yeah, if you guys want to start building a neural network or LLM of some kind, that would be cool. But keep on coming back to these sessions on Sunday. Also, next week, we're going to go through doing a neural network without any code whatsoever, right? And then we'll also hit on some of this data pre-processing that we were talking about, because clearly there's some interest there, okay? So yeah, so thanks so much, guys. Really appreciate it. I think this makes for a good stopping point. Gosh, you guys made me go for 2 hours. You know how hard that is to go from like 0 stream to 2 hours? Jeez. This is tough, guys. I'm gonna sign off. I'm gonna watch my show. I always watch a show after this just to kind of decompress and all that. And yeah, but thanks so much, guys. Keep on coming back on Sundays, 1500 GMT. Closing words here. Leo says, "There's no better place than here, and better person, Dennis." That's a fact. Oh, I appreciate that, Leo. Thanks so much. Really appreciate that. Like I always tell you guys, I'm just trying to put out good information. You guys know I don't sell cheap courses. I don't, I don't ask anybody for money. I don't, ignore any scams that tell you I'm asking for money, because I don't do that. It's just not my style. What is my style is I do enjoy coaching people. I work with people one-on-one. So if you'd like to sign up for a coaching session, please let me know. Would love to work with you. I have a great roster of clients right now, and I can't tell you how happy it makes me to work one-on-one with you guys. Starry Vibes says, "I truly appreciate your guidance. This session has been incredibly informative." Thank you, Starry Vibes. I'm glad you found it informative. But it always worries me when the students tell me that, right? Like, wait a minute, like I shouldn't be your teacher. Like, don't you guys have your own teachers? What are they teaching you guys? But thank you, Starry Vibes. Always good to see you guys. Thank you for the learning. It was very great. Appreciate that. Thank you, Vitor. Appreciate you coming by. I think it's one of your first times, but keep on coming back, Vitor. Appreciate you. Rosendo, appreciate it, Dennis. Thank you, Rosendo. Michael, my good friend Michael, such a great supporter. Thank you so much, Michael. Thanks for the class, Dennis. Thanks for being here. Thanks to Michael. Thanks to everybody. So guys, as always, like I say, I worry about you guys. It's a dynamic world we're living in. So please, take care of yourselves, take care of your families, keep on coming back on Sundays. Um, really appreciate you guys, and I'll see you guys next time. Part 2 of neural networks. What I want to do is I want to start with a review, and then we're going to talk a little bit about the code goals that we want to achieve today, because we're going to keep on learning a little bit about neural networks, and then we're actually going to do some code creation, right? We're actually going to start coming up with code. But just like we did in other series, and I think in all of our series, we're not going to write the code ourselves. We're going to use AI to help us with the prompt. Well, we're going to prompt AI to help us with the code, and kind of see how AI can also guide us, right? Because that's all based on the premise that the data scientists of the future will be heavily aided by AI, right? If you're starting from a blank screen in the future and you're a data scientist, you're probably doing it wrong, right? So we're just going to kind of keep on building on that, right? Okay, so one thing I want to get clear from the very, very beginning is you guys know that I'm a big fan of this book, and a lot of this series and some of the charts you're going to see today, I'm drawing from this book. Now, I want to be upfront with that because I want to be intellectually honest. I'm not trying to steal anybody's work. I'm very inspired by this book. As I told you guys, this book really helped me in my learning. So I want to be clear that I am pulling some inspiration from this, and I am pulling some charts from this. I'm highly encouraging you to go out and get this book and work through this book. But just want to be upfront with that I'm not, I'm not trying to steal anybody's intellectual property. I'm very inspired by the book. And I'm kind of going in the same order that this book does, because I think that the order it does, it's very, just very logical, right? But at the same time, I'm building upon the work, right? We're going to be doing AI. This book doesn't really have any AI. We're not going to be using any of the code from the book. So highly encourage you to go out and get this book. And I'm just putting it out there because I want to be intellectually honest about this, okay? All right. So what's a neural network, right? We talked about this last week, about how if you're new to data science, or if you're new to neural networks, maybe you know other models, but not neural networks, it can be kind of intimidating, right? Like the word alone can be intimidating, right? Like neural networks, like, whoa, that sounds heavy, right? So this is it. This is all a neural network is, right? It's a mathematical representation of how the human brain works. That's it. That's all it is. And we talked about that, right? So if we're going to say that it kind of mimics the human brain, then let's understand the human brain a little bit, right? And we basically talked about how there's these cells all throughout our bodies. There's a flow of electricity, from left to right in this case. There's some sort of an input, and in the majority of cases, it's multiple inputs. It travels along the cell itself for some processing and thinking. And then it goes out to these terminals, which basically go out to other outputs, right? And also it's more often than not multiple outputs. So you have multiple inputs coming into this cell. The cell makes some sort of decision of fire or not fire and sends the information on, right? So again, if I'm lifting my hand, there is a collection of cells that are starting from my brain, sending electrical impulses down my neck, down up my arm, and that chain causes my arm to go either up or down, right? And then on this side of my body, nothing is happening. There's nothing firing because there's nothing being sent there, right? Nothing is being asked to be activated, right? So a simple network like this is a representation of that. Here are your inputs. You can have multiple inputs. Here are the additional cells where the information or the pulses travel. The cells do some sort of processing, or rather the nodes do some sort of processing. They decide whether to fire or not fire. and they go on and they send it to subsequent cells. In this scenario, this is a very simple neural network with only one hidden layer, but you can have any number of nodes and any number of layers. It's really just kind of up to you, right? It's kind of, that's one of those like just general architecture decisions that you make on your own, okay? But that's it. That's all a neural network is. It's just a mathematical representation. Each one of these nodes represents a cell. Each one of those nodes does some sort of processing to help decide what happens when, and you just kind of go on from there, right? We also talked about this processing that I keep on mentioning. There's a name for it, and the name is activation functions. So each of these nodes has an activation function that takes in some inputs, runs through the function, whatever that function may be, and gives a result. And based on that result, the node or the cell does or does not do something, right? So, audience participation time. What were some of the challenges that we talked about with neural networks? Let me know in the chat, because there are some challenges in working with neural networks. And even if today is your first class, even if you didn't attend last week, you can probably guess at some of those, right? So let me know. What do you guys think? VK says, where's the screen? So VK, right now you are watching on my vertical feed. I'm streaming both vertical and horizontal or widescreen. So feel free to click on my profile and you should see two streams listed, and you'll be able to see my screen on that one, okay? So guys, let me know in the chat, what are some of the challenges in working with neural networks? Okay. CJ is already putting up poor interpretability. Yeah. Yassine says vanishing gradients, interpretability. Cool. So who remembers what vanishing gradients are? We talked about this. Who remembers what vanishing gradients are? Can somebody describe vanishing gradients? Osama says, needs large data and interpretability, difficult to understand decisions. Yep. Doodle, what a great name. Doodle Dad Lifts says explainability, not being able to explain to stakeholders. Yep. Denelson says memory. Yep, definitely. Mooey time? Moo time, welcome. I think it's your first time. Welcome. Glad to see you over on Twitch. Moo time says values get closer to zero. Moo time, let me know. Was that a answer to vanishing gradients? Or Moo time, let me know. I think you're trying to answer vanishing gradients, but let me know. Anaren? Is it Anaren? Anaren says, how do you choose the right activation function? We're going to get to that. Great question. I love that you guys are headed in that direction, right? Because that is the next question, right? Like, activation functions sound pretty important. We should learn about them, right? So Denelson says, vanishing gradients is when the products or neurons get so small they become zero and inactive. Yeah. And Mood Time says, yes, that they were asking for, or they were answering for vanishing gradients. Yep. Starry Vibe says, is it gradients become too small or too large, making training unstable? Ooh. Okay. So Starry Vibes is asking an interesting question. When we're talking about vanishing gradients, are we talking about values becoming too big or too small? Let me know in the chat. You don't have to give me an explanation. Nobody's going to call on you. Just give me an intuitive answer. Is it because they're getting too big or too small? Manoj says runtime. Manoj, let me know more about that. What do you mean? I think you're on the right track, but give me a little bit more information. Yassine says requires good data pre-processing. Oh, that's a good one. Guys. Nobody's mentioned that before. I'm going to come back to that. But yes, Yassine, remind me of that if I don't come back to it. But yes, we definitely need to talk about that. Denelson says exploding gradients is the opposite of vanishing gradients. So the gradients get so big. Okay, cool. I love the explanation, Denelson. Wael says not knowing how they behave. Okay. Yassine, Ty, and Denelson all say too small for vanishing gradients. Yep. Brandon says vanishing gradients means that learning of the network slows down because the weights become small. Yeah, Brandon, but it's not just slowing down, it's that it becomes ineffective. Right? So guys, all of you are correct. Vanishing gradients are basically gradients that become so small that they approach zero. And why would they do that? Well, because a lot of values and weights that we're going to be dealing with are not big numbers to begin with. Typically, they're decimals, right? And what happens when you multiply a decimal by a decimal? It gets smaller, right? Decimals times decimals just results in a smaller decimal, right? Smaller and smaller and smaller and smaller, the more you multiply, right? So Brandon, it's not that they slow down, it's just that they're like everything just becomes zero. And then it just becomes 0 times 0. So in a way, it can kind of become a little faster because it's a simpler calculation. But yeah, I mean, you can basically nullify all of your work just because you have so many layers, so many nodes, so many inputs that you're just calculating yourself to death, basically. That's the vanishing side of it, right? Shashank over on Instagram, how are you? Says, hey, how are you, sir? I'm doing great, Shashank. Glad to see you. Welcome to stay on Instagram, or you can switch over to YouTube and join us on the widescreen. So Moo Time or Mooey Time says, I think it's because they are getting too small since called vanishing. Yep, that's exactly right. That's exactly right. It's kind of built into the name, right? Khalif says, sometimes optimization gets messy. Have to try different techniques. You're not wrong. But Khalif, isn't that a function of any model? Like you just described data science, not necessarily neural networks, right? Like we should want to optimize and streamline all of our models, right? Even if it's just like a gradient boosting model or something, right? So what do you think? Like what you described is not wrong, but it's not exclusive to neural networks. I guess is what I'm trying to get you to think about, right? Manoj says problems that occur during the execution or deployment of a neural network model. Yep. So Manoj is bringing up a good point, and I still see the answers that are in my chat, and I'm going to come back to those answers. But let me take a little bit of a detour here, because Manoj saying that the problems that can occur during the execution deployment of neural networks is very key, and it allows us to circle back to Yassine's previous statement about pre-processing. What are some of the challenges? Let me know in the chat. What are some of the challenges around pre-processing and deployment that also happen to neural networks, that are unique to neural networks, right? Because you have to be careful in any data science deployment. But there's some that are unique to neural networks. Or what does Yassine mean when he talked about pre-processing overall for neural networks? Let me know. What do you guys think? I'll give you a hint. Remember that I said that your nodes are mathematical formulas that take in inputs, right? What about text? Can a node take in text? How do you multiply text? How do you multiply pixels in an image? Right? Let me know. What do you guys think? Manoj says data quality issues. Manoj, that can be in any model, right? Any model has that. CJ says you mentioned tokenization last time. Yep. Okay. So you're on the right track, CJ. What is tokenization and why do you need it? Why did tokenization come up in our same discussion as neural networks? So give me a little bit more, right? Yassine says different input size. Yeah. That's a concern, right? Text doesn't always have consistent input. You can have sentences with any number of lengths and characters and words, right? Brandon says, for neural networks, you have to be careful that you do not introduce future conclusions, outcomes, merge into training data. I think this is called leakage. Brandon, is that unique to neural networks though? I feel like that would apply to a lot of models though, right? Let me know, Brandon. Maybe I misunderstood your statement. But remember, we're trying to focus on things that are unique to neural networks. Denelson says text needs to be tokenized and pixels need to be processed into the RBG values. Yeah, why, Denelson? You're so close. You're so close, my friend. Why? Denelson goes on to say tokenization gives text values that can be interpreted by the model as numerical values, and it can change the importance of a word or phrase as it trains. Yeah. So I think the portion I want to highlight in your answer, Denelson, is about the numerical values. And that's really the answer we're looking for here, guys. Remember that neural networks, it's all just numbers based, right? You can't multiply text. You can't multiply a pixel. But you can translate it into numbers. And that's what tokenization is, right? Tokenization is a numerical representation of text, right? So you can do that. And same thing for like pixels and images, right? How do you convert an image to something a neural network can understand? Well, you can extrapolate out the RGB values, right? So that's really what we're looking for. So let's take it all one step further, because who was it? Manoj mentioned the deployment, right? So what happens if you used pre-processing during your training phase? What do you need to do when you go to deploy an algorithm? What do you need to do when you go to deploy it in at a production or runtime or prediction time situation? What do you guys think? I'm going to come back to some of the previous chats that I skipped while you guys think about that. VK says interpreting becomes difficult. Yeah, absolutely, VK. A couple of people have mentioned that. And interpretability with neural networks is not great. They're not known for being interpretable. I know. Somebody's out there sitting, but neural networks are much more interpretable now than they... I know that there's additional tools and additional techniques that make them more interpretable. But from a learning perspective, like a history perspective, you should know that neural networks have kind of had this knock on them that they're not very interpretable. Brandon says, does this also have to do with gradient descent, where we have multiple local minima, and in this case, the steps become smaller and smaller, and like you say, converge to zero, and nothing is learned? Yes, Brandon, you're on the right track with that. The only thing I would add is that the multiple local minima is a problem that can happen at other times also. It's not exclusive to vanishing gradients. But yes, it can definitely be a side effect of that. So you're on the right track with that. Denelson says speed can also be an issue. Yep. Yeah, so here I want to remind you guys that neural networks are not fast to train, and they can also be slow at runtime, right? So you guys know that I'm not very bullish on self-driving cars, right? I think that we should be more cautious than we are about them. And this is one of the reasons, because most of those cars, most of that technology does rely on neural networks, and neural networks can have a lag time to them in their responses, right? Obviously, you can fix that with hardware, with the quality of the neural network, the way it's implemented, so on and so forth. But neural networks can add lag to your decisions, to the speed that you need things done at. So yes, Denelson is right. Speed is an issue. Just remember that it's an issue for both the training side and the actual runtime side. Okay. Wael says overfitting and underfitting. Yep. But again, that can happen with any model, though, right? You can overfit a regression model if you try, right? So you're on the right track, Wael, but it's not exclusive to neural networks, right? Let me pick up where this goes again. Yassine says different data types. What do you mean by that, Yassine? I'm not sure I understand that. Because the pre-processing should take care of that in the sense that you're only going to have one data type, and that's going to be long values, right? Which are usually decimal values. But yeah, so let me know what you mean. You see, maybe I'm just not understanding. Manoj says yes, tokenization converts text into numeric. Yep, absolutely. Very important step in neural networks. Khan says, "Hey Dennis, how are you?" I'm doing great, Khan. How are you? Hope you're doing well. I see you over on Instagram. You're welcome to stay there, or you're welcome to join us on YouTube for the widescreen. Okay. I think it's Umair. Umair on my vertical stream is asking, do neural networks have a functional form? Umair, let me know what you mean by functional form. Can you describe that a little bit more? What does functional form mean to you? I want to make sure I understand your question first. Let me know what that means to you first, okay? Brandon says, isn't a neural network limited in the number of layers and nodes? Would that represent a limitation of how accurate one can be? Ooh, great question, guys. Great question for the chat. So, Brandon is asking, is a neural network limited in the numbers of layers and nodes? What do you guys think? Let me know in the chat. You only have to give me a yes or no if you'd like, or give me an explanation if you'd like. But Brandon's asking an excellent question here. What do you guys think? Is a neural network limited in the number of layers and nodes? What do you guys think? Good question. So Moo says, since neural networks use math to mimic the human brain, so we need tokenization to be able to use math. Yeah, absolutely. Tokenization, very, very key part of data science, or of neural networks. So Moo goes on to say, we need to make sure that we use the same tokenization when training and deploying. Yes, that's exactly right. And Moo, I wouldn't say same tokenization, it's the same data pre-processing, because pre-processing also applies to image work, right? To computer vision work, not tokenization, obviously, but the same pre-processing you do there has to also be done on runtime, right? So what happens if you use a tokenization file during training, but you use a completely different tokenization approach or dictionary on your runtime? You'd have wildly inaccurate results, right? Or same thing for your RGB values. If the way you process them in training is different than runtime, bad things are going to happen, right? So that's really what I want to impress upon you guys, that it's all about the maintaining verity between your pre-processing during training versus what it looks like at runtime. Okay, very, very important part. Wael says, could need a huge amount of data as the neural network gets deeper. Yeah, but I think a couple people have mentioned the data. I think Osama mentioned the data requirements. Yeah, absolutely. Yassine says, yes, it was an answer to why pre-processing is needed. Let me make sure I remember different data types. Yeah, so Yassine, it's not that it's different data types, it's that it's not numerical. Text by its very nature is not numerical. So really that's, or same thing for images, right? Images aren't numerical. So really that's why we need the data pre-processing, because otherwise the neural network doesn't know that. You can't multiply, words by words, right? So it's more about, it's not the different data types, it's that it only supports numbers as inputs, right? Jaya over on Instagram says, hi, sir. Hey, Jaya, nice to see you. Hope that you're doing well. I'm glad to see so many people on Instagram today. That's wonderful. All right. Okay, so coming back to Brandon's question, Yassine is answering, no, it's not. We can choose the number of layers and nodes as we want. Denelson says no and yes, it is limited by the amount of memory you have, but hypothetically, it does not have a limit. Diffio over on Twitch, welcome. I think it's your first time. Nice to see you. Diffio says neural networks are limited in size, not in theory, but very much so in practice. Okay, Diffio coming in strong with their first answer. That's a great answer. So Diffio, Denelson, Yassine are all providing answers for Brandon's question. And all of them are correct, right? There is no limit on nodes, on the number of layers and the number of nodes within those layers. And if you remember, last week we kind of talked about how I kind of stopped short of calling them a hyperparameter, but you can kind of say, like, hey, I'm going to play around with the number of nodes and layers to kind of see if I can improve my results. Like, that's a valid way to construct these, right? There are dedicated hyperparameters for neural networks, but the architecture itself of the network is something that you can play around and experiment with. So Brandon, that's basically the answer, that no, there is no limit to layers and nodes. It can be, your network architecture can be whatever you want it to be. Now Diffio here is correct, and some other answers I've touched upon that I think Denelson mentioned speed, but yes, they are limited in practice because the bigger the neural network, the more time it takes to train, the more processing power you're going to need. The slower it is at runtime. We talked about some applications where you don't want a slow neural network, right? You might need very high speed neural networks. So no theoretical limit, but from a practical perspective, you might have to go with a smaller neural network than what you would like to otherwise. Okay. Starry Vibes. Oh, okay. Sorry, Starry Vibes. I missed your answer previously, but Starry Vibes contributing to the same answer says no. It just depends on your needs and the resources you have available. Yeah, that's a very, very practical answer. Yeah. Moo says, I think we have as many nodes as resources allow. Excuse me. However, whether it is needed depends on the problem, I believe. Yeah. Yeah. And I guess it's really not, well, it is depending on the problem in the sense that what gives you the better results, right? Like, that's really what it is, right? Like, that's really like the main driver, right? Okay, so Anna says, what kind of number is the tokenized word converted into? Is there a standard function applied to the word to convert it to a number? Okay, great question. So Anna, here you're kind of talking more specifically about like NLP related work. But when it comes to NLP, one of the first things you're gonna do is you're gonna tokenize your text, and it's basically just taking every word and assigning it a number. That's all you're doing. Every possible word, you're assigning it a number. So as you can imagine, the token dictionary, and it's usually referred to as a token dictionary, by the way. So as you can imagine, the token dictionaries can vary in size, and they'll definitely vary by language. But for example, in the English language, it's commonly accepted that there's about 20,000 words that are used in the English language. I think the total number is like 35,000, 40,000, but like in day-to-day conversations, it's like 20,000 words. So most dictionaries use that as like as a starting value, I guess you could say. And yes, there are some standard dictionaries out there. For example, um, a lot of the tutorials you're going to come across, or maybe stuff in your schoolwork, is going to mention NLTK, right? The Natural Language Toolkit. That's a toolkit that was put out, I believe that was put out by Meta or some engineers at Meta. So they have their own dictionary, their own tokenization. There are dictionaries that are based on social media that will take common words in social media. There are dictionaries that are based on Wikipedia, where they'll take kind of like all the words that you'd find in Wikipedia and tokenize those. And then beyond that, you get into some of the vectorization libraries or vectorization values. So the Stanford NLP Lab has put out some of those dictionaries that are popular for that, or vectorization libraries that are popular for that. I think that one is WordNet. So I'll stop there because my intent is not to make this an NLP discussion. But yes, there are standardized libraries out there, or you can make your own. So like NLTK gives you the ability to make your own, right? Because you might be working in a domain that has particular words or particular lexicon that is important to that domain. So it just kind of depends on the application that you're working on. But yes, there are like, widely accepted general libraries that are out there. Okay. And we'll get to that if we ever decide to have like a dedicated NLP series. But yeah, I mean, that's just the quick answer. And I kind of don't want to go beyond that, because again, it's really not my intent to do NLP. It's really more about neural networks in general. Okay. Manoj, yes, word to vector. I think word to vector is the Stanford one, and then WordNet, I believe, is put out by other people, if I remember right. But yes, word to vector is the Stanford one. Thank you so much, Manoj. Brandon says, "Thank you for the insights." Yeah, you're welcome. Just just trying to give you guys the best information I can in the best format that I can. I know it's your first time here, Brandon, but this is kind of how all of my Sunday series go, or at least I try to make them go like this. So Denelson also agrees with word to vector. Yeah, I think word to vector is the Stanford one. If you guys want to know more about this, just Google Stanford NLP Lab, and they have plenty of materials on their website. Okay, so let's keep going. So where do neural networks fit, right? And I want to give you this chart again, guys, because for me, this is kind of like the progression I have in my mind as far as like the different tools that you could be using, or the different ways you could be working with kind of data science in general, right? You can start out with statistics, and then that leads to analytics, and then you go on to machine learning, and then you kind of work with neural networks, right? And I shared the story with you guys that you can pick up machine learning, with tutorials and models, the ISLR book, which is basically a machine learning book. If you're interested in that, you can find my series on my channel. But to me, my learning like really took off, really like started blowing my mind when I started thinking about neural networks. Like when I read that book, I told you, the Tariq Rashid book, that's where I thought like, oh, okay, this is why data science is so like powerful, right? When I started doing that, it was like, oh, okay, I get it now, right? So obviously it can go beyond this into AI and things like that. But then again, most AI is based in neural networks. But this is kind of like the stack or the progression that I would ask you to kind of keep in your mind as far as how these tools are all kind of relate to each other. Okay. So over on my YouTube vertical, I see Lallman. Lallman says, Hope I wasn't too late. No, of course not, my friend. So Loman, you are on my vertical live. You're welcome to stay there or come join us over on the horizontal, which is where you usually join us. You can probably click on my profile, and it'll go to it should show you 2 live streams running at the same time. Okay. And actually, you know what? I kind of want to verify that real quick. So give me just a second here, guys. I kind of want to check that on my own. Yeah. So I'm looking at my own YouTube page, and it is showing me as doing 2 live streams, and one of them I've called the vertical stream. So Lalman, right now you're on my vertical stream. You're welcome to join me on the widescreen. Okay. Okay. Lalman is back. Lalman says I was confused why you decided to go with the vertical one. So Lalman, that's a good story. Good question and a good story. So because of my success due to you guys, and I really appreciate all of you for this. My channel has grown quite a bit over the last year. I do have my little YouTube plaque back there. So because of that, YouTube has sent me these invites to participate in these boot camps and these trainings, I guess you could say, for creators. And I have a what's it called, a community manager or something like that. They're supposed to be like my helper at YouTube, like if I ever need something. One of the things that YouTube has been doing over the past 2 months is they've really been encouraging people like me to use the vertical format. They're really trying to have many, many more vertical live streams. I guess because they're comparing themselves to TikTok, maybe, because TikTok obviously has a lot of vertical streams, so many more than YouTube. So they're kind of encouraging people to do that, and they're encouraging people and saying, well, you can stream on 2 things. You can stream both horizontal and vertical if you want, which is kind of weird because I don't think any other platform lets you do that, run 2 streams at the same time. But that's how much YouTube wants you to do it, because they're really encouraging people to do it. So I saw that this morning. They sent me a note about that this morning. And I thought, I'm going to try it. It can't hurt. I've never streamed twice like that. So that's what I'm doing. So yeah, so if you go to my profile, you're going to see 2 streams. You're welcome to stay on the vertical or the horizontal. It's up to you. But anyways, just giving you an answer there, Lalman, just to help you guys understand why I'm doing that. I'm enjoying the YouTube ecosystem. I got invited to one of their little get-togethers last month, which was a lot of fun. Like I said, I have this contact at YouTube, so if something ever happens, I got my own little personal tech support, which is nice. But just trying to see what the vertical offering on YouTube is like. All right, so getting back to the materials, this is new material, right? This was not in last week's deck. So let's talk about nodes, right? Because as I think has become clear to everyone, nodes are pretty critical in the whole study of neural networks, right? So again, being open and honest, I'm pulling this from the Tariq Rashid book, right? Very good book. Highly encourage all of you to pick it up. And this is what we're doing, right? We have 2 inputs, a 3 and a 4. There's some sort of calculation that happens in the center, and then there's some sort of output. That's it. That's all it is. If you do this across multiple nodes and multiple layers, you have yourself a neural network. That's it. That's all it is, right? So if you can see that, right? There's inputs, calculations, and outputs. What happens when an output is incorrect? Have we seen other models when an output is incorrect? What do you guys think? What happens if you were to have this calculation node and the output was 10? What would we do in that scenario? What do you guys think? Let me know in the chat. I mean, we kind of have to do something about that, right? What do you guys think? Anna says the loss function comes in. Yes. Yassine says we need to adjust that calculation. Yeah, that's right. Right? I mean, that's really the answer, right? That we would need to adjust. And we would need to say, well, wait a minute, we need to kind of retrain, right? Something has gone wrong in our training, and this calculation in the node is not correct. So we need to adjust that, right? Manoj says, matrix multiplication gone wrong within the nodes. Yes, but the matrix multiplication is more about the training, right, Manoj? Starry Vibe says it will come back. Starry Vibes, I'm going to take that to mean that you mean that it's going to be retrained, and yes, that's correct. Speaking of retraining, Osama and Denelson are both mentioning back propagation, which is arguably a form of retraining, or at least revisiting the calculation. Yeah, but you're exactly right. Right? Have we seen this in other models? I know many of you have been here for a lot of my live streams before. Some of you are new. That's okay. But have we seen this with other models? What do you guys think? Yassine says yes. Okay, tell me more about that, Yassine. Because you're right. We have seen other models. Tell me more about that. Where else have we seen this? Lallman says gradient boosting. Yeah. Anywhere else, guys? Where else have we seen this? Where the model output is incorrect? What do you guys think? Yassine says there are many models that use gradient descent in their process to adjust their parameters. Yassine says, as in simple linear regression. Yeah. So look, the whole purpose of me asking this of you guys is to realize that the way that we handle the training and the process of a neural network is not much different than what you already know. Again, I'm just trying to take like the mystique out of it, because I think so many people kind of get like caught up in how complex neural networks can be. But it's the same. It's the same as other items that we've seen before. It's going to make errors. You're going to go back and you're going to adjust, and you're going to go back and you're going to try to improve on your previous model. But overall, it's the same thing. Okay? So that's all I'm really trying to impress upon you here. That yes, you're going to have nodes that make incorrect calculations, but that's okay. You're going to fix them in the same way that we've tried to fix other models before. It's really no different than that. You're going to adjust your weights. Sometimes you can adjust your input, and then you're going to see what downstream effect it has on your results, and you're going to go from there, right? Just as Yassine says, just as you would in a simple linear regression, right? So speaking of which, what measures, let's build upon that, right? What measures did we use for model evaluation in the past? And also, what is a ground truth? I know most of you are going to know the answer to the second question, but I just want to establish a common understanding here, right? Or there could be some people that are also newer in the chat, right? So what did we use for previous model evaluation? Because we just agreed that we're going to fix the model in the same way we fixed other models. So can't we use the same evaluation metrics? Right? So what are they? And what is a ground truth? What do you guys think? MSE, and a ground truth is a recorded expected prediction from the data we collect. Yeah. Yeah, I think MSE is a pretty good example of what we've used in the past, but it's not the only one, right? So feel free to suggest other ones out there if you want, chat. But what are some of the metrics that we've used? And a ground truth is recorded expected predictions on data we collect. And that's true, right? A ground truth is basically what happened in real life. Not what we think would have happened or what the algorithm said was going to happen, but what actually happened in real life. So Yassine says, for regression classification, we have accuracy, precision, and recall. Yeah. And yes, we can use the same metrics. Manoj says, agree with Yassine. Yeah. Yeah. You guys are all on the right track, right? And that's exactly what we're looking for here. That regression, accuracy, precision, and recall are going to be as useful here as they were in other models. That's exactly right. That's exactly right. Okay? That's what we're looking for, right? Again, we're just trying to take the mystique out of it. We've talked a lot about nodes and layers, and we're going to see some code today, and we've talked a little bit about math. But it's the same thing. It's the same metrics that we're looking to work for ourselves, okay? So I'm going to jump ahead here because I already see some of these answers in the chat. What are we looking at here? What is this? And if you guys want extra credit, who wants to take an explanation? Give me an explanation in the chat for precision and recall. But here's the thing. Talk to me like a business person. Don't give me that math geeks talk. You guys know I don't want you guys talking like math nerds out there. Give me the business explanation. I'm your managing director. Tell your managing director what the heck this precision and recall thing is. Go ahead, guys. That's a challenge for the chat there. What is precision and recall? And talk to me like I'm a 10-year-old like I'm a 10-year-old managing director, because there are some 10-year-old managing directors out there. So what do you guys think? And if you don't know what we're looking at there, that's okay. You should know that what you're looking at is going to be a common a common theme throughout your data science career, right? This isn't exclusive to neural networks. What do you guys think? Okay, so Sravan says, how many times are we predicting correctly? Okay. Give me a little bit more to that, Sravan. You're on the right track, but I think we need to go a little bit deeper. So Denelson says, precision is how many it got right overall, and recall is how much it is able to remember accurately. Precision is how many got right overall, and recall is how it was able to remember accurately. Denelson, I'm tempted to give you a pass on the first one because you're not wrong, but I would ask you, didn't you just give me the definition for accuracy and not precision? And for recall, I'm not on board with the answer. I think the answer goes a little bit deeper. So take a think on that, Denelson, and come back, okay? Anna says, precision is how good the model is at correctly labeling the object as the original. Recall is how good it is at finding an object. Recall is how good it is at finding an object. Okay. I'm on board with the precision. The recall, I don't know. I don't know. And also, by the way, if somebody wants to just give an idea of what we're looking at for some of the newer people or whatnot, just feel free to tell me what we're looking at in the graphic, right? Is it Rexman or Rockman maybe? Welcome. I think it's your first time, so welcome to the stream. Rockman says, precision tells all of the times our model predicted something is positive and how many of those are actually correct. Yeah. But tell me like I'm a managing director, right? But you're on the right track there. Yassine says it's a confusion matrix. Yeah. So for those of you that are kind of confused in what's going on, or maybe not, maybe it's you're early in your studies, this is a confusion matrix. This is what's known as a confusion matrix, and it helps us understand what our algorithm predicted versus what actually happened in real life, or our ground truth, right? And by looking at how often the algorithm was actually correct in predicting what actually happened, or predicting the failures or the other classes versus what actually happened, you can come up with additional measures, right? You can come up with your accuracy, your precision, and your recall, right? So that's kind of what we're working through here. Okay, Yassine is going for the examples. I love it. Yassine says, we have two scenarios for some cakes we're cooking. Either the cake is good or overcooked. Precision is from the one that are good. How many are actually good? Recall is out of all the overcooked. How many did we identify? Okay, Yassine. I think we could massage a couple of words in there, but I think you're on the right track there. I'm on board with it. Starry Vibes says recall is the proportion of true positives identified among all the real positive cases, and precision is the proportion of true positives among all the total positive precisions. Do we reflect the validity of the predictions? I don't know, Starry Vibes. I could be misunderstanding you, but I don't know if I'm on board with this. It almost feels like you're describing the same thing twice. I don't know. Rockman says recall tells out of all the positive cases how many did our model correctly find. Rockman, I'm looking back at your definition of precision, because I'm not seeing enough of a difference from your recall and precision. I'm jumping ahead here because it's catching my eye. Diffio says recall is about not missing opportunities. Okay, Diffio, I think you're on the right track. Tell me more. This is great. I'm glad we did this exercise because, sometimes it's very difficult to express, because I'm positive that all of you are smart and all of you know how to use these, but being able to express it properly is kind of like it's actually difficult, right? And I'm asking this because this is a popular interview question, right? Tell me the difference between accuracy, precision, and recall, right? Now, in those cases, you're probably explaining it to a technical person, but you're also going to be explaining it to your management, right? I've had to explain this many, many times in emails and phone calls and meetings. So it's good for us to go through this. Okay, so Osama says, precision answers the question of all the positive predictions I made, how many were actually correct? Oh, I love it. I love it, Osama. I love it. So give me recall. Give me recall. I think you're on the right track there, Osama. CJ says, recall. Out of all the customers we predicted that 20 would subscribe rather than the 50 that actually subscribed. Okay, CJ, I love that you're putting it like in real terms. Take it one step further. Why would you need this number? Because you're giving me a good example, but I don't understand why I would need that number. Right? And I want you to think about Diffio's answer about not missing opportunities. Because you're right there. You're right there, CJ. All right. Denelson says precision is how many predictions our model gave are right. And the recall is how many of our ground truths we were able to predict either accurately or not. Okay, cool. Okay, Danielson. I like it. I like it. Maybe a little bit still too technical for a managing director, but I like it. You're on the right track. Okay, so Diffio says recall is not about is about not missing opportunities. Of all the customers who actually wanted our product, how many did we correctly identify? It has a cost. Great answer. And that's exactly it, right? So CJ, coming back to your answer, it's not about the 20 who would subscribe, it's about the 30 that you missed, right? Because you could say that your algorithm missed 30 people that did subscribe that you should have predicted as subscribing but didn't, right? So Diffio, I like the way you're putting this, right? Of the actual ground truths that happened, how many did we anticipate happening, right? Because that is important in most algorithms out there, right? Because if not, that means you're missing out on opportunities. You didn't correctly identify people, places, things that you should have targeted when your algorithm told you to not target them, right? Okay, so Anna says, I'll take another stab if you don't mind. Feel free, Anna. Feel free to keep the answers coming, guys. You guys can answer anytime you want. If a model detects 100 objects and only 80 correct, that's 80% precision. If there are 100 ground truths and the model can only detect 70, the recall is 70%. Yeah, I like that. I like that, Anna. You got to put it into business terms for most managing directors, but you're on the right track there. Yeah. Okay, Osama says recall. Of all the actual positive cases, how many did I correctly identify? Yeah. All right. I love it. You guys are. We got to an answer, chat. Right? We kind of felt around different things, but I'm glad how the chat kind of converged on an answer because I think you guys are basically there. So Lawman says, precision is out of all the positive cases, how many were correctly predicted as positive? And recall is of all the positive cases, how many were correctly predicted as positive? Yep. That's great, guys. Did that disappear? That's weird. That's the second time that's happened to me. Where a chat disappears from my window. That's weird. Lawman, I don't know if you removed that chat, but it felt like you were on the right track. I mean, I wanted to read it again, but I think you were on the right track, or maybe I deleted it I don't think I did. Let me know, Lawman, if you deleted that or if I deleted that. But that happened last week too. Weird. Okay, but yeah, you guys are on the right track. Very important to understand this because this is what basically tells you whether your neural network is on the right track. Do you have the right number of layers? Do you have the right number of nodes, right? Do you need to adjust your hyperparameters? By looking at these numbers, these results is exactly what you want to do to refine your algorithm. This is how you create that feedback loop to be able to say, yeah, this is a pretty good neural network, or no, we got a lot more work to do. Okay. Diffio says, I've never seen someone streaming on so many platforms simultaneously. Thank you. I think. You know what? The technology exists, right? So why not do it? And I have enough followers on all the platforms that I go ahead and do it. So, you know, streaming has been very good for the growth of my channel. So yeah, I guess it is a lot, but you know, have some fun with it, right? Diffio says it's great. I just imagine the complications. There's software that helps me a lot. But it did take me a while to figure out all the components and getting it all to work and talk to each other and all this stuff. But yeah, glad you're enjoying it, Diffio. Lawman says, I recall the answer both times. I thought it was wrong. Oh, okay. Listen, guys, there's no need to be shy about wrong answers on my chat, right? I mean, you know, I try to tell you whether you're on the right track or on the wrong track, but there's no shame in it, right? But Lawman, from what I read, I thought your last answer was on the right track, you know? Manoj says, Precision says, of the kids I gave the chocolate to, how many actually like? Yep, that's a good one, Manoj. Because you would think all kids would like chocolate, right? But you never know. Ria says, hi, can you get me a job? I am ready to work under you. Ria, I myself am not a source of jobs. I can certainly help train you to get you a job. I do that as part of my personal coaching. So if you are interested in personal coaching, there's a link in my Instagram bio. But I myself am not a source of jobs. But I get it, guys. It can be challenging. It can be frustrating to get a job. I'm here to support you. I'm here to teach as much as I can. And if you want personal coaching, we can do that too. Okay. Recall. So Manoj, to close out his idea, says, recall of all the kids who like chocolate, how many did I find and give it to? Yep. That's a good one, Manoj. Yep. Okay, guys. So again, really glad we converged on an answer. I feel like we're ready to move on here. So we've talked about the calculation side, and I always been telling you guys, oh, and then it fires, right? And then something else goes on. So this here illustrates that part of it, right? Kind of like the output part of it. And this is how you can think about it. The dial represents the calculations you're going to do. And if you land in the red zone, that's some sort of a threshold or desired outcome. So that's where your output is going to fire. Whereas if your answer sits outside of that threshold range, answer whatever, you're not going to fire, right? You might send off a 0 in that situation, or some sort of lowered weight in that situation. So that's what this chart, from the Tariq Rashid book illustrates. But the real takeaway here is that while the output is kind of like a 50-50 yes, no, or I shouldn't say it's like a binary output. It's like a yes, no, true, false type of output. The calculation itself is not necessarily equally binary, right? It's binary in that it's in the range or not, but that doesn't, in the threshold or not, but that doesn't mean that the threshold is 50-50, right? There can be a lot of nuance in those thresholds. So let's talk about this. Who recognizes this? Let me know in the chat. I know all of you are very smart and capable, so I'm sure that more than just one of you is going to recognize this. What is this? What's up on the screen? So I see people on my Instagram. Thank you so much. You're welcome to stay there. You're welcome to join us on YChat. Thank you so much for people on Twitch. I'm seeing a couple people on Twitch. I don't see anybody on Kick, but thank you so much for being here, guys. Really, really appreciate all of you. Oh my gosh, we're at an hour and a half already, guys. Crazy. Okay, so Yassine says Relu. Yassine says activation function. Okay, anybody else? You can also just choose to agree with somebody in the chat. You can just say, hey, I agree that I agree with Yassine or whatnot. Diffio says this is the step function from elementary analysis. Diffio, help me understand what you mean by elementary analysis. Help me understand what you mean by that. Or maybe you're saying that that's just your own initial take on it, right? Diffio says, sorry, math background. That's okay, but just let me know what you mean by that. Khalif says Relu, okay. Lalman says sigmoid, okay. Manoj says sigmoid, okay. Yassine is correcting himself and says yes, step, not Relu. I was wrong, okay. Diffio says no, it's a fundamental concept in real analysis. Okay, cool, thank you. Anna says perceptron. Okay, I like that, Anna. CJ says looks like a digital signal. It does, right? Like, I guess it'd be what? This would be like a DC signal, right? Not an AC. But I think you're right. I think it's a DC signal. Yeah, for those of you guys who don't know that, I went to a technical high school. So technically, I have like this high school degree in what is it? In electronics. So yeah, so we used to study stuff like this. Starry Vibe says it's a tan H. Okay. Diffio says it's like the steps and prime counting function. Okay. Okay. Anybody else? Last call for answers. Last call for answers. And I'm appreciating all the answers. We're gonna come back to the actual name though, right? Anybody else? Last call for answers. What is up on the screen right now? What do you guys think? Khalif says, yep, it's step. Okay. Denelson agrees with step function. Okay. All right. So I want you to think of all the answers that we saw, right? And I want you to take a look at this one. What do you guys think? There's this one and there's this one. So two questions. Some of you said that this one was a sigmoid. Are they right? And then for those of you that gave another answer, what is this one? And if you want to go for the extra credit, what is the difference between this one and this one? And if you want to go for extra credit, talk to me like I'm a 10-year-old managing director. What do you guys think? So Khalif is answering sigmoid for the second one. Yeah, and obviously the answer is there, right? So again, two questions. For the people that said sigmoid at the beginning, what do you think about this one now? Because some of you answered, some of you answered sigmoid for this one. And I'm not naming names, right? But what do you think about this one after seeing this one? And then for the second question is what is the difference between these two? So Diffio says both examples of nonlinear activation functions not the same. Diffio, I agree with you that they're not the same, but is it a nonlinear activation function? What do you guys think? Yassine says it has two conditions. If output is less than a threshold, then output is 0. If not, it's 1. The second one outputs a prediction between 0 and 1. Yeah. Yeah, if you look at the sigmoid function and you look at the formula over here, right, which is a pretty common sigmoid formula, I think a good number of you in the chat have seen this formula before, right? You're going to get an answer between 0 and 1. It's a range-bound answer, right? Anna says it's discrete versus continuous. Yeah. Yep. Ty says the first one is a hard sigmoid. Yeah, sure. You could think of it that way. Oh wow, LR, is it LR or LARB? LARB over on Kick. Welcome, you're our first participant on Kick today. So glad to see people participating on Kick. Denelson says the difference is that the first image has a function that after a threshold, it is immediately classified as 0 if not 1. The second one has a probability prediction between 1 and 0. Yeah, okay. I'm on board with that, Denelson. So Denelson and Yassine, you guys are definitely on the right track with an answer. So if you guys want to think ahead, why do we need this? Why do we need to have a sigmoid function? Why can't everything be a step function? Right? You're telling me the differences, but why? Like, give me the practical side of it. Excuse me. Anna says the step function forces values to 0 or 1. A sigmoid will give values between 0 and 1. Okay, yeah, but why? Why would you need this? Lawman says, agree with Denelson, agree with Yassine. Cool. Yeah, if you guys just want to participate in a small way, you can just say who you agree with. That's totally cool. Thanks, guys. Wael says, I think the difference is the transition is smooth transition and it is more natural than a sharp one. Yeah, but why? Why? Diffio says you can create the step function using a Fourier series, but you need an infinite number of them. Okay, cool. Yassine says for like a 10 years old answer, the first one gives straight answers. The second one gives how sure we are of our decisions or how much we learn towards an answer. The second gives how sure we are of our decisions. Okay. Yassine, there couldn't, some people would argue that there's a name for that. Just go one step further, Yassine. You're so close. Give me one step further. Osama says a step function, it gives you a discrete output. Yeah, right. We're gonna come back to that, but yes, Yassine, you're on the right track there. Denelson says, amazing answer, Yassine. I agree. Yeah, so Denelson, so think about that too, though, right? How sure we are of our decisions. Yassine said that in his answer, right? There's a name for that. There's a name for that, guys. Sigmoid function output is continuous. Yep, you're right about that, Osama. It is a continuous output, range bound between 0 and 1. You can kind of see that in the formula, right? The formula itself would tell you that it's a range bound answer, right? LR says, are you streaming on other platforms at the same time? Yes, I am. I'm streaming on, I don't know, 5-6 platforms, whatever it is. Yeah, I'm using 5-6 platforms. I'm on 2 phones right now, but just trying to spread good content here. But thanks for joining us, Elarb. Diffio says they both give valid probabilities. Starry Vibe says probabilities, and that's exactly right. That's exactly right. How sure we are of an answer, just tell your managing director, it gives you your probability, right? So I'll tell you something that I'm working on with a current client right now. And this is an interview question that I have given and I have received in the past. What is the difference between regression and logistic regression? What is the difference between regression and logistic regression? Think about that and put your answer in the chat. I guarantee you I assure you that I've asked this in interviews, and you will probably have this in an interview. What is the difference between regression and logistic regression? CJ says the gradient is more gradual in the sigmoid function. Yep. And let's talk about that because we never really concluded on this one here. So to CJ's point, to CJ's answer, this is referred to as a step function. And there is very little nuance in this one, right? You're either at the threshold or you're not, right? It's like a very binary answer. You're either at and past the threshold or you are not. That's it, right? If you are past the threshold, you're up here at this value. If you're not, you're down here at this value. True, false, yes, no, 1, 0, right? That's all there is. Whereas the sigmoid function does allow for that nuance as you have different inputs, right? Because our x-axis is our input. So as you have a scale of inputs, not a threshold, not a set threshold, you can have a different set of values for your outputs. And then we know that we are range bound between 0 and 1 as all probabilities basically are, right? Yeah, Lallman, I love your answer. The first one gives straightforward 1 or 0. Second one gives a probability that it is 1 or 0. Yeah. Lallman, excellent answer. That's a great answer. That's a great answer. Diffio says, regression predicts continuous values. Logistic regression chooses categories. Take it one step further, though. Take it one step further. Yassine says, regression's range of output is not limited. Logistic regression only outputs probability scores between 0 and 1. Okay, Yassine, you have all the answers. You have all the elements of the answer. Yeah, let me come back to that, Yassine. So Denelson says regression can have values that span from infinity to infinity, and logistic regression is a binary decision model. Ooh. Oh, Denelson, you had me at span, you lost me at binary. So close, my friend. Logistic regression is a log of linear regression equation in a mathematical context. But Sravan, don't we also use the sigmoid function in logistic regression? I mean, there's a reason why I'm asking this at this point, right? Give me a 1 if we use sigmoid in logistic regression, or give me a 0 if we don't. What do you guys think? Don't we use sigmoid in logistic regression? Haven't you guys seen this formula for logistic regression? Yeah, see, I'm seeing a couple ones, right? Manoj says logistic regression predicts categorical outcomes, often binary. Yes, no regression predicts continuous. Yeah, Manoj, everybody read Manoj's answer. That's exactly right. And Yassine, you were so close there, right? You're outputting a probability, right? That's what you're doing. You're outputting a probability. And that's the difference. When somebody asks you that question, it's a valid answer to say that regression would give you a continuous output, whereas a logistic output you would want for something that's more probability based between categories or between like a true, false, yes, no, binary type of decision, right? But that is one of the answers, to say that logistic regression gives you a probable answer, whereas regression gives you a continuous answer, right? Linear regression predicts a continuous variable, and logistic. I can't talk all of a sudden. Logistic regression predicts a probability. Yeah, that's exactly right, Starry Vibes. Yeah, you and Manoj came upon the same answer. Remember, guys, there's a reason why I'm asking this, and that's because you also use this. You use the sigmoid function in logistic regression. In logistic regression, right? If that's news to you, then maybe, it'd be a good time to review some of your regression studies. But this is the same type of output that you would chart for most of your logistic regression problems out there, right? Because the world isn't binary. You're going to have times when you need a little bit of a different answer, right? A probable answer, right? Wael says sigmoid gives you a chance for a gray area not to be green-red, we need that to compare the model for human decision. Sigmoid gives you a chance for a gray area not to be green-red. We need that to compare the model for human decision. Yeah, I'm on board with that. I think I would say that we needed to compare the probabilities for human decisions. But you're on the right track, Well. Khalif says regression target value is continuous, while logistic is a categorical value. Yeah, I'm on board with that. I would just add that the number tells you the probability for the category, right? And by the way, this is important, guys, because a lot of the answers that you're going to get from neural networks are based in probabilities. One of the ways that you can get your outputs is you can say, let me go back to that screen. Give me just a second here, guys. So if you remember, we have an example here where we have two outputs, but we could have hundreds of outputs, literally, right? And one of the ways you could possibly get answers back is it'll just tell you the probability that the answer belongs in one of these classes. It'll say, to output 1, I'm assigning 0.25. And to output 2, I'm assigning 0.75. Right? So it's not that it'll give you the exact categorical answer. It's that it'll give you the most probable categorical answer. And that's another way you can also kind of measure your progress. Are you getting good answers, good probabilities, or not? Because let's take this one step further, guys. And this is an exercise I go through with some of my junior analysts, like my first year data scientists. Let's say I give you this problem with two outputs, and you've designed a model, you've done your own modeling, and you've gone away and you worked on your neural network and all this stuff. And you come back and you tell me that for some of your answers, you're getting output 1 of 0.52 and output 2 of 0.48. Is that a good neural network? No, whether you think it is or not, give me a rationale. You're one of my first year junior analysts. You've gone off. You come back to me with your results, and you tell me that in some cases, your output is going to tell you that it's this class, 0.52, and it's going to be this class, the second class, 0.48. Is that a good network? Is that a good model? What do you guys think? This is a real world problem I'm giving you guys, because this is how I train some of my first year analysts. What do you guys think? Is that a good model? So Diffio says, well, to a previous answer, Diffio says yes, but at the end of it, it gets quantized. A choice has to be made. Yes, absolutely, Diffio. And that's kind of where I'm going with this question. How do you make those choices, right? Sravan says, Dennis, in a sigmoid function, can x be a linear equation? Can x be an equation? Yes, x can represent the result of an equation. Yes, Sravan, it can. And if you read the Tariq Rashid book, it's in there where he shows that. But yes, yeah, because the sigmoid function itself only has one input, right? It has this negative x as the only input. Because if you guys don't recognize the lowercase e, that stands for Euler's number, right? So that's a fixed number. The formula itself is fixed. So yes, your x is usually derived from another formula. So yes, Ravon, great question. Yassine, it was quick with the answer. And I think some of you are still thinking about this question because it is a little bit of a harder question. But yeah, Yassine is exactly right. If you come back to me and you tell me that this is your problem, you have two outputs, you can have any number of layers or nodes, whatever, right? And you tell me that this is 0.52 and this is 0.48, you're flipping coins. You're flipping coins, right? So to me, that's a weak model. That's a bad model. Because you could probably get those results just randomly, right? There's only two classes, right? So assuming balanced data and all that, right? I would tell you that that model stinks. I as a manager would not sign off on that model, right? Because you're no better than a coin flip. You're no better than random choice. So that's why that sigmoid function and understanding the results of those probabilities is important, because it kind of helps you say, okay, well, wait a minute. Like, if I only have two output classes, I better be a lot higher than 0.50, right? That's kind of like your baseline in a way, right? Now, what happens if you come back to me and you say, for your outputs, you're consistently getting 0.20 up here and 0.80 down here? How would I, as your manager, feel about that model? Well, now I'm feeling much better, right? Because now you're consistently being able to say, hey, I can distinguish the two classes because I'm showing you much higher probabilities, right? So that speaks to the strength of the model. So coming back here to the sigmoid function, when you're 50-50, you're basically here in the middle of the curve, where you're basically saying, it could be this side, it could be that side. Well, but you only have two classes, right? So you're not really strong to say, yep, you're approaching, you're approaching a high value or you're approaching zero. But if you come back to me and say, well, I'm at 0.8 and 0.2, okay, well, now you're much higher on the curve, right? Now you're much higher, or you're much closer to approaching a significant output, right? So this is why sigmoid functions are kind of important in neural networks and kind of important to understand, because so much of it is based in probabilities. Yes, there are neural networks that you'll need to decide to solve this. But if you're looking at something like this, it's probably also solvable by other models, right? Like, step functions are still valuable, don't get me wrong. But you can also get some of this via any other number of methods, right? All right, so I'm glad we went through that, because I could tell by the answers that some of you are still processing through sigmoid and kind of like the significance of it all, because it can be very significant, right? All right. So here, what I want to illustrate is that you can also have multiple inputs. We've been talking about inputs from a fairly like kind of like a generic way, but you should realize that you can have multiple inputs. And remember that some of these inputs can actually, well, usually they represent another node, right? So when you see input A, B, and C, you can pretend that there's another node layer here that happens to have 3 nodes. Because remember, as we established last week, all nodes are interconnected, right? So all nodes connect to subsequent nodes in the layers, in the network. So here, you could assume that there's a layer with 3 nodes. What happens if that layer had 50 nodes? Well, that means that we would have to modify this graph to show 50 inputs. Because remember, all layers are connected to other layers. All nodes are connected to other nodes. So now you're taking in those inputs and you're saying, well, are we doing like, some x equals, which is basically like a threshold, right? Or excuse me, I should say like a step function. Or are we going to do something else more nuanced and do it via sigmoid? But again, the greater point here is that you're taking all of those inputs, tying it into one function, whatever that activation function may be, and then going on and doing something else with it. Okay? Everybody with me on that? So, in passing, I've mentioned weights. But now we're going to be talking about weights. Now we're going to be talking about the inputs and the weights. Because the weights is kind of like where the magic is at, right? Because the weight is what actually makes the adjustments, is the adjustments that your neural network is making. Right? So if you remember when we talked about regression in other times, we've always talked about y equals mx plus b, right? X being your input, and then m being the weight. Like what modification are you making to that input to give it some to generate some sort of output value, right? And that's what this is illustrating here. That we can't just say, oh yeah, there's the inputs and we put in the nodes. Well, no, we also put in weights. And the weights, like I said, is kind of like the secret sauce that the neural networks add. That's the dial that neural networks get to adjust and say, oh, that formula didn't go so well. Let me adjust the weight here. Let me adjust the weight over there. Right? Kind of knock the answer back and forth into place, right? So it's not just inputs going into the nodes. It's inputs and weights going into the node, and then that is calculated or taken into account during the formula, whatever the formula may be. And as Sravan asked earlier, this X represents a combination of those weights, of those multiple outputs and weights. So even though your sigmoid threshold might only have one input, which is the X, right? Which we've already verified on this formula here. There's really just one input. Sigmoid is a fairly straightforward formula. That X itself can be made up of any number of inputs and their respective weights, right? Diffio says, in this context, X is sometimes called a logit. I love that name, easier to say than logons. Okay, yeah, sure. Yeah, guys, call it whatever you want. I'm just trying to give you guys the meta view into why we need all of these things, right? But that's fairly straightforward, right? Where it's the understanding of it's not just inputs, it's inputs and weights. All right? So let me look ahead here. Yeah, okay. So this is the last slide for today. I can't believe we've gone almost 2 hours already. So as you can imagine, so far we've only talked about individual nodes, but I told you that there's different layers and different nodes within those layers. So this is a very quick representation of what a network starts to look like, right? Where you have all these connections between the layers and with the nodes themselves. And they all have their own weights associated with each one of those inputs. And you can see here, like if we focus here on node 3, at the bottom of layer 1, node 3 is connected to the next layer to 1, 2, 3. Node 2 is also connected to 1, 2, 3. Node 1 is connected to 1, 2, 3, and so on. I don't know if it's coming across on the stream, but just so you guys know, there is a gray line. So there's a green line, a red line, and a gray line. I don't know why he chose gray. It's a terrible choice for this chart, but you can see that there's interconnection. So there's a lot of calculations happening at one time, right? And this is what we talked about, where neural networks are kind of a math hog, right? They're a resource hog because they do so much math at one time, right? We've focused on these, these example neural network structures, but there's neural networks out there that literally have like dozens and dozens of layers, hundreds of nodes per layer. So you can quickly get to these networks that are doing a lot of intense processing. Excuse me. Excuse me, my throat got dry. So this is where matrix multiplication comes into the equation, right? Because I know a couple of you mentioned matrix multiplication. And it would be impossible to handle all of this without matrix multiplication. You kind of need that, right? To be able to handle all the different math that's happening, all the different sizing. Excuse me. Because remember, layers don't have to be equally sized. So you could have some layers that have 10 nodes, and then the next one has 8 nodes, and so on and so on. So really, it's impossible to handle all of these calculations without some matrix multiplication along the way, right? It would also be equally impossible for me to teach you this in a single class, right? I mean, that would be foolish of me to even attempt that, right? So I'm going to encourage you to seek out some of your own resources to understand the inner workings of matrix multiplication. Now, having said that, there is one more thing I want to cover before we wrap up. We haven't talked about frameworks. We haven't talked about the practical side of how these are actually done in the real world. And the answer is that the construction of the neural networks, the layers, the functions, the math of that is essentially what the frameworks out there do for you. So Keras, PyTorch, all of those items, that is what decides whether, or excuse me, that is what handles all that heavy lifting for you. You will not be expected to do your own matrix multiplication. You won't have to rewrite the sigmoid function or things along those lines, because that will be handled for you in the frameworks. That's kind of like the convenience that those frameworks add, okay? So this is where I want to pick up for the next class. I can't believe this took 2 hours. This is crazy. Because what I want to do is next week, we're going to do a little bit of review, and then I want to do some coding of neural networks without any frameworks. And then we're going to bring in some frameworks to help us understand how much more convenient it is with modern frameworks. Okay? So I know we covered a lot. I'm going to once again encourage you to get the Tariq Rashid book, because it's a very good book, and I'm very inspired by it. I'm adding my own work to this, but his book is very good. Next week, we're going to do a quick review, and then we're going to get right into coding. We're going to be using AI to help us code some of these collections, okay? And then we're also going to talk about the frameworks that are used in modern data science, okay? So what I'm going to need from you is you can do it today in the chat if you want, or we can do it later on, during the week. But I need you to tell me if you grew up with a father figure in the home, because if you didn't, we're going to send you to PyTorch class. But if you're a normal, well-adjusted human being, we're going to be using Keras for our neural network instructions. Okay. Oh man, as you guys know, I prefer Keras, right? PyTorch is for people who just don't know any better. Um, but we're gonna pick up on that next week, because if you feel intimidated or you feel like this is something you don't want to do, don't worry about it. A lot of the modern frameworks handle a lot of this work for you, okay? Okay, there's the chat. I wanted to make sure you guys are still listening. Diffio says lol, Manoj says lol. So, I respect that PyTorch exists. It's just for people whose father one day said that they were going out for cigarettes and they never came back. That's how you end up as a PyTorch developer, right? Let's be honest. All right, guys. I can't believe that went for 2 hours, guys. You guys are crazy. You guys are making me stream for 2 hours. Oh. Diffio says, nice content, well done. Thank you. I appreciate that. I appreciate that, my friend. And Diffio, thanks for joining over on Twitch. I love seeing people on all the different platforms. So guys, we definitely covered a lot of stuff today. Don't feel intimidated. Neural networks is definitely achievable. It's definitely possible to learn. I'm giving you guys the fundamentals because I think these are really important to understand. And, this is how we build up our skills brick by brick, right? Yassine says, was missing the bullying. The bullying? Bullying? Yassine, I'm giving you, gems. These are gems. You should be writing that down. You should have it in your notebook. PyTorch is for people that don't love themselves. You should be writing that down, okay? This is not bullying. This is quality instruction, Yassine. Denelson says, always love the content. Thank you, Denelson. Always love having you around. Moo says, many thanks. Really appreciate it. Yours Ramfully. What a great name. Yours Ramfully. That's a great name. Hello, sir. This is Arjun from India. Arjun, welcome. Welcome. You're joining us a little bit late, or maybe you were just listening. That's okay. But thank you. Thank you for being here. I think somebody just retracted their message. CJ, was that you? Somebody just retracted their message. Diffio says, doing my master's thesis in AI right now. Always good to go back to basics. Yeah, cool. Thank you, Diffio. I appreciate you pitching in, and keep on coming back. So for those of you who don't know, maybe it's your first time like Diffio. This series I stream on Sundays. Same time that you joined today, it's 1500 GMT or 8 a.m. Pacific, 11 a.m. Eastern if you're in the US, but it's 1500 GMT for those of you worldwide. And I might get back to streaming daily. I might have another idea for some daily streaming I might want to do. So who knows? Maybe we'll do maybe at some point we'll get back to some daily streaming. Who knows? But yeah, guys, keep on coming back every Sunday. We'll just continue this series. I think we have at least 2 to 3 more weeks in this series, maybe more. And then I want to do a series on robotics. I think Starry Vibes had requested a series on robotics. So definitely willing to do that. I have an idea for that. If anyone else of you, what a terrible sentence. If any of you would want to suggest another series topic, let me know. I'm open to the suggestions. So let me know. Diffio says robotics. I'm down. Yeah. I think it'll be fun to do something on robotics. I got a small idea to do. Manoj says thanks. Love the content. Thank you, Manoj. Appreciate your support. Again, if you guys see that icon next to Manoj, that means he's a paying member of the channel. Really appreciate support. If that's something you want to consider, really appreciate that. Lawman says, thanks, Dennis. You're awesome. Thank you so much. Appreciate you saying that. Hope you're well out there I think you're in Nepal. So I hope you're doing well out there. Ty says, thank you, Dennis. No, thank you, Ty. Really appreciate your support. Yours Ramfully says, I'm planning to do a master's in AI. What's your idea about this, sir? Yeah, there's nothing wrong with that. I would never want to discourage someone from advancing their education. Just make sure that you keep a real world perspective on it. Okay? As I've shared with you guys before, I sit down to dinner with some of my friends, and all of my friends are directors and managing directors, at some large companies. And they always tell me that. They always tell me, Dennis, I'm getting these masters in data science who don't know anything. I hire them at that level, and I want to rehire them as summer analysts because they don't know anything. They don't know anything practical that he needs on day one. So make sure you keep a practical view on what you're learning, okay? Super critical. I hear that a lot as criticism. Or yours Rantfully, I think you're a little late, but somebody else expressed that in the chat, right? That they're a data scientist, but they don't feel like they know anything. I've heard that. I have clients that tell me that, right? So yeah, I mean, just keep in a real world view on all your work, okay? Otherwise, you're going to graduate and you're going to be basically worthless, right? Starry Vibes says, big thanks, sir. You're seriously awesome. Oh, thank you so much, Starry Vibes. I appreciate that. You're awesome too. Really appreciate your continued support. Keep on coming back. Ty says NLP. Yeah, a series on NLP might be interesting. Yeah, Ty, we can talk about that. That could be interesting. Diffio says, thank you. Have a great day. Yeah, thank you too, Diffio. Nice seeing you. And again, welcome for your first time. Okay, so CJ says, are you familiar with this book? And if you are, what are your thoughts? Hands-on machine learning with scikit-learn, Keras, and TensorFlow. Concepts, tools, and techniques to build intelligent systems. I can't say I am. I can't say I am. Sounds like a good set of tools. But you know what, guys? I know that not everybody has access to these books, or maybe, your budget is a little tight. Honestly, one of the ways that I learned a lot about neural networks or the frameworks is by going to the Keras documentation. And I mentioned that, CJ, because this book is obviously kind of focused on Keras and TensorFlow, which is great, right? That's the tool set that I also use. And like I said, guys, for full disclosure, I'm also one of the, I'm a moderator on the Keras mailing list. So, I want to disclose that so you guys, don't think I'm biased, but I am biased. I like Keras. But the Keras documentation is actually pretty good. And like Keras has built-in pre-processing tools. They have built-in tools for a lot of things in neural networks. So, the book sounds great. I can't tell you to not buy it. It seems reasonable. But for those of you who don't have access to books, don't have the money for them, go look at the Keras documentation. Go look in their help section. It's actually pretty good. It helped me, so maybe it'll help you too. Yours Rantfully says, thank you so much, sir. Will improve my... Excuse me, guys. Sorry. Will improve my practical skills. You're awesome. Thank you. I appreciate that. Yours Rantfully, I think it's your first time, so please subscribe to the channel, like the live stream, all that stuff. Keep on coming back. I'm going to keep on teaching as long as you guys show up, so... Thank you, Dennis. Always appreciate your content. Ashu from India here. Welcome, Ashu. I think it's your first time here, so welcome. Glad you're joining us. Anna says, I like your jokes. You should do more of those in the session. Oh, Anna, now I am 100% sure it is your first time here, because the regulars on the stream, if you want chat, go ahead and start typing out my rants, because Anna, the regulars in the chat know that I have a long list of people that I go after on this chat, right? So I know people like Starry Vibes, Yassine, Manoj, they already know. So they can tell you in the chat all of my rants, because I have plenty of rants. So don't you worry, Anna. But I have to find a balance between that versus teaching you guys good stuff. Because like I said, ultimately, I want to put good stuff out into the universe, good data science stuff, right? I told you guys how much I truly believe that data science is like a learned profession. It's up to me, like, the older people in the profession to help other people, help the younger people, right? So this is me, reaching my hand back to help you guys. So I want to put out good information, right? Yeah, Osama also knows my long list of rants. So if you guys want, put them in the chat. I'm not embarrassed. I call people out all the time. I'll tell you what they are. Yeah, but Anna, this is definitely your first time, because I have plenty of things I go after. CJ says, thank you. The stream is awesome. CJ, I think it's your first time here. CJ, I think we might follow each other on TikTok. If it's the same CJ I'm thinking about, Maybe I'm wrong. But let me know, CJ. Yours Rantfully says, already subscribed, sir. You'll be seeing me here often. Cool. Thank you so much. Yeah, turn on those notifications and all that. But like I said, Sundays, 1500 GMT is when I stream. So whatever time this is for you, 2 hours ago in your part of the world, just keep on coming back at that time, and that's when you'll find me. For me, it's 8 a.m. on Pacific time in the US or 11 a.m. Eastern. But 1500 GMT for those of you that are all over the world. I'm so so grateful to have so many followers from around the world. So that's why I always publish the 1500 GMT time, so you can find it, vis-a-vis your own region or your own time zone in the world. So yeah, as I always say, because of okay, Rob's asking. I'll take Rob's question as one of my last questions here. So Rob's over on Twitch. Thank you. I think it's your first time. Thank you so much for being here. What do you think about those concepts in time learning, vibe coding, no low code? Don't you think it'll be an excuse for skipping learning fundamentals? For some people it will, but that won't make you a good data scientist, right? Look, guys, the future is going to be no different than now. There's going to be good people who do good job. There's going to be people who do a bad job, right? Even if you gave everybody AI tools or the vibe coding tools, there's still going to be people who are great at it. There's going to be people who suck at it. That's not going to change, right? That's just the normal distribution of talent, right? You take a group of people and they'll normally distribute. You're going to have your outstanding performers, you're going to have your terrible performers, and you're going to have a lot of people in the middle, right? The fundamentals, it's what's going to distinguish that. Whether you actually understand what you're doing, what you're going after. Can you understand when things go wrong? Can you understand how to fix your nodes, how to fix your network? Can you explain it properly? Can you talk like a human to the people that pay your bills? Right? This is why I go through some of these examples and some of these exercises. Because who cares if you're a math nerd? Anybody can do that. But can you walk into a room of managing directors and have them understand you? That's the skill, right? So same thing with like vibe coding. Okay, great. Yeah, you're good at prompting, but if nobody listens to your presentations because you suck at that, then who cares, right? So yes, all of us are going to be heavily aided in the future by AI. I've been saying that for like the greater part of the last year, but you still have to be good at it. You still have to be a human about it. You still have to be able to express yourself. You still need to have soft skills so that people will want to work with you, right? So yes, AI is going to have an impact on what we do. We're going to be heavily aided by it. We're going to be expected to do more with it. We're going to be expected to do more projects. But keep on studying. Keep on trying to develop your soft skills. Keep on coming back and listening to good guys like me, and you're going to get there, right? So I think there's still reasons to be optimistic. Okay. Wrong, CJ. I was here for last week's stream. I just have different accounts for my phone. Okay, thank you, CJ. I appreciate that. I'm pretty good at keeping my memory with my different followers, but sometimes, I make mistakes. But like I said, so fortunate to be able to have followers all over the world. But that also makes me worry about all of you because we live in such a dynamic world, such a changing world. So please take care of yourselves. Take care of your families. Thank you so much, and I'll see you next time. Good morning. Happy Sunday. So glad. Okay, you know what? Let's start all over again. Let's start by having my microphone in front of me. You would think that after all this time, I would be just completely ready to go, a fully polished professional, and I still forget some of the basics, especially around getting everything ready. I have to spend so much time getting everything ready for the stream, all the software, all the different components I need, the the screens, my lights, my camera. You would think that it'd be a lot easier to stream, but it's not. This is hard work, guys. So I'm sorry that I forgot the microphone there. That's my mistake. But as I was saying, happy Sunday. I hope that you're well. I hope you're doing good in your part of the world. Let me know how you're doing. And for those of you that haven't joined us before, Sundays is when we usually do our tutorial series. Right now, we are in the middle of a neural network tutorial series, which we are on week 3. I think we're going to have at least 2 more sessions, maybe. We'll see. But, we took a little bit of a diversion last week. We had a different session last week, but now we're back to learning neural networks. I love doing these Sunday tutorials with you guys. They tend to be my most popular live streams. They tend to be a little bit longer. And today we're going to start looking at some of the code behind neural networks. We haven't looked at code yet, and that's really my fault. But now we're going to start looking at code and seeing where that leads us in terms of neural networks. So I hope you guys are ready. I'm certainly excited. I'm going to try 1, maybe 2 different things today. So we'll see how some of those go. But let me know how you're doing in the chat. Let me know that you're here and you're ready to go, ready to learn about neural networks. I'll see the chats up here, over here, up on the screen, and I'm pushing out my stream on multiple platforms, so we'll all get to see each other's chats. So let me know how you're doing. Let me know how you're feeling about neural networks. Are you feeling a little bit more confident? Are you feeling a little less confident? And we'll see where the lesson takes us. Today, I want us to do some code. We're going to be working under the same premise that I've always said before, that the data scientists of the future will be heavily aided by AI. So we are not going to write a lot of code ourselves. We're basically going to use our prompting skills to help us create code that we need. The prompts for today might be a little bit different than usual because the prompts will also maybe include a couple of educational type of questions, little questions that we might have or that we might pose to ChatGPT to help us with our understanding of neural networks, right? I mean, we can use ChatGPT as a way to help us with neural networks, right? So let me know how you're doing in the chat. Let me start seeing some people in the chat before we really get started, because I am going to be doing some audience participation right from the beginning. So let me know how you're doing. Let me know how, oh, shoot. I haven't gone live on YouTube. No wonder I wasn't getting my YouTube people. Oh my gosh. My gosh, guys, that is 2 big errors that I've done on my stream already. Ugh. My YouTube people, I'm so sorry that I didn't start on time. I see my Instagram people. My Instagram people heard me. But my YouTube people, I'm so sorry I didn't actually press the button to start the stream. I'm telling you guys, sometimes I'm just not feeling like a professional over here. Oh my. Okay. Let's reset. Hello, it's Sunday. Welcome to our tutorial series. We're continuing neural networks. So my YouTube people, I'm so sorry that I screwed up. I didn't press the live button. Where is my mind today? Let's go ahead and get YouTube people in the chat. I know you're there, so go ahead and just start filling up my chat. Say hello. Let me know how you're doing. Guys, I really need the chat today because I'm going to be doing some audience participation right from the beginning. So let me know how you guys are doing, okay? There we go. There's our chat. Landry says, dare we say you're getting old, LOL. Hello from Belgium. Well, hello to you too, my friend. So good to see you, Landry. I know you're a student now there in Belgium, so I hope you're doing well. Am I getting old? Yeah, maybe. I mean, my birthday was last month. I am now 48 years old. So yeah, maybe I'm getting a little old. Maybe I should retire. Just forget all this stuff, you know? Just go out and buy a sailboat and sail around the world. Have you seen that guy on TikTok? He hated his job. I think he was in Oregon or something like that. Hated his job. So a year ago, he bought a sailboat, taught himself how to sail, and now he's providing updates as he sails around the world by himself and his cat. You guys believe that? Have you guys heard this one? He's on TikTok. He's a good follow on TikTok. So maybe that's what I need to do. Landry, is that what you're suggesting? Maybe I need to just, pack it up and just retire and just, I'm too old for this. Is that the suggestion here? Landry says, lol, no, don't retire. I gotta tell you guys, sometimes I feel retired just because I enjoy this stuff so much, It's not work if you enjoy it, right? So sometimes I do feel like semi-retired, and maybe sometimes I'll think about like maybe getting like a motorhome or an RV or something, and maybe just drive across the country while still, keeping this job and still doing this. So we'll see. Manoj, our good friend Manoj says, greetings from Manoj. Hesaragata, Bangalore, India. Happy Sunday. Happy Sunday to you too, Manoj. Glad you're here, Manoj. Over on Instagram. Okay, cool. My Instagram chats are working today. Naved, I think you've been here before. Welcome back. Says, we love you, sir. Thanks. I appreciate that. I love getting messages from you guys that tell me that you guys got jobs, because of my content or whatever. So I definitely feel the love. So thank you so much for that, Naved. Thank you. Anybody else wants to say hello before we get started? We're going to go into some audience participation right from the beginning. Excuse me, guys. My eyes are itchy. It's really bad allergy season out here where I live. It's a rainy day today, so I think that kind of shakes up the pollen or the trees or whatever. But my eyes are just, suffering from the allergies today. But I've got a big week coming up, guys. Big week coming up. I got to get a haircut today. I got to go do some shopping today. And then this week, I'm going to go to Los Angeles for 2 days. I'm going to be out there in LA doing a couple things. I'm going to take my dog with me. So big week coming up. Elijah, nice to see you. Thank you for introducing yourself. Elijah says, greetings, sir. It's my first time here. Nice. Welcome in. Even after all this time, it's nice to get newcomers. Glad you're here, my friend. So Elijah, if you want to tell us a little bit about where you're from or your experience, whatever you want to tell us, feel free to share. But thanks for being here, Elijah. Khalif says, hello, sir. Good day, everyone. Good day to you too, Khalif. Hope you're doing well. Hope everything is good in your part of the world. Yassine, our good friend Yassine, longtime supporter, says, hello, sir. Yassine from Tangier, Morocco. So Yassine, when you say you're still in Tangier, I assume that you're still in school, right? Because I know you don't I know that you don't permanently live in Tangier. So glad to see you. Hope you're doing well. Let us know when your school ends, Yassine. I assume it's coming up soon. But guys, thanks so much for being here. You know what? Let's go ahead and get started. We have more than enough people. We're going to have some audience participation right from the beginning, guys. So hey, Osama. How are you, Osama? Nice to see you. Hope you're doing well out there in Morocco. All right, let me bring up my classroom view and I'll show you what I have in mind for today. All right, guys. So this is week 3. Well, it's actually lesson 3, right? We took a little diversion last week, but we are in week 3 of learning neural networks. So I think that you guys know that we've spent a lot of time doing the foundational work to understand what neural networks are. And I think we've done a pretty good job of that. What we haven't done is we haven't done a lot of coding. So we're going to try to focus on that today. And then I'm going to use that code to help us prepare for future lessons for next week's lesson, where we're going to get into a little bit more of the advanced portions of of neural networks, or kind of like the finer points of neural networks. Okay, so my intent is that we're going to do a lightning round review. Lots of participation, so get ready to type in the chat. And after that, we're going to go into code creation. Okay, Ratnajit, I think that's how I pronounce it. Let me know if I'm incorrect. Hello, Dennis. Hello, nice to see you. Welcome. Hope you're having a good Sunday. Elijah says, I'm from Zimbabwe studying medical analytics and informatics in uni. Nice. So I'm sure it has different names, but here in the US, we would call that the bioinformatics field. Huge field, guys. Lots of opportunities in bioinformatics. So I actually have a couple of clients that work in that field. Very interesting type of work, and it's a lot more diverse than you think it is, right? Most people think, oh, it just means working with patient records, but there's a lot of data in that world, a lot of data. So yeah, Elijah, thanks for being here. I'm glad it's your first time. Thanks for stepping up and introducing yourself. Always cool to see new people coming in. All right, guys, so before we do the lightning round, I just want to remind you, I'm a big fan of this book, Make Your Own Neural Network by Tariq Rashid. Please go out and get this book. It really changed my perspective on neural networks, really helped move me forward. I pull a lot of information from this book, but I'm trying to be intellectually honest and tell you that I'm building upon his work. I am using some charts from the book, but I'm trying to add my own original take on it. Either way, I recommend that you go out and get this book. It'll really help you, guaranteed. Starry Vibes, our good friend Starry Vibes says, hello, sir. I hope you're doing well. Doing very well, Starry Vibes. How are you? Hope you're doing well out there with your studies and all that. So let us know how you're doing, Starry Vibes. Okay, so Tariq Rashid book, highly recommended. All right, what I want to do is I want to go straight into audience participation. So these 4 portions or 4 groups of data of the world of data science, they're out of order. In previous lessons, I presented to you the order in which I think a data science progression naturally follows. Whether you're studying, whether you're learning data science, or whether you're conducting a study, right? There's kind of a natural progression in order. I've had this slide before, but these are out of order. So from 1 through, so give me in the chat, give me your order in how these different phases of data science should be ordered. What should go first? What should go second? What should go third? What should go fourth? And you can think about it in your own learning progression, right? Maybe like what your school taught you, or where you're at in your learning. It's up to you. But go ahead and tell me in the chat. And if you're too shy, you can always just say, oh, I agree with so-and-so, or maybe just give the ones that you do know. You don't have to know all 4. But let me know. These are out of order. What is the order that they should be in? Go ahead and put your answers in the chat, okay? Starry Vibes says, good, sir. Thanks for asking. Good. Glad to hear it, Starry Vibes. Glad that you're well. Yassine is giving us an answer. Let's wait for some answers to come in. Okay, Khalif says statistics. Khalif also says agree with Yassine. Okay, Landry also says statistics, but Landry, give me an order, my friend. What's the order for all of them? Denelson says, hello, everyone. Denelson from LA. Sorry for being late, doing early morning errands. Won't be on chat. Will be participating out loud in my car. Nice. Denelson, it's early to be doing errands, but good for you. And be careful. Please drive safely. But good to see you, Denelson. Thanks for your continued support. You're always such a great supporter. Okay, so I'm seeing a couple of people agree with Yassine. Osama says statistics, machine learning, neural networks, and analytics. Manoj says statistics, analytics, machine learning, neural networks. And Yassine's answer was statistics, analytics, machine learning, neural networks. Okay. Landry is saying statistics, analytics, machine learning, neural networks. Ratnajit is suggesting analytics, statistics, machine learning, and neural networks. And Sujay, welcome. Nice to see you in the chat. Says statistics, analytics, machine learning, neural networks. Okay, so a couple of people have the same answer. Lanry, Sujay, Khalif, and Yassine all essentially have the same answer. Kuntal, welcome to the chat. I think it's your first time. Welcome. Kuntal is suggesting analytics, statistics, machine learning, neural. Okay, so they also have the same answer. Elijah is also saying statistics, analytics, machine learning, neural networks. Okay, Kuntal says yes. Yeah, Kuntal, welcome. Always nice to have new people. We have a couple new people in the chat today. That's awesome. Awesome. Okay, so guys, we basically have two competing answers, right? Osama is saying statistics, machine learning, neural network, analytics. Yassine and a few other people are saying statistics, analytics, machine learning, neural networks. What do you guys think? Does anybody want to change their answer? Anybody want to kind of think about their answer or change it? Easy says hello. Hello, Easy. Easy, is this your first time? I think it might be. So Easy, welcome to the chat. I see you over there on YouTube. Thanks so much. Manoj says, I would like to call all context statistics core. Maybe. Landry says stats first because without it, you can't understand how the data set behaves. Yeah, okay. Well, look, why don't we adjust that, right? Because basically all answers. Let me look at Osama's answer. Yeah, but basically all answers put statistics first, right? Like everybody has basically agreed on that. Now here's the thing. Lanry is saying stats first because without it you can't understand how the data set behaves. Okay, no, I'm sorry. It was Manoj. Sorry about that. Manoj said, I would like to call all context as statistics core. Maybe. So guys, let's have a second quiz question that relates to what Manoj just says. Why do we even need modeling? Why can't we solve everything with statistics and analytics? If we can't solve everything with that means they must have some limitations, right? So I'm asking the question a different way. What is one of the limitations of analytics? Why don't we just use analytics for everything? You guys should know that. If you guys have trouble with that answer, like, you know, like what are the boundaries of analytics? You know, might want to study that a little bit more, right? But give me an answer in the chat. So, because Manoj, I'm not sure if I'm on board with that. Statistics and analytics have their limits. What do you guys think? Let me know. Okay, so I think the only difference now is, let's see, everybody put machine learning second. And then neural networks, yeah. So the only difference here is where analytics goes. Yassine and others answered that analytics is second, while Osama says it should be last. Anybody want to change their answer? Or anybody want to update their answer? Anybody want to give a new answer if you're just joining us in the chat? And the other question to the chat right now is, why can't analytics solve everything? Why don't we just use analytics for everything? Are there limitations to analytics? Let me know. What do you guys think? We got a few people on Instagram today. That's cool. If you're over on Instagram, thank you so much. Feel free to say hello. Let us know where you're watching from or whatever you'd like to participate with. But while you guys are thinking about those answers, I'm going to let you know that our original slide was actually like this. We are putting analytics after statistics. Okay, Starry Vibe says, I think data analysis helps us understand data, but it doesn't necessarily allow us to make predictions. Okay, Starry Vibes, I'm on board with that. I like where you're headed. Why doesn't it let us make predictions? Because you can make predictions. You can. Like, there's no law against it. But why? Landry, oh my gosh, Landry, you're even closer. Analytics limitations is because it's mostly what happened and why it happened. Landry, you're so close to the model answer that I'm looking for. So Landry and Starry Vibes, I want you to put your answers together. Guys, if you're in the chat, look at both Starry Vibes and Landry's answer. You guys are so close. Kuntal says, because we need prediction models which can't be solved by analytics. But you can make predictions from analytics though, right? You can. Like, there's no law against it. But is it a good idea? Are there limitations to analytics? Landry and Starry Vibes are so close. Are so close. And by the way, this is a question that I ask in interviews. I can't say I've come across other people asking it, but this is the type of questions that you're given in a technical interview where they're looking for your thought pattern, right? And they want you to get to the right answer, but it's more about how you think about things, right? So Starry Vibes and Landry, you're very close. So Yassine says statistics is only backwards looking. Yeah. Yeah, that's true. So you guys are so close, right? Because combine all of those thoughts. There's a little bit more of a scientific way to express everything that you guys have written, right? And this is part of being a good data scientist, how to sound like a professional, how to carry yourself like a professional, right? You guys are super close, super close. So what are we looking for here? Why can't we use analytics for everything? Last call for answers, and then I'll give you guys the model answer. Starry Vibe says statistics and analytics explain the past, and NN and ML predict the future. Yeah, but you're so close, Starry Vibes. But why? Why? Give me the why. All right, last call for answers. Last call for answers. Last call. Anybody else? Analytics can't be done on a complex system, says Manoj. I disagree, Manoj. Analytics can get quite complex. They can get quite complex, especially who mentioned it? Landry. Landry mentioned about what happened and why it happened. Analytics are pretty good at showing you interactions, and you can have a lot of interactions, right? Interactions aren't always one-on-one. They can be one-to-many, right? Khalif says analytics does not learn from data. I don't know. I don't know if I'd agree with that. I'd agree that there's no training data for analytics, but you can learn from data in analytics, and it learns from itself. Landry says because doesn't learn, scale, handle complex situations very well. So Landry, that's basically the same answer that Manoj just gave, and I disagree. Analytics can get very complex. Okay, guys, so here's the model answer for something like that, and it's kind of one of those things to live by. Very important, write this down. If you don't know this, you know, it's definitely a gap in your progression in data science. You should always think about analytics as being range bound. You you should not you can, but you should never make predictions from values that are outside of your range, right? So if you have like sales data and your range of sales is 1 million to 4 million, you should only try to predict sales between 1 million and 4 million. Analytics fail when you start to say, oh, we're going to predict for $6 million worth of sales, $7 million worth of sales. Why would you do that if it's not in your data, right? Like that's like the danger zone. Like that's like a no-go. So that's the main key you should remember when dealing with analytics. The moment you start dealing with data or projections or other things outside of the range, danger, right? And that's why we have modeling, right? Because analytics tells you what happened, how it happened, when it happened within a certain range. But then the modeling is where you can come out and start making predictions, because now you're training your data. You're adding weights to your data. And weights are really just kind of like educated estimates, right? Or refined estimates. So super, super important to understand that analytics are range bound. Never, ever try to use analytics to make future predictions, numbers, whatever, that are outside of the range that it knows. So earlier this week, we had a little quiz question on what is MMMR. And this is why MMMR is very important, right? Because you have to know your ranges of any data that you're dealing with. And when you're trying to go outside those ranges, that's when you should be using a robust, properly trained model. When you start using analytics to make predictions, that's where the danger starts, okay? Michael, our good friend Michael from, oh gosh, Michael, where are you from? I think you're from Nigeria, yes? I think so. Hello, Sir Dennis and everyone. I trust we've all been doing great. Yeah, Michael, thanks for being here. I think we are all doing great. Hope you're doing well. It's been a couple of weeks since I've seen you, so hope you're doing well, my friend. All right, guys, so that's the answer, right? Analytics, you got to stay within your range. Stay in your lane when it comes to analytics, okay? All right, so I think we've hit a consensus here. So this is actually the answer, right? Statistics, analytics, machine learning, and neural networks. And as I mentioned before, for me, going from machine learning to neural networks, that's where like data science like really took off for me, like in my mind and in my learning. That's where I was like, whoa, okay, like this is really cool. Like it really kind of started opening my mind to the possibilities of what you can do with data. Okay. Lightning round of review, guys. Because remember, my intent is to do a quick review and then we'll get into some coding, right? So feel free in the chat to answer any one of these 6 questions. You can answer one, you can answer all of them. Doesn't matter. Just hit the chat with your answer. What is a neural network? How many layers are in a neural network? Is there a maximum? Is there a minimum? What is an activation function? What are some of the negatives of neural networks? What are some of the metrics we use to evaluate a neural network? What's a sigmoid function? What's a step function? I also consider all of these valid interview questions. So you don't have to say, and I'm not asking anybody to out themselves. But if one of these questions is difficult for you or you're kind of lost on it, might be time to do more review before you do a data scientist interview, right? So keep that in mind. I think any of these are fair game for a data scientist interview. Really hard to be a modern data scientist without having pretty good knowledge of neural networks nowadays, right? So if any of these 6 present trouble for you, might be time to study more than to interview more. Okay, guys? Okay, so Landry's jumping right in. Guys, and you don't have to answer in order. Just pick one of these or pick all of them. Just give me your answers in the chat. Landry is telling us, to quote you, I believe, neural networks are a mathematical representation of the brain. Yep. I'd accept that answer. Yeah. We've talked about how a neural network is nodes and all the nodes are connected, just like all the nerves in your brain and in your body are connected. It's all electrical impulses. Some nerves fire, others don't. It just depends. Yeah, I think that's a pretty good answer. That's a pretty good answer. So let me know in the chat. Feel free to answer any of these. If somebody wants to say, hey, I don't know any of these, or I'm having trouble with number whatever, let me know. But I consider any of these 6 questions fair game in a data scientist interview. So feel free to go after any of the 6 that are up on the screen. One more time, what is a neural network? How many layers are in a neural network? Is there a maximum? Is there a minimum? What's an activation function? What are some of the negatives of neural networks? What are some of the metrics we use to evaluate a neural network? What's a sigmoid function? What's a step function? Okay. Starry Vibe says neural networks is a mathematical representation of how the human brain works. Yeah, great answer. I'd take that answer, sure. And just to clarify, I want to say that these are valid questions for a entry-level data scientist interview. If it was an advanced data scientist, like a lead data scientist, I'd probably ask some harder questions around neural networks. Yeah, I would. But yeah, what do you guys think? I think we've come to a consensus on answer for number 1. Anybody want to take on any of the 6? Anybody over on Instagram want to try to answer one of the 6? I really think that this is important. It's a pretty good measure of where you're at. If you can't answer these 6, might be time for more study. Anybody else want to try these? So Manoj says, activation function determines the node with a given input. Manoj, I think you meant to say determines if the node fires with the given input, right? I think that's what you meant to say. Yassine says we can have as many layers in a neural network. Yeah. Yeah, now, is there a minimum, Yassine? So you're saying there's no maximum, but is there a minimum? Hansla, I believe this is your first time. Welcome. Activation, squeeze the inputs. It depends on what you mean by squeeze, Hansla. What do you mean by squeeze? Do you mean compute? Activation computes the inputs? I'd agree with that. Is that what you meant? Let me know. There's 6 questions on here, guys. Feel free to go after any of them. Landry says neural networks can have a minimum of layers, but no strict maximum. It depends on the problem to be solved. Okay, so what's the minimum, Landry? What's the minimum? Yassine says activation function is a node responsible for controlling the decision whether to communicate with the next nodes or not. Okay. Hansla, for replying to squeezing the input, says like in the range of 0 and 1 or 1 and -1. Ooh. I don't know, Hansla. Hansla, did you take a look at question 6? What is a sigmoid function? What's a step function? I want you to think about your answer and then think about question 6, please. Okay? Okay. So Yassine says no minimum for the layers. Is he right? Does somebody want to say they agree with Yassine or disagree? Landry says 1 layer, not counting the inputs. Well, you have to count the input, Landry. The input is one of the layers, and you have to count it because you probably have done processing on your source data to get to a input layer, right? So guys, so we're still in the question, guys, is there a minimum number of layers to a neural network? Starry Vibe says neural networks are evaluated using metrics like accuracy, precision, recall, F1 score, and loss. Yeah, that's a good one. I like that. That's a good answer, Starry Vibes. I'm on board with that. Yassine says some of the negatives are vanishing, exploding gradients. Okay. Okay. Anybody else want to do about the negatives of neural networks? I think Yassine is proposing a pretty good answer there. Sujay71, welcome. I think you've been here before, but welcome back. Neural networks, in simpler terms, is teaching the system to learn stuff on its own. Well, but all models do that though, right? Any model that you train is doing stuff on its own, right? So let me know, Sujay. Yassine says weight besides the input and the output layer. I'm wrong, was considering only hidden layers, so minimum would be 2 layers. Starry Vibe says, I think the minimum is 2. Okay, guys, I'm open to being wrong, so feel free to go out and Google the answer. But I'm of the mind that the minimum number of layers is actually 3. You have to have at least one hidden layer to process your inputs, right? Because otherwise, if you're just going from an input to an output layer, that's just a pass through, right? You might as well be doing it with regression if you're modifying it at all, because there'd be no weights, right? So I think, yeah, Lanry says the minimum is 3, input, hidden, output. Lanry, I'm on board with that. So Yassine and Starry Vibes and anybody else who thought it's 2, feel free to find a source on that. I'm happy to be wrong, but it's 3. Otherwise, it's just a pass through, right? It would just be like an empty pipe, right? So I think it's 3. I think Lanry is right on this one. Okay, Ratnajit over on Instagram says one of the negatives would be the variance bias trade-off. But isn't that all models? We're always concerned with bias, right? We're always concerned with variance. That is inherent to not even modeling. It's inherent to numbers in general, right? Statistics can have variance, right? Variance can be in anything. Variance is definitely not exclusive to neural networks, right? So I don't know, Ratnajit. I'm not sure if I'm on board with that. Khalif says neural networks require computational power, which might be expensive. Absolutely. Absolutely, Khalif. That's very true. Yassine says some metrics are precision, recall, and accuracy. Nice. Very cool. I like that answer. I think Starry Vibes also gave a really good answer. Manoj says, agree with you, sir. It's 3 layers. Yeah, guys, it's 3 layers. I really think that's the case, because otherwise you wouldn't be processing the data at all, right? There'd be like no processing effort. So did we get everything? We got the neural network, layers. Okay, anybody want to try the activation function? We've gotten a couple of answers. Some of the negatives, we got some. We got the metrics. Okay, so what about number 6? What is a sigmoid function and what is a step function? So I think it was, if you look at Hansela's previous answer, there's kind of a couple clues in there. Anybody wanna give a shot about what's a sigmoid function and what's a step function? We had some charts around that in last week's or rather 2 weeks ago in the presentation. What do you guys think? What's a sigmoid function and what's a step function? That's the last one. And again, guys, if you're feeling unsteady in any of these, you know, maybe put the resume reviews on hold, and maybe, you know, start brushing up on some of these skills, okay? Yassine says, I found an answer that says it can have only the input and output, but anybody else want to try number 6? What is a sigmoid function? What is a step function? Yassine says it would be simple linear regression as you stated. Yeah, that makes sense, Yassine. If all you're going to have is an input and an output layer, you don't need a neural network for that, right? That's just like a math formula, like an algorithm that's like a math formula, which is basically like a regression model, right? So yeah, that makes sense. I mean, you can do it, but like it doesn't make sense. Like the code will run. Like I'm sure frameworks will let you do that, but like why, right? All right, anybody else? Last call for answers on number 6. What is a sigmoid function? What is a step function? So again, I want to keep on emphasizing because many of you come to me, I want an internship. Can you help me get a job? I'm looking for something for the summer. I'm getting a lot of inquiries right now of you guys looking for summer internships. But if any of these are giving you trouble, you might not be ready for a summer internship, okay? The Yassine says the step function is an activation that outputs one answer from the set 0 to 1. The sigmoid function outputs a probability from 0 to 1. Sujay says step function is like a switch. It's just on or off. But sigmoid is like between on and off. Yeah. Yeah, okay. Yassine and you, CJ, I'm on board with those answers. Yeah, I would accept those answers. I guess the part that I'm a little hesitant on, and this is just a different way of explaining it. I don't think you guys are wrong. But when I think of a step function, I think of a threshold, right? Because remember, if you think about it in an x and y graph perspective, a step function has like a threshold you're trying to meet, and then that takes you to whatever desired value you want. And it's not always 1, right? It can be whatever desired value you'd want, or whatever desired result you want. But the key there is where you are on the x-axis. Did you pass the threshold, right? Are you above a certain threshold? But overall, I'd accept that answer, the answers you guys gave. Landry says a step function is a simple activation function. A sigmoid function is a smooth shape math function that changes any input to 0 or 1. A sigmoid function is a smooth shape math function that changes any input to 0 or 1. Landry, you had me at smooth and shaped. You lost me at 0 or 1. I think that Yassine and Sujay put it a little bit better where it can find the answer between 0 and 1, or better said, the probability between 0 and 1, right? So that's the beauty of sigmoid, that it doesn't give you just a binary 0 or 1 answer. It gives you a probability of it being one class or another, right? So very close there, Landry, very close. All right, guys. So that was fun. If you have further thoughts on these, you want to have questions on these, feel free to add them in the chat. But what I'd like to do right now is, let me look. I'm pretty sure that's the last slide. Yep. So now what I want to do is I want to get into coding, right? We haven't done that yet. I'm sorry. That's my fault. Let's look at some code. So We're going to be using our friend ChatGPT because, again, as I've told you guys, the data scientists of the future will be heavily, heavily aided by AI. There is no need for us to sit here with visual code on a blank screen and say, oh, well, import pandas. And why? Never start from a blank screen, right? So we're going to go here. By the way, guys, we're going to start using the O3 engine. If you've attended this series and my other series before, you guys know that I'm a big fan of 4.0. 4.0 has treated us really well when it comes to code. It's really only made like a couple of mistakes that we could attribute back to the engine. Other mistakes was maybe my hardware setup or versioning things, right? But 4.0 has been good to us, right? But you know what? Let's go with O3. I haven't done a lot of coding with it, but I have done like text work with it. But let's see how it treats us with code. Okay. All right. So excuse me. Sorry. I'm going to make this bigger and then I'm going to write a excuse me. Sorry. Excuse me. I got my burps all of a sudden. And I'm going to show you how I would write the prompt, and feel free to let me know if we need to refine it, okay? Okay. So I think this is a fairly reasonable prompt to start off with, right? As I've mentioned to you guys before, if you really want to go through the Tariq Rashid book, my recommended view, what I did, what would help me in my experience was, well, first of all, you should know the Tariq Rashid book doesn't use any frameworks. He shows you the math, like the actual code on how to do it. Go through the entire book first. So in other words, he's going to show you neural networks without any frameworks. Finish the entire book. And then when you do that, start all over and figure out how to do all of his examples, all of that same code, but this time using a framework like Keras or PyTorch. Okay? That's what we're trying to kind of simulate here, because that really helped me. And I really think it's the best way to learn, because you'll also be knowing enough of the underlying items that need to happen with Python code, okay? Or with neural networks code. So let's see what O3 gives us. Okay, so it's telling us it's going to give us 2 inputs, 2 hidden neurons, I think it means nodes, and then 1 output neuron as a sigmoid. It trains on a classic XOR truth table to show it can learn a nonlinear function, shows the complete forward pass, back propagation, and weight updates in less than 60 lines of code. All right. So let me copy this over into Visual Studio so that we can see things a little bit better. And we'll just call this NN1. I think that should be big enough on the screen. Let me know. Okay. Um, does anybody recognize that? Anybody recognize that that function right there? What is that? If you also want to look at the structure of that piece of code, what else can you tell me about that piece of code? Or rather the results about that. So we're looking at line 6, guys. So Sajad, welcome. I think it's your first time. Welcome. Sajad says that's activation. Fabricio says, yes, that's the function that's listed there to transform a probability between 0 and 1. Well, to transform a number to a probability between 0 and 1, I think is what you meant to write. But Fabricio, welcome. I can't remember if it's your first time or not, Fabricio. Let us know, but glad you're here. Yassine says sigma, it's already written, result probability between 0 and 1. Yeah. So that's the key takeaway, guys, right? Whenever you have a 1 over something, you're going to get a probability, right? You're going to get something that's less than 1, right? So that's exactly what the sigmoid function looks like. Osama says logistic function. Yeah, that's exactly right. Is it Kowalyashu? Kowalyashu, welcome. I think it's your first time on Instagram or first time joining us. Thanks so much. Kowalshu, on Sundays, I usually do a little bit of a tutorial. I don't take individual questions, but you're welcome to hang out. You're welcome to, contribute to the chat. But I usually only take questions Thursdays, Fridays, and Saturdays during those live streams. All right, so what else can we learn? What about here? What does this tell us? Does somebody want to take the... Oh, come on. Why can't I highlight this? There we go. Anybody want to look at this and tell me what this means in plain English? You know what? And let's go ahead and put this... Let's just look at these 3 lines. I'm a managing director, right? Explain it to me like I'm a managing director. What's going on in these 3 lines? Who wants to take a shot at explaining that to a managing director? Osama says it's the number of nodes. Okay, but give me a little bit more, Osama. Give me a little more detail. Hansla says structure of the neural network. Okay, so describe that structure, Hansla. What is it? I think you're right, but what is the structure? Explain it to me like I'm a non-technical person. What do you guys think? What's going on in those simple lines of code? Yassine says we are taking 2 known informations. We have processing them and then give 1 result telling us how likely something is happening. Okay. Yeah, I like that. Right? We know that we have 2 pieces of information that are going to be coming into our neural network, right? We know that we're going to have some processing. And we know we're going to have some output that tells us how likely something is happening, right? Like a probability, right? And we know that because there's only 1 output, right? So it's going to give you a probability of how close it is to one class or another. ChatGPT already told us that it's setting us up with an XOR function, so it's a 0 or 1 answer, right? Fabricio says inputs are your X features and Y true value, and are hidden layers and the number of layers which contain the neurons. The types of layers store patterns so they can be used to predict or classify a future value. Great answer. Terrible for a managing director, right? The managing director stopped listening to you about 4 words in, right? So I agree with your answer, but you're probably going to lose your audience in that one. So guys, I'm bringing this up because for some reason, this week it's been super popular for people to approach me with questions about soft skills. I've gotten a ton of soft skills questions this week. This is one of those soft skills you should be practicing. Like, I get this, I understand it, I wrote the code. How do I, 2 things to practice. How do I explain this to a managing director? And how do I explain this in less than 5 minutes? Or as briefly as possible? It probably wouldn't take you 5 minutes to do this, but how can I explain this in 30 seconds? Those are 2 very important skills to practice when you think about improving your soft skills, your presentations, things like that. I get it. I understand it from a technical perspective. But how do I teach this to a non-technical person, number 1? And 2, a non-technical person like a managing director. And 2, what is the briefest way that I can explain this? Under 30 seconds, under 1 minute, under 5 minutes, depending on the problem. Super important for soft skills. Okay. So now we also have our hidden weights. And we also have our output weights. So remember, as we've seen before, you're going to have your inputs, but the whole secret sauce of neural networks and of most models is the hidden weights, right? Because that's modeling, right? What's the factor? Like, what's the input? And what weight do you want me to assign to it? And then I put those together and I come up with a new answer, right? So the hidden weights is like the result. Sometimes, when you see like the OpenAI documentation or other things, you might hear them talking about the weights file, right? Because in a lot of modeling situations, like, that's what counts, right? The weights file. Like, I don't care what inputs you want to give me. You can give me whatever inputs you want. What's important is how I'm going to weigh them. So right here, that line 27, that collection that we're putting together, that's where the money is, right? That's the payoff. So it's giving us very simple training data. If you've never seen an XOR table, this is what an XOR table looks like. A 1 or a 0 is a 1. Anything else is a 0, basically. If that's new to you or you're confused on that, what you want to look up is you want to go out and Google or educate yourself on Boolean logic. That's where this is rooted. Like, when you hear about an XOR function, that's rooted in Boolean logic. I happen to know that because, when I was in high school, I did take a lot of electronics engineering courses, so I had to sit there and learn the different chip diagrams and stuff like that. But here it shows XOR just because it makes for convenient training data. But if you want to know a little bit more about it, perhaps it's not critical to data science, but if you just want to increase your thinking, go ahead and look up some Boolean logic items. So as you can see here, basically in our training data, these are our inputs, and then this is the output. So can we build a neural network that recognizes that type of XOR function? That's essentially like the task, right? And then here, it goes ahead and runs it through a number of iterations, a number of training cycles, or if you want to sound professional, the neural network's term is an epoch. An epoch is a training iteration that you let your neural network go through. It's going to come in and do some forward passes. Excuse me. It's going to go ahead and look at the different errors that are made. And then it does a back propagation pass. So this is where I'm hoping to stop. This is where I'm hoping to stop today so that we can have a much bigger discussion about this next time. But if anybody wants to take an advanced shot at this, let me know in the chat. What is back propagation? And you can explain it any way you want. You can go technical or not. It's up to you. If you don't know, that's okay. But what is back propagation? We're going to go ahead and update our weights. We're going to update our hidden weights, right? This is where we say, okay, we ran an experiment. Now we're going to update the weights. And then we return. We go back and we do it all over again, right? Fabricio says, I recommend to use the TensorFlow Neural Network Playground. It helps visualize the layers and neural. Yeah, but Fabricio, we want to learn without any frameworks at first, right? We're not trying to learn TensorFlow. We're trying to learn neural networks, right? So keep that in mind. Lanry says 10,000 times. Oh, and also Fabricio, another thing you guys got to keep in mind, and this is something I also talk about to a lot of my clients. Just because you know a particular framework doesn't mean you're going to have access to it at work, right? Tools will be dictated to you, right? If you have the unfortunate luck in your life to end up working for a place that uses PyTorch, you're going to use PyTorch, right? You're going to hate yourself. You're going to want to quit because they make you use PyTorch, but that's what they use. That's what you're going to use, right? So we're trying to build up a good foundational understanding so that we can use other tools in the future, but not PyTorch. Okay. So here, pretty simple. For every 1,000 epochs, it's going to tell us how we're doing, and then it's going to tell us how we did with XOR. Let's run this code. There's some changes I want to make already, but as a first iteration, let's run this. Lanry says 10,000 times. Yeah, Lanry's right. Lanry is referring to the epochs for the iterations we're going to be doing, and we set that earlier here, right? We said we're doing 10,000 epochs. Right? Actually, guys, do you see this number? Is that valid in Python? To use an underscore? If it is, that's my first time seeing it. What do you guys think? Have you seen that, or is that an error? Is that a hallucination? I didn't catch that the first time. Let me know in the chat. Have you guys seen this before, or is that an error? Let me know, guys. A number with an underscore? I've never seen that. What do you guys think? Will it work, or is that an error? Let me know in the chat before I run this. I mean, of course we could run it and we'll get an answer, but is that an error, guys? Yeah, okay. Yassine says, I've never seen it either. Fabricio says that's wrong. It should be 10,000. I've never. Yeah, so guys, that's funny. We have an error. Lanry says, nope. Lanry, I'm assuming you haven't seen this before. Yeah, guys. So, all right. So right out the gate, 03, is it 03 that yeah, 03 is failing us, guys. We looked at these lines earlier and I didn't catch that. But yeah, that should not work. That should be okay. Lanry says Python allows underscores and numbers. Is that true, Lanry? I've never seen that. But you know what? Let's try it, right? but it felt like it was letting us down right away. All right, but let's try it. So I'm in my code. Let me know if you need me to make this bigger. Actually, I just made it smaller. Let me make that bigger. Okay, so Lanry is saying that that is allowed in Python. Okay, guys, so we have nny, nn1.py, nn1. Okay, well, so a couple things have happened here. One, O3 was not incorrect. O3 actually taught us something. I have never seen that. Neither had Yassine or Fabricio. But it does work. Lanry, you've seen this before. Good to know. Thank you. I had never seen that before. So that's very interesting. Very interesting. Okay. Thanks, guys. That was interesting. Okay. So what are we looking at here, guys? Khalif says, yes, I think I heard that before as well. Okay, well, but I think we can agree it's not standard though, right? Because yes, maybe it's acceptable in the Python syntax and all that, but that's pretty unique to see that. All right, so O3 taught us something. Let's see what else it taught us. So what do we have here in our output, guys? So here, as we saw, every 1,000 epochs, every 1,000 training cycles, it was going to give us an update on where it's at, right? Does anybody want to take a shot at interpreting what this loss number is? Because we talked about precision, we talked about accuracy and recall, but loss is also a valid a way to measure your progress on your neural network, right? Does anybody want to kind of give me an explanation of what loss is? And are we looking for a big number, small number? What's a good loss? Like, how do we know that metric is headed in a good direction? And if you want to think ahead, I want you to think about this down here. Does somebody want to take a shot at interpreting this table? What do you guys think? Why do we have nothing but decimals here? So Fabricio is saying the difference of true and predicted value reflects how accurate your model is at predicting or classifying. Okay. Yassine says we are looking at the evolution of loss as we move through the epochs. Okay, so you're saying loss is prediction error. Okay. Give me a little bit more. Give me Fabricio and Yassine. Give me just a little bit more. Okay, so Narina, is it Narina? I think it's Narina or Naren. Narina, let me know how I pronounce your name. But Narina says predicted values and actuals, the difference. Yeah. Narina, I think that's the best answer so far. Loss is a representation of how far you are from your actual results, right? Your ground truth versus your predictions. Yeah, Starry Vibes also says how well the model's predictions match the actual values. Yeah, that's exactly right. Jonathan, welcome. I think it's your first time. Welcome over on YouTube. If the distance between the prediction and actual value, the closest to zero is better. Jonathan, you read my mind because that's the next question, right? So if you know that loss is the difference, do you want a high number or a low number for this metric? And Jonathan's right. You want to be as close to zero, right? Now, you very rarely reach actual zero. You'll be in the decimals, but you want your loss as low as possible. An ideal neural network has very little loss to it. Well, and actually, I should say any model, because loss is not unique to neural networks. Fabricio says it's doing it 9,000 times and converging to a number to n. It's actually doing it 10,000 times, Fabricio. And we know that because that was in the code, right? So that's how many times the neural network learned. Okay, so I think we have a pretty good understanding of what's happening in the top portion of this, right? But what about the bottom portion? Okay, it's Naren. Naren, thank you so much. Naren, I'm pretty sure it's your first time. Thanks for being here. Really glad to see you. So Naren, right now, the question in front of the chat is, what about the bottom part here? What is this? How are we interpreting this? And if you're not 100% sure, if anybody in the chat's not 100% sure, tell me about the decimals. Why is every result here a decimal? Landry says loss starts high, meaning that the predictions were initially bad. Yeah, that's exactly right, Landry. So Landry's bringing up a good point. Monitoring your loss in the way that we see here is a good way to track the progress of how your neural network is doing. Ideally, you'd want to see loss continually go down. That's not always going to be the case. Loss can have variance in it, but as long as you're seeing an overall downward trend, that's a good thing, right? Manoj says learning rate. Starry Vibes says it's a confusion matrix. And Starry Vibes added 2 question marks. So I'm assuming that it's a shaky answer, Starry Vibes, and that's okay. That's okay. Okay, Yassine says there are predictions for each case. It's a decimal because it's a probability. Yeah, so guys, look at Yassine's answer. That's the right answer. So Starry Vibes, this isn't quite a confusion matrix. This is actually a display of what the model would give you as an answer. So this is saying if I use the model now, or the weights that I've learned, right? If you gave me 0, 0, I would give you this answer. If you gave me 0, 1, I would give you this answer. 1, 0, I would give you that answer. And 1, 1, I would give you that answer. So that's different than a confusion matrix. This is more telling you like what the model usage would look like, what answers you would get in an answer. And Yassine's right. It's all a decimal because guess what? We saw the sigmoid function, right? A sigmoid function is always going to give you a probability, which by definition is between 0 and 1, right? Landry says it drops rapidly after a couple thousand epochs, showing the network quickly learn the basic XOR. Khalif says the output is a probability between 0 and 1. That's why the output is a decimal. Yeah, so Khalif, you're right about that. So Landry, I want to go back to your answer. So guys, I want everybody to read Landry's answer. I'm going to read it one more time. This relates to loss. It drops rapidly after a couple thousand epochs, showing the network quickly learn the basic XOR. Landry, I love you, my friend, but I'm going to disagree with you here. So guys, very important. Write this down. Write this down. Don't confuse dropping loss with a good model. It means you might be headed in the right direction, but that doesn't mean it's a good model. Okay, guys, so take what I just said and then look at the second results. Or this table down here, this second table. So we just agreed that these are probabilities because it's a sigmoid function. XOR is a 2-category problem, right? Essentially. What do you guys think? Interpret these numbers for me. What do you guys think? What's your interpretation of these numbers? I'll very quickly remind you, let me go back here, that this is our source data, right? This is our training data. This table is what an XOR table looks like. If you go out and look for Boolean values, a Boolean logic table, you'll find this in textbooks or Wikipedia or whatever. This is a valid XOR table. So now look at this. Is this a good model? What do you guys think? Ratnajit says, do you also mean the loss is equivalent to the probability loss? No. This relates to the differences between the predictions and the ground truth. Or maybe you have a different definition or probability loss that matches that. Let me know, Ratnajit. Starry Vibe says it doesn't feel good with 0 and 1 and 1 1. It doesn't feel good with 0 and 1 and 1 1. Okay. So Starry Vibes, I don't want to put words in your mouth, but I'm assuming that you're catching on to that this is 0.5 and 0.5. So I think Starry Vibes is right. I mean, it's 50-50. If your model is 50-50 on a 2-category problem, is that good? Sounds like you're just flipping coins. Right? Okay, so I skipped over this answer because I wanted to give people a chance to reply, but Yassine, Khalif, let me go to Khalif's answer. Khalif says it mistakes the last predicted value. It mistakes the last predicted value. Sorry, I don't know what you mean by that. Okay, but let's go to Yassine's. Yassine says bad results. It hasn't learned the logic yet, and yeah, I would agree with that. These are terrible results. Terrible results. This is a bad model, right? So why do I say that? Oh, I made a mess on my screen. Hold on a second. Okay, why do I say that? So Landry, this also comes back to your statement. It has not learned the XOR model at all. These are horrible results. So a couple of things are sticking out at me. Starry Vibes already caught on to it. You're 50-50. You're 50-50 on 2 classes, which means you're flipping coins. Your model hasn't learned anything. You might as well just ask it to choose randomly, right? Here's the second thing that caught my eye. What caught my eye too was the 0.5 here and the 0.97 here. Now remember, we said that an XOR function is either a 1 or a 0, but not both of either is a 1. So from an input perspective, these 2 rows are exactly the same, right? They both result in the same answer of 1. But look how different the results are. It's counterintuitive, right? That I could give you a 0, 1, and a 1 and a 0, but yet the way you learn that is going to be like that disparate from each other, right? Like how did you learn this one but not this one? It's the same answer, same inputs, right? Like that's counterintuitive, isn't it? So yeah, so Landry, I disagree. It's not actually a very good model. So those 2 things caught my eye immediately. Now that's to me in my trained eye. But eventually I want you guys to think about that, developing that skill. Because if you have the same classes, why are you so far away from each other? 5, it's uncertain. 501, it's uncertain. Landry, it's not that it's uncertain, it's that it's ineffective. Because what if I told you that this was a 5-class problem and it gave you a 0.5 answer? That's actually pretty good, right? So it's not that it's uncertain, it's that it's terrible for 2 classes. If it's two classes and you tell me your model's 50-50, then you might as well flip a coin, right? Like you might as well write an algorithm that says, give me an even or an odd number, and if it's an odd number, do this, and if it's an even number, do that. Like you're not training anything. It hasn't learned. You haven't created those synapses that simulate the human brain so that this model can live on its own, right? So it's not that it's uncertain, it's that it's just like not good business, right? So I don't mean to be picking on you, but I want you guys to kind of think about this in those terms. Like, yes, you created a code. Yes, it runs. Yes, it looks fancy on the screen, but is it good? Like, have you really made a business impact here? Like you haven't, right? Okay. So Landry, you're also bringing up two interesting portions here. Landry says 0.971 rounds to 1, very accurate. Landry also says 0.031 rounds to 0, close to correct. Ah, yes. Okay, so Landry is bringing up an interesting point here. What about this one? What about the 971? And what about the 031? He's right in the sense that these two classes or these two inputs are actually not terrible on the prediction side. But the key is, how do you make a final decision? Your final decision is not 0.971 or 0.03. Your final decision has to be yes or no, true or false, 1 or 0. We go left or we go right. So in practical usages of sigmoid functions, you have to create thresholds and say, here's the threshold. If you're above that threshold, I want you to tell me that the answer is 1. If you're below that threshold, I want you to tell me the answer is 0. Does that work here? Because, by the way, this is another thing that caught my eye, but I wasn't really anticipating that we'd be talking about thresholds right now. But think about that. Look at these numbers. What threshold are you assigning that would work? Okay, Yassine has put the answer. Yeah, we set a threshold. Yeah, that's right, Yassine. You would set a threshold for your sigmoid results. Yassine says, no, it doesn't work. Scores are very close. It's not that they're close, Yassine. It's that no threshold works. Right? Like you couldn't put a 0.5 threshold because this one would be incorrect. Right? You couldn't put a 4.9 threshold because then this one would be incorrect. So it's not that they're close, it's that the model's no good. And could you round up? No, you couldn't, because technically this one would round up to 1 when it should be 0. You could choose to round up. That is not necessarily an invalid approach, but rounding up usually fails, or rounding down, any rounding, usually fails when you have a lot of classes, right? It might work for something like this when it's binary, but not everything in life is a binary problem, right? Okay, so Landry is also saying, do we need 20 epochs, 30K epochs? Should we adjust the learning rate? Fabrizio is saying, should we do hyperparameter tuning? Yeah, so that's the next question, right? What do we do about this? So how do we improve this, guys? Let me know in the chat. Let's try some modifications, because these are terrible, right? We cannot present these results. These results are trash, right? So what can we do? Let's go back to our code. So give me some suggestions, guys. What do you want to do? What can we adjust? What do you guys think? Name is Can, says hi. Hey, how you doing? Nice to see you. Glad you're here. I think it's your first time. Good to see people over on Twitch. Right now, we're discussing neural networks, so feel free to hang out. Starry Vibe says add hidden layers. Yeah, we could do that. I don't want to do that in this scenario because it's a little bit trickier to do it when you're working in raw code. But yeah, adding additional layers is good. Adding additional layers helps with it's just made a lot easier with some of the frameworks out there. Okay, so Khalif says adjust the learning rate. Yeah, I agree with that. Yassine says agree with Starry. Yeah. Yeah, you guys aren't wrong about the hidden layers. It's just a lot harder to do when you're working in raw code. So we'll do that in other instances. Yassine says increase epochs. Yeah, absolutely. That's another good one. You can always just throw more time at it, right? Because to Landry's point, the loss was headed in a good direction. Maybe not very fast, right? Like here it went from 0.2521 to 0.2518. But at least it was headed downwards. So yeah, more epochs shows possibilities, right? Fabricio says add more layers, create a new class called config, a combination of layers, can be different different layers. Feature tuning, normalization, and remove outliers. But we don't have outliers. It's an XOR table, right? So let's focus on the problem at hand. Some of these you're right. Some of these I'd give you some pushback on. But yeah, I mean, let's focus on the problem at hand and what we can do. Atlas Joy over on Instagram says, hi. Hey, Atlas, I think it's your first time. Welcome. We're talking about neural networks and how we can improve our results. Here, what about this? What if I were to do this? What does that do, guys? Naren says more training data for the 50-50 cases. We can't, guys. We can't, right? I mean, an XOR table is pretty straightforward. This is our entire data set, right? And this is really good practice, guys, because there's going to be plenty of business cases or like real world data science cases where more data is simply not available. You're going to go back to the stakeholder and say, hey, we need more data. And they're going to tell you, nope, not happening. Do what you got and do what you can with what you got. So no, Naren, we really can't do that. This is the entire universe of an XOR table. Yassine says it adds nodes in the hidden layer. Yeah, that's exactly right. So we could definitely add more nodes in the hidden layer, right? Make the network bigger, or at least that layer in our network bigger. So let's try that. Remember, there's going to be an interaction effect here, right? So in a real world scenario, you probably would try some of these changes or some of these tunings in combination with each other just because of time. But for now, I want to just go ahead and just show you guys real quick, right? What does it do when we go to 10 layers? Okay, so before we do this, actually, I want you to think about this. One, is it reasonable for us to expect an improvement? Yes or no? And two, what does this do to the performance of the neural network? All right, so think about that. What should be our expectation going into this? And what will it do to our performance of the neural network? Think about that. All right, let's run this. Basically running the same code, just modified. Okay. All right. Look at these results, guys. Okay, Yassine, 100% right. Slows it down, right? And it generally should improve results. He's right. Yassine is right on this. You're going to expect worse performance. Why? Because we just added more nodes. When you add more nodes, you add more calculations. And if you have a network with multiple hidden layers, adding nodes has an exponential effect because now you're doing so many more calculations. Because every node is connected to each other, right? So Yassine's right. You can have a reasonable expectation that it'll improve, but it does affect performance. Denelson says batch size, so it makes bigger steps for epoch. Denelson, yes, but we have limited data. Adjusting batch sizing can work when you have like massive data sets, but we have very limited data, and a lot of problems in business are going to have limited data. So you can't always rely on batch sizing. Okay, so now what do we think? Now look at the tables. Look at both tables, and tell me what you see. What do you see? Starry Vibe says it adds complexity to the model. Yeah, absolutely it does. And adding complexity in neural networks means added time, added processing power. So yeah, you're right about that, Starry Vibes. Okay, so Yassine says good results, good model. Is he right? What do you guys think? What do you guys think? Fabricio says you can suffer from vanishing gradients if you keep adding nodes too. No, I don't agree with that. You get vanishing gradients when you add layers. But if you keep the same number of layers and increase the nodes, the probability of you creating vanishing gradients is not as high. Because remember, vanishing gradients happen when you do the multiplication across layers. Right? Because multiplication is ultimately what causes vanishing gradients. You multiply a decimal times a decimal, the only thing you get is a smaller decimal, right? But you're not doing that if you're expanding the nodes, which is kind of like a vertical expansion versus a horizontal expansion of additional layers. So I think we're okay on the vanishing gradients as long as we don't expand the number of layers. Yeah, so Denelson says with more layers. Yeah, so Denelson's right here. So Fabrizio, I want you to look at Denelson's answer because he's right on that. It's the layers that get you the vanishing gradients, not the nodes within the same number of layers. Okay, so Starry Vibes agrees with Yassine's answer. Good results, good model. Yeah. Okay, Yassine, that's exactly, yeah. So while I was explaining the answer, you guys had it in the chat already, but yeah. It's the layers that get you the vanishing gradients, not the nodes. Khalif says it is better now. Landry says more hidden neurons give the network more power to learn. Yeah, that's right, Landry. Just as long as you recognize that more power comes at more computing time and cost, right? Okay, so it seems like you guys are in agreement that this is going well. Why? What tells you that? Like, give me a rationale, right? A good scientist always has a rationale for what they say, right? So what's your rationale for saying that? I mean, don't just tell me that it looks better than the previous effort, but what is it about these results on their own that make it look better? What do you guys think? Fabrizio says, you're right. It's through the chain rule multiplication with layers on nodes. Yeah, that's exactly right, Fabrizio. So what do you guys think? What is catching your eye in these results? What do you guys think? Landry says it predicted 4 out of the 4 XORs, and it has a lower MSE or lower loss. The probability outputs are fair now. Yeah. Both Landry and Khalif are on the right track there. right? I mean, the losses are great. As I mentioned to you guys, you'll never actually get to zero, but getting to the 0.00 levels, you're on the right track with your loss. And then down here, right, you're approaching what should be the right answer, or what we know is the ground truth, right? Because we know that 0, 0 should result in 0, and we know that 1 and 1 should result in 0. And these values reflect that. We know that O and 1, 1 and O should result in 1, and these values reflect that. Earlier, I had told you that I was very uncomfortable with this class being 0.5 and this class being 0.97. Like they should be, those two numbers should be close to each other because we know that these two outputs result in the same answer. Now we're seeing that. I mean, look, now it's night and day. Now it's 974 and 975. That makes me a lot more comfortable, right? Because they should be close to each other. It's the same output or same class, right? Yassine says the scores for the different classes are very far from each other. We can easily set a decision rule. Yeah, that's exactly right, Yassine. So coming back to that threshold, right? Now we can see our way to a threshold, right? Now we can say, well, now we can go back to Lanry and we can do a rounding function, right? A rounding function would work here, a round up or round down. Or we could say, if you're above 0.8, go ahead and give a 1. If you're below 0.8, give a 0. Right? We couldn't do that previously, right? We could even use 0.50 in this scenario if we wanted to. Lots of numbers we could use, really. So yeah, these are great results. And the only thing we did was add more nodes to that one layer. That's it. Right? Okay. So let's undo that. Let's undo that. We did 10 nodes. Let's go back to 2. What about epochs? Somebody suggested more epochs. Let's do that. So now instead of 10,000, we're going to triple the number of epochs and go to 30,000. Okay? Okay, what do you guys think now? So we can see that we clearly did more epochs, right? What now? Tell me about these results. What do you guys think about these results? Not JC White. Welcome, JC White. Nice to see you. Is this R? No, this is all Python, my friend. Oh my God, if I'm ever teaching R to you guys, please kill me. Oh God. Okay, guys, new rule. If you ever see me teaching R on this platform, go ahead and unsubscribe, please. Something has gone terribly wrong in my life if I'm here teaching you guys R. Oh my gosh, you're going to give me a heart attack there, JCY. Oh my gosh. No, wait, guys, come on. Listen, guys, do me a favor. I want you to write down the local emergency phone number in your area. And if you ever see me broadcasting R and teaching you guys R, go ahead and call that number and send them to my home address. Tell them that I'm obviously having a stroke online. I'm having a stroke live in person, teaching you guys R. Go ahead and call the authorities if that ever happens. No, this is definitely not R. Okay, please look out for my mental health and well-being, because if I'm teaching you R, something has gone desperately wrong. My dog died. I'm having a stroke. My car got stolen. It's obviously like the worst day of my life if I'm ever on here teaching you guys R. Okay. Thank you for your help, everybody. Okay, so focusing on these results, Yassine says it's less attractive than the previous one. It still has trouble for the last use case. However, we can set the decision rule accordingly. Yes, we could set the decision rule accordingly. I just saw a percent and I thought you went down south. Oh well, I'll definitely be going down if I'm teaching R, but no, this is Python. Okay, so Yassine, yes, Yassine, you're on the right track. I mean, what you're saying is factually true, but the real lesson here is that we just need more epochs, right? Because we're still headed in a good downward direction, right? So, with the real takeaway is this. Let's go to 60,000 epochs, right? Like, that's the real takeaway. So 60,000, we should run this. What do you guys think? Did we do better? I want to look at this real quick. Landry says loss starts at 0.25, it ends at 0.168. It means the model is learning, but not very fast or not very confidently. Yeah, that's true. But here's the thing, Landry, it's learning, right? You know, one of the things that I always told my data scientists is make sure you always have a lever to pull on. What do I mean by that? It means that we should always just make sure we still have more studies to do, right? You're never dead until you run out of experiments. So yes, Landry, you're right, but it still should give us encouragement that, hey, there's still more to do here, right? There's still more meat on the bone. So yes, it's not learning great, but it's learning. There's still a lever to pull there, right? It was stuck on a local minima, I guess. Maybe. Let me think about where I want to go next with this, because there's so many things I still want to get across. There's two more concepts I want to get across, and then we're going to wrap up here. But let me show you guys something else here. Tell me about line 27. What do you guys see there? Because here's the thing, guys. How did we go from running 30,000 epochs and kind of sort of doing okay? But then we ran 60,000 epochs, and these results are more like the first model we ran at 10,000 epochs, right? Like it's more closely related to that. Why? Why is that? And I want you to look at what I wrote there, or what I'm highlighting there. What do you guys think? What do you guys think? Yassine says, yes, depending on the starting weights. That's exactly right, Yassine. So in this line is where our code assigns the initial amount of weights. Because remember, we already said it's factor times weights. But during your first training cycle, you got to start with some weights that you don't know what they are. So here, the code, the ChatGPT generated code correctly chose to give us random weights. That is one of the ways to do it. But is that going to give us consistent results when we run these models? No. right? Because based on where that randomness is and based on the number of epochs you give it, you're going to get differing results on every model, right? And that's kind of what we're experiencing here. What this tells me is that when we ran the 30,000 epochs, by random chance, our code just picked better starting weights. And because those weights were better, the 30,000 epochs was able to refine it to a relatively reasonable number or a more reasonable number. Whereas here in 60,000, again, just by randomness, it didn't pick such great weights. And then 60,000 epochs was not enough to get there. So if we run this again, different results. Wow, look at these. Those are much better results. Look at our loss now. Our loss now is 1598, whereas before it was still like 25 something. Or look at here how little our loss changed in the last, 12,000 epochs. But that's all just random happenstance, right? Because we started with the random weights, a set of random weights. So for your homework assignment, do you have to start with random weights? Is that a requirement? I want you to think about that. Okay, last thing I want to cover here. We've clearly seen two ways, two changes in our code that improve our model, right? Because we modified the epochs and we modified the number of nodes. We did 2 nodes and then we tried 10 nodes, and 10 nodes got us excellent results, right? We started off with 10,000 epochs and we worked our way up to 60,000, and we saw improvement there. Maybe not as good improvement as we'd want, but it's headed in the right direction, right? All right, so here's the question. Is there a difference between adjusting this and adjusting this? Are they the same? Are they different? Anything you should know before doing that? We adjusted this, the number of nodes in the hidden layer, and we adjusted the epochs. Are those equal? They both had improvement, right? They're both headed towards an acceptable model. But is there a difference? Let me know. Let me know in the chat. What do you guys think? If you're a little confused by this, I will admit that this is slightly more advanced. But let me know what you think. We saw improvement. They're both very simple changes in code. But is there anything else you need to know? What do you guys think? I'll give you guys a minute to think about that. Let me know in the chat. So Yassine is saying there's a difference. First one I can think of is that our model is with less nodes and more epochs. It means the model is still simple but well trained. Meeting the prediction cycles, we don't need big resources. I think you're on the right track, Yassine, but refine that answer for me a little bit. Let me know. Refine it just a little bit. Or if anybody else wants to agree with Yassine or give another answer. You're generally on the right track. Just I think it needs a little bit of refinement. What do you guys think? We made two distinctly different changes, but are they the same? Like, it doesn't matter which one we change? What do you guys think? Starry Vibe says adding more layers increases the model's capacity to learn complex patterns, while adding more epochs means they're running the training process multiple times. Yes, but what's the net result of that, Starry Vibes? Okay, so Yassine says, with more epochs, the model doesn't change its size. With more nodes, it does. Yeah, that's the right answer, guys. So again, if you don't know that one, that's kind of okay. That's a little bit more of an advanced question. But you should realize things like that, right? If you start putting everything we've gone over in neural networks, that should start to click in your mind. Adding more nodes adds more what? Adds more calculations, which means more processing power, which means that your weights file is now bigger because now you have to track more weights. So that means that you're going to need more hardware when you go to deploy your algorithm. What if they tell you that we want you to write an algorithm, but it has to run on like a small camera or something? So you might be space constrained, right? But epochs it does not increase your weight. It just increases the time for training. So maybe you have a project that can't run on GPU, it has to run on a CPU. That's okay. You can just increase the epochs because the epochs doesn't care. It's going to use the same amount of resources. It's just going to use them for a longer amount of time, right? Whereas nodes, you might hit a point where you have so many nodes, so many layers that you are pushing the boundaries of what a CPU can do. Don't get me wrong. I've already said before, GPU is not a requirement to work on neural networks. Don't let that stop you. You can do a lot of work on CPU. But realize that these two changes that we made are not the same. More nodes, more layers equals more processing time, which you may or may not have. Whereas epochs is just more development time during the training. Because epochs won't matter once you're deployed, right? Predictive cycles are usually just like one-shot items, right? Or one-time items, I should say, to be more accurate. So keep that in mind. We've made progress. We're clearly headed towards a better model, from our first one, but they're not the same. There are definitely implications to you increasing your layers and increasing your nodes, which you may or may not be allowed, depending on the solution you have. Okay. All right, guys, really good work. We covered a lot of really good stuff. I like how we've set ourselves up to talk about some of the more advanced items that I want to cover I want to cover in future lessons. So really good job. Really happy with the progress that we've done. So listen, now for next week, we're going to build on what we've learned, and then we might also build on it using the different frameworks that are out there, right? Because in the real world, you won't be writing code like this. You'll be writing it with the frameworks that are out there. Okay? So I'm going to have 2 classes next week. 1500 GMT, the same time now, if for the people that want to learn Keras, right? So I'm going to do Keras at 1500 GMT. And then if your mother never loved you and your parents never hugged you as a child, come later for the PyTorch, maybe like 3-4 hours later, because, PyTorch people are always flaky and late. And then, we might do some PyTorch, okay? But 1500 GMT next week, if you do Keras. If your mother never told you she loves you, we'll be teaching you PyTorch. And then, we'll kind of go from there, okay? All right. All right, guys. So really good work today. A lot of really good stuff covered. Thanks so much for the participation. Thanks so much for all the new people that are in the chat. Pavan, I see you over there on Instagram. Lots of new people today, so that's always encouraging. But yeah, guys, so we'll pick up here next week, next Sunday. We're also going to be talking about some more specialized cases. I know some of you mentioned learning rate in the chat, so I intentionally overlooked that because I'm not ready to talk about learning rate just yet. But I think we're gonna, make some progress on that next week. Starry Vibes says, "Thank you so much, sir. This session has been really helpful." I appreciate that, Starry Vibes. Yeah, I know a lot of you had requested a neural network series, and I think this is going well. So, kind of fun to teach this. I see at least 2 more sessions, maybe 3. But yeah. Let's just keep going, guys. I think we did good work today. Good work today. A lot of ground covered, and I really hope that this is helping you guys understand more about neural networks. Again, a lot of the stuff we talked about, I would consider like data scientist level 2-ish. So if you feel lost, maybe you didn't want to give a lot of answers because you weren't steady on some of these items. Might be time to review instead of doing more, less resume work, more study work, okay? Casual Economist, you've been here the whole time. You didn't even say hello. Thanks for the Sunday school. Yeah, thank you, Casual Economist. I love doing these on Sundays. Hina, welcome. I don't know if it's your first time or not. Let me know. After these sessions, can we go for data mining techniques? Hema, maybe. The next series I'm going to do a little robotic series. I think it was Starry Vibes that had suggested that one. I think it's a good suggestion. I have an idea that I want to do for that. So Hina, keep on coming back, keep on contributing. I might do something around that later on, but I'm already set on doing a robotic series after this series is over. And sometimes what I'll do is I'll maybe take like a 1 or 2 week break in between series, and we'll still meet, but we'll still just kind of talk about like other things, or like 1 day tutorials, right? But yeah, I'm kind of already set on doing a robotic series after this one. Yeah, sometimes during those single series, it's also good to just talk about different things, talk different frameworks or different things that people want to talk about. The PyTorch people usually come in here and tell us about how they're losers and their life isn't going well and how they can improve things. So we do a little bit of group therapy for that also. So it just depends on what we'll do on future series. Denelson says, "Thank you so much, Sir Dennis. As always, amazing content." Oh, thank you so much, Denelson. I'm just trying. Hope you're still driving safe out there. Casual Economist says, "I feel like I learn more when I'm not making crazy comments." Yeah, but you know what, guys? All crazy comments are welcome. So, Lord knows that I have my own crazy comments that I make and my own biases that I express on here, and that's okay. It's supposed to be an open forum. This is a safe space, guys. This is a safe space for everybody. Beat Drown, welcome. I think it's your first time. "I love data and learning by myself through tutorials, and I love your channel as it's practical. Where do I start from? NN was difficult for me to follow." Okay. So Beat Drown, if you go to my channel, in my playlist section, I have a playlist on the Introduction to Statistical Learning book. That would be a pretty good place to start because that's more of a machine learning book. And it's kind of hard to transition into neural networks if you don't have a really solid foundation on neural networks, on machine learning in general, excuse me. So I would start there, okay? But thank you for your honesty. I'm sure you're not the only one. I think other people, might be shy about expressing that. But yeah, I mean, I'm putting this stuff out there for you guys to kind of help measure yourself. Because like I said, I would expect the level 1 data scientist to be able to do virtually everything we covered, right? Like, and some of these questions I would 100% ask on interviews. So yeah, so if you're able to show maturity like Beat Round here and take an honest assessment of yourself, then this is a pretty good measure of where you're at. Danielson says, still out doing errands, but this session has made them very enjoyable. Though I didn't take my earphones, so I had some people turn around when I was next with the stream on. Wow, that's crazy. So the stream is being heard while you're out doing errands. That's crazy. That's pretty cool. For some reason I find it to be pretty cool. Of course, now you're gonna have people thinking that you're just listening to some crazy man who's talking about PyTorch and mothers that don't love them or something. So I wonder what they make of that. But yeah, guys, so great session. Really happy we did this. I can't believe you guys made me go for more than 2 hours. I'm an old man. What are you guys doing making me go for 2 hours? That's crazy. But thanks everybody. As always, I love the fact that I have followers from all over the world, but it makes me worried for you guys because, we live in such a crazy world. So please, take care of yourselves, take care of your families, and I'll see you guys next time. Slides. Okay, guys. So we've been doing these lightning rounds in these last few lessons, and I think they've been going well. So let's keep going with the lightning round. Up on the screen, I have a variety of questions. These are the same questions we went over 2 weeks ago. I'm going to have 2 lightning rounds, guys. Okay? We're going to repeat the one we did before, just as a review, because I know it's been 2 weeks. I took a break last week for Mother's Day, So let's review that, and then I'm going to have a new set of lightning round questions. So up on the screen, 6 questions. You can answer one or all of them, any of them, and you can go in whatever order you want. Let's just start filling up the chat with answers, okay? So 1, what is a neural network? 2, how many layers are in a neural network? Is there a maximum? Is there a minimum? 3, what's an activation function? 4, what are some of the negatives of neural networks? 5, what are some of the metrics we use to evaluate a neural network? And 6, what is a sigmoid function? What is a step function? So think about those. I will look at some of the chat messages. I see you guys. And go ahead and start filling up the chat with some of your answers, okay? And if you don't know, that's okay. You can use these questions as a, as a measure of where you're at. I wouldn't call these interview questions. Maybe for some internships you'd follow, but these questions are probably too basic to be interview questions, at least in my eyes. So you can also take this as a guide for where you are personally. If you don't know the answers to some of these, then you might need to study a little bit more before your next interview, right? And same goes for the next one. But it's a good way for you to kind of measure kind of where you're at, okay? All right, so Khalil says, good morning, how's everything? Khalil from Germany. Khalil, welcome. I think it's your first time here, so welcome. I don't have a lot of followers in Germany, so glad to see that you're here. Hope that you're doing well. Akash says, any sort of questions I should be prepared prior to the interview? I mean, beginning would be introduction and so on. So any pattern you would recommend? When's the interview? It's on Tuesday. Okay, first of all, Akash, my best recommendation to you is that preparation for an interview begins long before 2 days, right? I mean, your interview's in 2 days, right? So don't try to crash yourself out right now studying or whatnot, right? Like, the best you can do right now is just relax, be yourself, just take a deep breath and go into the interview with as clear of a mind as you can, and that's it. That's really all you can do 2 days out, right? When I work with my clients, when we have a lot more time to work with, I will do mock interviews. I will come up with questions for them to research. They usually send me the job description of who they're going after so that I can, critique them and kind of give a probability of them landing the position, give them different things to think about. according to what the job description says and what I know of the person, the work we've done together. So if you really want to prepare for something, it takes more than just a couple days, right? So 2 days out, since it's on Tuesday, the best thing that I can do is, just tell you to calm down, relax. Don't stay up too late the night before the interview. Get as much rest as you can. And just go into it with a clear mind. Just do your best. Right? That's really all you can do. 2 days out from it. Your work is your work, so feel free to stand by it and be proud of the work you've done and express that as much as you can in the interview. But just do your best, and we wish you luck and let us know how you do. Okay. Okay, so we have a couple people going for the same one. We have a couple people going for question 2. Yassine says there's no maximum number of layers. The minimum is 3 input, hidden, and output layers. Great, thank you, Yassine. And Yassine, I'm glad you chose that one because we did have some back and forth on the previous session. We did determine that you do have to have at least 3 layers. Some people were suggesting that it's 2 layers. But if you just have an input layer and an output layer, you don't really have anything, right? So the minimum really is 3 layers. Osama agrees, says question 2, minimum 3 layers, but we don't have a maximum number of layers. Okay. All right, so maybe Yassine and Osama, you want to take a look at number 4. What are some of the negatives of neural networks? If there's no maximum number of layers, then why doesn't every neural network just have 50,000 layers? Right? So guys, if anybody in the chat wants to pick that up, why doesn't every neural network in the world just have 50 or 100,000 layers, right? What stops us from doing that? More layers, more better, right? All right, guys. So anybody else who wants to take a chance at answering? What is a neural network? How many layers are in a neural network? What's an activation function? What are some of the negatives of neural networks? What are some of the metrics we use to evaluate a neural network? And what is a sigmoid function and what is a step function? You can answer in any order, right? You can choose to agree with people. You can just say, hey, I agree with what Yassine said, or I like what Osama said, right? You can just say that. Or just take a stab. Take a stab at one of these answers. But again, if you're having trouble with these, then it might indicate that you need to do a little bit more work on the neural network side, okay? Michael, our good friend Michael says, hello, Sir Dennis and everyone. I hope we've all been doing well. Michael, so good to see you. I know you're such a consistent supporter on Sundays. I know you love the Sunday session, so thanks for being here. I've been doing really well. How are you, Michael? Michael, remind me, I think you are from, is it Nigeria? I think it's Nigeria. So hope you're doing well out there. But yeah, doing well. Thank you. Just getting our Sunday underway. Michael, you came in just in time for our first lightning round review. We're going to have 2 lightning round reviews today, Michael. So this is the first series of questions. You might recognize it from the previous Sunday. And then we're going to get to a whole brand new set of questions pretty soon. Okay? Okay, so Denelson says, some metrics used for neural networks are MSE and MAE. For more visualized metrics, we can use a classification matrix. Okay, Denelson, I see where you're going with that. Classification matrix, confusion matrix, you can use those interchangeably. So thanks for that. So that's Denelson going after question 5, I believe. So Yassine for question 3 says an activation function is a function that is used to decide whether a neuron fires or not, therefore whether to communicate with the next neuron. That makes sense. I think I'm on board with that. If you think that's a good answer to you, and you want to participate, you can just say I agree with Yassine. But as we've always talked about, right? The neural network is like the series is like cells in your body, right? As my hand goes up, there's a whole series of cells that are firing from my brain all the way down to the tips of my fingers that are telling everything to do, right? But there's reasons why these cells are firing and the ones in my shoulder over here or in my hand over here are not, right? So that's what an activation function is. It decides what's moving and what isn't, right? Osama, for question 4, the negatives of neural networks says requires large data, expensive training, and hard to interpret. Ah, Osama, you had me at hard to interpret. You lost me. It requires large data. Does it require large data? Does it? Somebody let me know in the chat. Does every neural network require large data? Osama, I know you were here last time we met, so think about the neural network we worked on last time. We did some modifications. We learned a lot from that neural network, and how much data did we have there? So I get it, guys. I get it. A lot of the idiot influencers I talk to you guys about out there, they always include, you know, deep learning and neural networks in the same tutorials or the same vocabulary. I get it. And it is true to say that when you have a lot of data, a neural network is usually good for that. But don't make a logical fallacy there. Just because neural networks are good for deep data sets doesn't mean that neural networks require deep data sets. Right? So I'm kind of giving you guys the answer, but think about the work we did a couple weeks ago, guys. How many data items did we have in there? We had like what? 6? Was it 6 or 4? That's not deep data, right? Yassine says some negatives are vanishing or exploding gradients. Yep. Yep. Okay, guys, so for extra credit, what's a vanishing gradient? Right? I didn't ask that in this one. Perhaps I should have on my other lightning round. Denelson says negatives of neural networks are memory storage needed is exponentially increased at each added hidden layer. Yeah, that's exactly right. Right? When you add those layers and you're adding those calculations, you're adding additional weights, and those weights make up like the file, right, of the neural network. So yeah, you're right, Denelson. That's another reason why every neural network isn't like 100,000 layers, because that means that every file would be huge, right? And maybe you need to run your neural network on some small hardware, so you can't have a large neural network. So yeah, good answer. Anybody else? And let me know if you guys are done with this, because then we can go to the next lightning round. But think about some of the items that we've talked about on this one. Hey, in the chat, we have Ox. Ox says, oh, look, it's Daddy Dennis. What up? Thanks so much, my friend. Good to see you. Hope that you're doing well out there. Guys, Ox is a really good guy. He's an expert at cybersecurity. He basically does what I do for data science. He does for cybersecurity. He also doesn't tell you guys on pie in the sky dreams and all that nonsense. He's a good guy. So if you're interested in cybersecurity, which I know a lot of data scientists are, go check out his channel. He's a really good guy. Ox, so glad to see you here. Hope you're doing well, my friend. All right, so Yassine wants to go after question 6. 6 says a sigmoid function takes an input and based on it outputs a probability score from 0 to 1. A step function takes an input and outputs one value from a given set based on some threshold. Yeah, that's excellent. I think that's pretty good explanations for sigmoid and step functions. So thanks a lot for that, Yassine. Just to put a finer point on that, I thought I had my charts up for that. Here we go. There's your step function. So as Yassine says, this is your threshold, and you're either at some value or you're not, right? Usually, well, I shouldn't say usually. Usually it's a binary like 0 or 1, either you are or you aren't. But that's the step function. Whereas a sigmoid function, I believe is on my next screen, is a little bit more probability based, right? A little bit more nuanced. There's a lot of values between 0 and 1. Things don't always have to be on, off, true, false, yes, no, right? You can have variability in there, right? So that's a sigmoid function. Ox says, you are too kind. Thank you very much. No, you're welcome, my friend. You deserve it. I love the fact that guys like you and I can be out there giving out good information that's based in professional work, and just do it for the love of it. So I appreciate you too, my friend. Like I said, guys, you know, if you want cybersecurity without any trash or any nonsense, Ox is a good guy to check out. So make sure you give him a follow, please. Michael, for question 4, returning to our lightning round, says negatives of neural networks, difficulty in explaining results to stakeholders. Yeah, that's right. Neural networks are not known for their explainability, guys. And explainability is very important in business. Now, I know that's changed. There's tools and methods out there to help you with explainability in neural networks now. But yeah, neural networks can kind of be a little bit of a black box. You don't always know what's going on. So that is definitely a downside to neural networks. Okay, guys, so I think we're ready for the next lightning round review, and after that, we're going to get to code. So bear with me if you're looking to get to code. Bear with me, okay? And like I said, I consider this lightning round questions easier than the next one. So if you're in my chat and you didn't want to participate because maybe some of these questions are unknown to you or you don't know the answer, might be time to do some more neural network review, right? Because some of these I might ask for an intern interview, but these are too basic for like if somebody comes to me like wanting to be a level 1 or a level 2 data scientist, right? And certainly for like a lead data scientist, these are way too basic, right? So keep that in mind, guys. Okay. Part 2. So these are new questions. No one has seen these questions, okay? What is a confusion matrix? How do we assign initial weights to our neural network? What is an epoch? What is the effect of adding more epochs to our training cycle? What is the effect of adding more nodes to our layers? What are some of the things that we can do to improve the metrics of our neural network? So go to it, guys. You don't have to answer in order. You don't have to answer all of them. Just pick one and give me your answer. If you're incorrect, that's totally okay, right? We don't name and shame here. But again, some of these I would definitely add in a interview. In fact, I think I do ask what is a confusion matrix in some of my interviews. So again, if these questions feel too tough or you don't know, like you're a little bit lost, then you might not be ready for a data scientist interview, okay? So keep that in mind, guys. Keep that in mind. So what do you guys think? Let me know which one you want to answer. What is a confusion matrix? How do we assign initial weights to our neural network? What is an epoch? What is the effect of adding more epochs to our training cycle? What is the effect of adding more nodes to our layers? What are some of the things that we can do to improve the metrics of our neural network? And I just realized I'm missing a question mark. So let me quickly. What do you guys think? Go to it. Put your answers in the chat and we'll see where we end up. I see a lot of people coming and going over on Instagram. Welcome. You're welcome to stay there, or you can join us on YouTube, where it's a little bit easier to see the entire screen, but it's up to you. Also, if you are interested in joining my data science school, I'm still looking for founding members. I'm trying to find 1,000 founding members so that I can, get some support behind the school. My intent is to open by August 1st, but I'll never open if I don't get the founding members. So there's a link in your chat to please sign up. Please sign up right away. Please do not wait until August 1st because it's possible that I'll kill the idea before then. But if you'd like to, have a more comprehensive data science education from a real world perspective, which is what I provide, please feel free to, sign up. So I'll give you guys another minute here for some of these questions. Let me know what you guys think. You don't have to answer all of them. You can just choose one. You don't have to go in order. Just choose what you know. After we finish with these questions, we're going to go into code. We're going to start reviewing some of the code we did last week, which I thought was a lot of fun, and maybe do some more modifications there. What do you guys think? Any volunteers for any of these 6 review questions? Silence in the chat, guys. Nobody wants to take a shot at these 6 questions? Some of these you guys kind of sort of answered before. Like, I'm surprised that question number 1 isn't getting answers. I'll give you guys another minute here. Okay, so Manoj, welcome. Good to see you, my good friend from Bangalore. Says epochs refers to the number of complete passes through the entire training data set by the neural network during the training process. Yeah, that's a pretty good answer, right? Michael also answering the epoch questions. As an epoch is when all the data samples have been exposed to the neural networks for learning patterns. Yeah. So you guys are both basically giving the same answer. So yeah. So Manoj, Michael, more epochs, more better, right? Yes or no? What do you guys think? I mean, you're describing something that sounds really great, right? So more epochs, more better? Yes or no? Let me know, guys. What do you guys think? Who was my... Okay, Brandon, I believe that you just signed up for my data science school. Brandon, if that's you, if it's the same Brandon in the chat, thank you so much. Really appreciate it. I just got your registration here in my email, so thanks so much. Let me know if I got the right Brandon. I'm guessing here. I'm guessing by the email address. But thank you so much. Thanks so much. Really appreciate it, guys. Again, if you guys want to sign up, I'm launching August 1st. I'm looking for my founding members between now and then. But this is the type of stuff I'm going to be teaching, right? It's all real world stuff. Brandon says, yes, that was me. Thank you so much, Brandon. Really appreciate the support. Look forward to having you hear more. And if anybody else wants to join Brandon and the other, I think I've had about approaching 40 signups now. Anybody else, if you guys want to join, please feel free to do that. Really appreciate you guys. Sajad, I think it's your first time here. Welcome. Sajad says, oh, say that fast 20 times, huh? Sajad says, confusion matrix is a table to measure model performance, predicted versus true labels and classifications. Yeah. So can we use those for neural networks, Sajad? Let me know. Sajad said, more epoch is not better necessarily, since models can overfit or overdrift. Ooh. That's a good question, guys. Okay, guys. So here is an interesting question. I can't believe I didn't come up with this before, but so overfitting, Sajad is correctly identifying as a risk of neural networks. But there's a lot of ways you can improve a neural network. You can improve a neural network by more layers, more nodes, right? What is more risky for overfitting? Is it epochs or is it nodes and layers? Huh? That's a good question. You know what? That's a good interview question, actually. So think about that, guys. What do you guys think? So Sajjad is saying, hey, look, more epochs, not more better, because you could be overfitting. Let's think about that. What do you guys think? Let me know in the chat. Let me know in the chat, guys. I have some thoughts on this topic, so remind me if I don't get to it. But yeah, Sajjad, you're bringing up an interesting point there. Osama says the confusion matrix is a powerful tool used to evaluate the performance of a classification model. It shows how well your model is performing by comparing predictive labels versus actual labels. All right, I'm on board with that. That's a perfectly reasonable explanation. Yassine says the effect of adding more epochs is good to a certain degree. Overdoing it can make the model memorize the training data instead of learning the patterns, which can lead to overfitting. Okay. Okay, so you are on the same track as Sajjad. Sajjad, talking about confusion matrix, says if they classify, yes. Yep, I agree, Sajjad. Brandon says, I bet you forget in a day more than I will ever know about machine learning, but I'm working on learning all of this. Well, glad to have you here, Brandon. You're in the right spot if you want to learn, with no nonsense, no BS. I don't sell, dreams of nonsense. I only give you guys real world stuff after leading a lot of teams over the years. So thanks for being here, Brandon. I appreciate your support. So coming back to our question about overfitting and layers, Yassine says, or overfitting and epochs, I should say. Overfitting with layers and epochs. More risky for overfitting is more nodes and layers. Okay, Yassine. So think about your previous answer, though. Isn't that slightly contradictory to your previous answer? Let me know. Michael says, 5, the model becomes more capable of capturing a wider range of features in training, but may also lead to a slower model due to more computations and also may cause overfitting. So Michael's providing that answer for what is the effect of adding more nodes to our layers. Yeah. Yeah, Michael, I think you're giving a pretty good answer, but keep in mind that only your input layer relates to your features. Your middle layers, your hidden layers, can have any number of nodes that have no correlation to your features. Like if you have 10 features, and yes, you have to have 10 input nodes, but that doesn't mean like the rest of your layers also have 10. They could have 500, they could have 3, they could have 700, they could have 6. It can be whatever you want. So you're on the right track. I agree with everything you said, but don't tie it back to, well, I have to have one feature per node or one node per feature, right? It can be whatever you want. Yassine says adding more nodes can help increase model performance, but it increases the model size, making it less performant in deployment. Yep, that's that's a pretty reasonable answer. So guys, I'm kind of still fascinated by our approach to epochs and overfitting, right? And then our nodes and overfitting. So the correct answer is that we are 10 times more danger of overfitting by playing around with the nodes. That's 10 times more likely to be an overfitting. But that doesn't mean that epochs are always the answer, right? What's a different danger? What is a different risk of epoch? Let me know in the chat. There is a different risk related to epochs that we should talk about. Let me know in the chat what you think it is. It's not overfitting, okay? Is it Anna? I think it's Anna, or let me know if I'm pronouncing your name incorrectly. Anna says, always monitor training loss versus validation loss to check for overfitting. Both will overfit at some point. Both will overfit at some point. That's not necessarily true. Not every model reaches an overfit state, guys. That's not. Anna, welcome. I'm not sure. I'm not sure if it's your first time, but I'm not sure if I'm on board with that. Overfitting is not a requirement, guys. As a matter of fact, I want you to think about the other question I just asked you guys. Is there a danger to epochs? Is there a danger to epochs that you should be looking out for? Yassine says adding more nodes is more risky to overfitting than adding more epochs, but the epochs can still overfit, as I know. Um, let's put a pin in your answer, Yassine, because there's another situation that I'm thinking about that relates to epochs. I want to give the chat maybe another 30 seconds to think about it. But there are other dangers with epochs. So let's put a pin in all of that. But let me know what you guys think. Epochs are really fun and really useful, but do they have drawbacks? Do they have drawbacks? Yassine says, I think another risk is that at a certain point, more epochs won't be able to improve the model or reach its full potential. Ah, there we go. There we go. Now we're headed in the correct direction, Yassine. So guys, Yassine is headed exactly where I was thinking about this. The danger to epoch, you could argue, is the opposite of overfitting. There are plenty of situations where your epoch basically reaches the best it can do. Your model has reached the best it can do, and it's not a very good model. Like, it'll just sit there and work and not get any better, period. The weights just aren't there. The gradients are too small. You know, maybe you've smashed a couple of gradients to zero, right? The vanishing gradient problem, or whatever the case may be. So that is another danger of epochs, and that is the opposite of overfitting. You are just stuck at a state where it's not a very good model and it's not going to improve. It's just there. So Yassine, congratulations. You're definitely on the right track with that thinking. Very, very important item for all of you to kind of keep an eye on, because that can absolutely happen where you're just kind of stuck and your network's not going to improve. It's not going to get better. If you want to kind of study that or want to know more about that, you would want to look up early stopping. Most frameworks offer a tool for early stopping. Or in some cases, you can just build it yourself, right? You can just you can add a loop and say, well, if I iterate 10 times and my loss hasn't changed or my metric hasn't changed, I'm going to go, after 10 epochs, if it's still the same, then go ahead and stop, because it's probably stuck in that type of situation where more epochs is not more better, right? Michael, I'm gonna come back to your topic, but let me stay here with Yassine. Yes, I kind of see it now. Now I think we can only overfit with more epochs if our model has more nodes layers than necessary. Yeah, that's right, Yassine. So it's very common for us to be making multiple changes at the same time, right? When we're testing our neural network. So if you go ahead and modify the nodes and layers, but then you also add more epochs, then you're going to say, oh, well, the epochs led to overfitting. Well, no, not really. The epochs just gave the nodes and layers more time, more cycles, so that the nodes and layers created the overfitting, right? Yassine says, so the issue remains the number of layers and nodes. Yes, that's exactly right. But the epochs itself is probably not going to lead to overfitting. It's more that it would lead to a stuck state. It's possible that you'll say, oh, I'm going to run this for 10,000 epochs, but there is zero improvement after the first 1,000 epochs, right? Because it's just not going anywhere. Michael says, memorization of training data, I think, not being able to perform well with new data. Michael, I don't know which particular one you were, which particular question you were going after, but that is a danger of any model, right? Like, like Michael, I like what you wrote, but that's not specific to neural networks. Any model is in danger of this, right? Any model can become um, overfit to its training data, or even just data that it's seeing live, but your data set changes, right? You have data drift, and the model and your previous model you deployed is no longer valid for contemporary data, right? But that's any model. That's not that can happen in any situation, not just neural networks. Yassine says some things we can do to improve the metrics is to label the falses, the model results, so we can evaluate what kind of error is more tolerable, so we adjust based on that. Yeah, sure. Um, yeah, labeling the falses and then kind of feeding them back to the model, right? That's totally a valid way to do it. To say, hey, here's where you went wrong. I'm going to add this to my training data, and then I'm going to rerun my training cycle. There's a name for that, by the way, guys. So let's have a little bit more fun with this, because this is one where so many of these idiot influencers go wrong with this. So many. I see this. And by the way, I see corporate people making this mistake too. Yassine just said, one of the ways we can improve our model is that we can label the falses of the model results. And then we can put it back into the training and have the model adjust on that. There's a name for that. There is a name for that, guys. Think about what we just said. We're going to take the falses of the model and we're going to put it back into the training data, and we're going to rerun the training data. Yassine, I know that's not exactly what you wrote. I'm paraphrasing what Yassine wrote, but there's a name for that, guys. I'm going to give you guys 30 seconds to think about it. Put it in the chat. So many people go wrong with this. I have had arguments with people about this. Brandon is stepping up. I love it, Brandon. Stepping up and suggesting supervised learning. Ooh, so close, Brandon. It's supervised because we're labeling the answers, right? So you're right that we're relabeling things. Oh, Yassine hits it right on the head, and Brandon, you were so close. Yassine says reinforcement learning. That's exactly right, guys. It's reinforcement learning. Manoj says smoke. Yassine got it, guys. It's reinforcement learning. Don't fall for those idiots out there that say, oh, well, supervised learning is another form of learning. There's supervised, unsupervised, and reinforcement learning, right? Those are the idiots that are talking that. They always point out to those three. Wrong. Reinforcement learning can happen anytime, guys. Oh, no, it's a supervised model. I can't go to reinforcement learning. Yes, you can. Yes, you can. Feeding back errors into your training data, making that part of your gold standard data, is reinforcement learning. Oh, no, I already started as supervised learning. I don't want to have to go back to step one. No, you can do reinforcement learning anytime. You can do reinforcement learning 5 years after your model's deployed. It doesn't matter. So yeah, think about what Yassine said. That's exactly what reinforcement learning is. Like, it boggles my mind that people have entire tutorials about reinforcement learning. That is trash, because reinforcement learning isn't like a big thing. It's just a way you grow a model. And you can do it on any model at any time. Just take the results from the model, human validate it, make sure that the humans give the right answer. Take that, put it back into your training data, and retrain your model. Congratulations, you've done reinforcement learning. That's all it is, guys. So many people go wrong on that. Starry Vibes, good to see you. How are you? Starry Vibes says, hi, sir. Hope you're doing good. We're doing really well, Starry Vibes. Hope the same for you. Let us know how everything's going in your part of the world, but good to see you here. Yassine says, to improve the metrics, we can put a dollar cost or business case and adjust to have the best expected value. Yep. Yassine is right about that. The right model isn't always the one with 100% accuracy, guys. The right model is the one that fits your business use case, and sometimes you're going to want a skewed model. You're going to have situations where you're going to say, hey, I'm okay with false positives. False positives are okay. Give me the model that's optimized for the most, well, give me the highest accuracy model you can, and if it has a lot of false positives, go ahead, I'm fine with that. There's going to be times when you do that. I know. In school, they always asked you for the highest accuracy with the lowest false positives and the lowest false negatives. That's not the real world. In the real world, there might be situations where you can say, hey, I'm 100% okay with false positives, but don't you dare give me any false negatives. Right? There's plenty of situations like that, or the reverse, right? You'll be in situations where false negatives are 100% okay, but don't even generate one false positive. Yeah. So yeah, Yassine's right on there, right? You adjust by the business case you're trying to solve. Okay, guys, so thanks so much for that. I think we spent enough time on this chart. Let's go ahead and spend some time on the code, right? So again, before we leave this, if any of these questions are too tough for you, or you're lost or whatever, you don't know what's going on, you might not be ready for a data scientist interview. Okay? So let me bring up my VS Code. All right, we got our good friend VS Code. And if you guys were here, you remember this piece of code. Forgot how to close out this window. Oh, the mini map. All right. So let me know if it's big enough on your screen. I think it should be big enough. If you guys remember, this is code that AI wrote for us, because remember, we are going to be the data scientists of the future that's heavily aided by AI. So we did not start this. We did not start this ourselves. We asked AI to do it. We have some helper functions, which are basically kind of like our activation functions that we talked about. We have our network parameters. So in the chat, what are we doing here? What can you tell me about our neural network just from looking at these parameters? Because if you're trained in neural networks, your eye should be able to tell you what you're doing here. Right? By looking at something like this, you should be able to tell, is this a big neural network? Is this a small one? Is it going to take a long time to run, a short time to run? What are we doing here? What can you guys tell me? Just give me your plain English summary of what's going on here according to the network parameters. What's happening here? And then if you want, tell me about this down here also. So I'm looking in Osama's general direction because we did have a brief conversation about deep data, right? Look at this, guys. This is our training data. This is the training data for our neural network. Is this deep data? Give me a 1 in the chat if this is deep data. Give me a 0 if it's not deep data. A 1 if you think this is deep data, and a 0 if you think it's not deep data. Okay, so Yassine says it's a small neural network training so many times. Okay, how many times, Yassine? Michael says agree with Yassine. Okay, cool. Hattie, I think it's your first time. So Hattie, welcome. Hattie over on Instagram. Hattie says it's 2 inputs, 2 hidden layers, a long training of 60,000 epochs, and the learning rate is high. You had me at 2 inputs, you lost me at learning rate is high. What's a high learning rate, guys? What is high? What is low? You can't say that, right? We haven't run any experiments. So you can't say that. Like, we don't have a frame of reference to say high or low, right? Different networks or different problems will need different learning rates. So you can't say high. You can say it's 0.5, but that's basically all you can do, right? Yassine says, pardon me for the off-subject data. What's deep data? So Yassine, good question. So we're talking about deep data would being for something you would use for deep learning or something that would have, a very, very large number of rows, right? Something where you have a lot of data accessible to you, right? And remember, I'm bringing this up because previously there was a statement in the chat about how you needed deep data for neural networks. And I think that's a little bit of a logical fallacy. Neural networks doing well on deep data does not mean that neural networks require data, right? It's like one of those like logic puzzles, right? Yassine says it's running for 60,000 epochs, which is true. Thank you for that. So the deep data question, Starry Vibes is 0. Michael says 0. Osama says 0. Okay, so Osama, you can see where I'm going with this, right? We did a lot of work on this little neural network with 4 inputs in our samples, right? Starry Vibes says, I think it's XOR data. Yeah, Starry Vibes, it is. But that's just like toy data we're using as for the example. The point is, it's only 4 rows. Is that deep data? Does that mean that we shouldn't be using a neural network for this? Right? Starry Vibes, coming back to our previous question. Starry Vibes, why do you let me down so bad? Guys, it's the people that you love that hurt you the most. Starry Vibe says, I think he compared it to the usual LR. What's the usual LR? Guys, don't do that. The usual LR, that's bias. Congratulations, we have now seen our first example of researcher bias. That's researcher bias. Because what are you saying there? Well, the last model I worked on didn't use 0.5. That's all you're saying, right? Oh, I've never seen 0.5 before. That can't be the answer. Don't do that to yourselves, guys. Starry Vibes, why do you hurt me? Guys, it can be whatever you want it to be. You don't know the answer. That's the whole point of being a researcher. That's why you run experiments. Now, is it likely to stay 0.5? No, but I'm going to try it. Why? Because it's a valid experiment, and I should be trying all valid experiments. Right? So don't say that, guys. The usual learning rate, or these are my standard parameters, this is the model I like, that's all researcher bias. We can't allow ourselves to do that, right? Hattie says, yes, I got you, given the network is simple and we haven't done any training yet. Yeah, it's not about the simplicity of the network, it's about that we haven't done any training yet, right? We don't know. You don't know what the answer is. We just don't, right? This is us coming into a new problem with a clear mind, a lack of bias, and just saying, hey, let's try it. Because that's what we do as data scientists, right? Anything else? That's just researcher bias, right? Osama says, I see, sir, thank you. Yeah, Osama, so deep data is not a requirement for neural networks. It does very well on deep data. but there's no requirement. Sansi over on Twitch says hello. Well, hello to you too, Sansi. Welcome. Sansi, we are going over neural networks, so you're welcome to hang out, contribute as much as you'd like, and just glad to have you here. I think it's your first time joining us, so welcome. All right, guys. So yeah, so coming back to our base question, right? So we know we're going to have two input layers. Two input nodes. We're going to have two hidden nodes in our layer, and we're going to have one output node. And that's because, we're just getting to like a yes, no type of answer, right? We know that our learning rate to start off is going to be 0.5, and we're going to run for 60,000 epochs as, which is a lot of epochs, as Yassine correctly identified. Sansi says, I have a question which is sadly not related to neural networks. May I ask? Go ahead and put it in the chat, Sansi. I usually don't take too many off-topic questions, but who knows? Maybe you catch me on a good Sunday. Go ahead and put it in the chat, and we'll take a look. Okay, so here's one of the questions that nobody wanted to take on. One of my questions in my review is, how did we assign initial weights to our neural network? Remember, as we've discussed before, right? A neural network is a lot of modeling, right? Is here's my input, here's the weight I want to assign to the input, put those two together, put those in an activation function, and continue processing in some way, right? Activation functions require an input, right? So how did we assign the initial weights to our neural network? So if we go back to our code, here it is, right? So Yassine says randomly. Is he right? Let me know if you agree with Yassine or if you want to give a different answer. And let me go look at my Twitch. There's an AutoMod message on Twitch. Give me just a second here, guys. Oh gosh. Sansi, the AutoMod held your message because you asked a question. Sansi, I can't help you with that question. This is a data science channel, my guy. I have no idea how to solve that problem. Yeah, the AutoMod held it for whatever reason. But yeah, Sansi, when you said your question was not related to neural networks, I thought you were still asking a data science question, but man, I do not have any idea what you're talking about. Yeah, good luck with that. All right, guys, so let's stay on topic here. Is Yassine right? How did we assign our weights to our model? How did we do that? And if you want to think about this a little further, what is the challenge there? Starry Vibes says we can specify values. Okay, tell me more, Starry Vibes. Because Yassine was right. We did it randomly. Do we have to do it randomly? Is Starry Vibes correct? We can specify values? What do you guys think? Osama says, I agree with Yassine. Okay. Fabrizio says, hi. Fabrizio, welcome back. How are you? Good to see you again, my friend. Fabrizio, right now we're talking about our neural network code. And we are looking at line 27. How are we assigning these weights? And also, take a look at this, guys. This loop is going through our number of hidden nodes, right? We already agreed that our network has 2 hidden nodes. So I think it was Denelson previously had talked about how more nodes means our file gets bigger, our neural network gets bigger. And he's right. And this is where that happens. Because now in this list of weights, in this collection of weights, this list grows according to the number of nodes. And if the neural network is our collection of weights, then this is just going to be bigger and bigger and bigger, right? And if it's bigger and bigger and bigger, that's a bigger file, more calculations to do, so on and so forth, right? So right here in this line, we are essentially determining how big our network file is going to be in the performance, right? Hattie says, we did random initialization, right? We did, Hattie. This is showing random initialization. Yassine says, yes, we can do it another way. Okay, what way, guys? If you want to get really fancy with this, how do you do it in NLP? How do you do this in NLP or some other network that you know about, right? Because aren't there dangers to starting with random initializations? Isn't it dangerous to start like that? What do you guys think? Fabrizio says you can send a random seed initially and adjust learning rate to take short steps so it doesn't jump too much and converge. Yeah, that's possible, right? But Fabrizio, isn't there a danger in starting randomly? You know, we're going to go over it again today, but think about the last time we met 2 weeks ago. Didn't we see some differences? What were some of those differences that we saw? And how are we able to tie them back to this one line? Because think about that. If your weights are random, then can you run this training cycle multiple times and expect to get the same results? Think about that. Can you? I don't know. Let me know, guys. What do you guys think? And just to have some fun with it, let's do something here. Oh, what did I just... Oh, okay. This will be fun. Fabrizio says, isn't the feed forward supposed to be randomly and then improve during back propagation? Is that a requirement? Is that some sort of law? Yassine says the training cycles will have different results for the same parameters. Each one have different starting point. That's exactly right. You can't rely on equal results, right? If you have random starting weights, right? Hattie says, yes, it will be dangerous as weights might vanish or explode, but that can happen anytime, Hattie, right? Starry Vibe says, no, we will always get different results. That's exactly right. Exactly right. Fabrizio says, if you want, you can try doing different configurations of layers during grid search. and look for a best initial point based on different layers, but I don't know if that works. That'll work for getting you to a model, Fabrizio, but that doesn't necessarily address the randomness problem. You're describing an effective workaround to help you with that. But remember, as we've already discussed, you might not always be able to do a bigger model, right? You might have a limitation where you're going to be deployed on a mobile app or some very specific, like embedded hardware or something. And they're gonna tell you, yeah, you can you can use a neural network for that, but it has to be less than 500 kilobytes or something, right? I think for NLP, we should be careful, not making them decimals nor big numbers. Yassine says, never done it, just a guess. Starry Vibe says, but if we start with the same values, we will get the same results all the time. Yeah, that's right, Starry Vibes. So guys, Yassine is answering me from earlier when I asked you, how do they do this in NLP? Because remember, in NLP, you're going to have a lot of inputs, right? Like there are no, well, you're very unlikely to have an NLP model with only 2 inputs, right? You usually have hundreds, if not thousands, if not tens of thousands of inputs, right? Like you could argue that an NLP model with hundreds of inputs is like a small model, right? Tiny model even. So how would you do that? Like if you did a NLP model with a couple thousand inputs and you did random weights, like it would take you forever to converge from random weights to something that you can use, right? Like it would literally be just like a long time and a massive model to do that, right? So why do embedding files exist in NLP? Hmm? Why are vectors and distances so important in NLP? If you guys want to Google that, go ahead and Google that. But that's kind of why those things exist, right? Okay, so Yassine just got it. Yassine says, "Oh yes, yeah, right." So you guys can start seeing how all of these other concepts you've heard about kind of tie back to neural networks. What's an embeddings file? An embeddings file is an advanced initial weights file that you can use in your NLP problems because you kind of need that. And because it kind of fits in NLP, right? Same thing with some of like these vector concepts you hear about in NLP, right? Some words and n-grams are going to be closer to other words and n-grams. You can pre-establish that. You can start randomly, but it'll take you forever to converge, right? So why not use an embeddings file, right? Now, take this another step further. I just told you that we're going to use something like an embeddings file to help you against this randomness. Fabrizio says, oh, so you can choose which features are more relevant. Yeah, that's right, Fabrizio. Essentially, yes. Right? Why wouldn't you use a random weights file? Because you know that some features are going to be more relevant than others. So you know that you want to start with a particular weight on some features and a little lower or a little higher weight on others. So yeah, I mean that's a layman's explanation for it. But let me take you one step further, guys. And it's funny that this is now becoming more of an NLP discussion, but that's okay. Yassine says we can do some weights from another model. Yes, you can, Yassine. But hold on a second. I'm about to make all of your minds explode, right? Okay, so I just told you that using something like an embeddings file helps you with your weights. And I think you all understand how your weights tie back to your inputs, right? And in NLP, our inputs are language, right? What happens when I change my language? Hmm? What happens when I'm still doing an NLP problem, but now I'm going from English to German? What happens? Let me know in the chat. Does my embeddings file and my weights file still hold? Yes or no? It's still language. It's still text. But I've gone from English to German. What happens? What do you guys think? Let me know in the chat, guys. What happens when you do that? We can still use the same weight file, right? Oh, Fabrizio. Why do you disappoint me so bad, Fabrizio? German to English translations to embedding. Wrong. Next answer. Yassine says, my guess is that we need something to relate to the English embeddings. Wrong. Next answer. 910Q says an AI app like you used for your parents. Thanks. 910Q, I'm sorry. I'm not sure if that's an answer for our current question. But thanks for being here, 910. 910, if I can help you in some way, let me know in the chat, okay? But yeah, 910 is referring to the insurance fight I did with AI for my parents, as many of you know here. I was on the news this past week for that. I've been getting a lot of new followers on my Instagram and on my YouTube because of that. Yesterday I published my DIY video for people that want to use AI. So if you're here because of that video, thank you so much. I'm happy to help you. Feel free to put it in the chat or send me a message, okay? Shawshank says, this is gold. Thanks so much, Shawshank. Thanks for being here. I think it's your first time, so welcome. There you go. There you go. So Fabrizio says German to an embedding that follows the German language structure. Yeah, that's the answer, guys. You don't do a translation. You go find a German embedding file. Right? So guys, remember, I've been giving you guys these hints. Do you guys remember, like, when last year when we on many streams when we were talking about AI and ChatGPT? Like, I know that I have a lot of followers around the world, and I've told you guys there is opportunities for you guys to come up with your own regional versions of LLMs. Why? Because NLP is not good if it's not English. ChatGPT is not great if you don't type it in English. So go out there and work on the Arabic version of LLMs. Go out there and work on the Darija version. Go out there and work on an Italian version or whatever you guys want. So that's what you would do, right? You don't do the English translation. Are you crazy? You'd come up with your own embedding file for those languages. NLP has a ton of opportunities for that. And this is basically right here the problem that you're solving. You're solving that you wouldn't have to rely on random weights, right? Like, this is why those opportunities exist, guys. I've been telling you guys this since last year at least, right? Like, if you want to do something in AI, go out and do like an AI version in your local language. There's huge opportunities all around the world for that, right? So think about that, guys. All right, let's put a finer point on this. Let's go and run this code. And as you guys saw, we're going to take a look at our starting weights and our hidden weight and our finishing weights. Okay. So let's go ahead and go to our terminal. I don't think I've activated my conda, so let me activate my environment. There it is. Python, NN1. And you know what? I want to dial this back. I want to dial this back to 10,000 epoch, which is what we originally had from the LLM. Okay. So what do you guys think? Look at this. Here's our starting weights, and here's our finishing weights. Is this a good model? Well, first of all, I jumped ahead. Sorry about that. Let's look at our loss, and let's look at this, because this is what this is telling us what it learned, right? One, is this a good model? What do you guys think about these results? What do you guys think about this loss? And then look at your starting weights, and then look at your finishing weights. Look how different those are. What do you guys think? So give me your impressions. What do we think about this model? Yassine says not a good model. Okay, why? Give me your rationale, Yassine. Michael says not good. Okay, good. I think you guys are on the right track. But give me your rationale. What's jumping out at you? What's making you say it's not a good model? And just so we're clear, some of you maybe don't remember it from last time. This is our input, right? It's an XOR table. So this here represents our ideal output, right? Because it's our training data, right? So it's a simple XOR. This isn't data science. This is Boolean logic. So a 0, 0 equals a 0, a 0, 1 is a 1, 1, 0 is a 1, and a 1, 1 is a 0, right? So in other words, an XOR table is looking for one or the other to be true, but not both. They can't both be false. They can't both be true. It has to be one or the other to give you that XOR result, right? So what do you guys think? Is this a good model? Yassine says results are not decisive for two different classes. It's giving very close probability scores. Results are not decisive for two different classes. It's giving very close probability scores. Yeah, sure. That's reasonable. Yassine says the last two. Yeah, right. These two. So Yassine, I think I'm going to interpret this correctly. But Yassine is saying, hey, these two are completely different classes, right? This should be a 1, this should be a 0. But the model basically can't distinguish between those two classes, right? So yeah. Fabrizio says, is it being tested on the test data? And also I saw the loss, but not the accuracy of the model. Fabrizio, do we need the accuracy? Do you have to have accuracy? Does every model have accuracy? Spoiler alert, it does not. Or you do not need it. Michael says comparing 0 and 1 and 1, 0 too far apart. Yeah, Michael, good catch. And we talked about this last time, right, guys? To me, this is what jumped out. We know that 0, 1, 1, 0 should have the same output. They resolve to the same class, right? They resolve to both 1, right? So why is it here 0.972 and why is it here 0.5? That's a model that's not learning. Right? If it's the same categorical output, why are they so far apart? So that's what Michael's pointing out there, and he's right. That's bad, right? Like, why is it recognizing the category, the class okay here, but not okay here, even though it's the same class? Um, Sudip, welcome. Glad to see you. I think it's your first time. Sudip says, "Can I understand this stream without prior experience in machine learning?" Um, it's going to be a little bit harder, Sudip, but I'm glad you're here. You're welcome to hang out. Maybe you don't know everything, but this is where learning starts, right? You got to start somewhere, right? So hang out and see what you can pick up. And if you have questions, let us know. Okay. But yeah, so I think Michael and Yassine are hitting on some things that really say this is a terrible model. And also, nobody really talked about the loss, but what do you think about the loss? For loss is more bigger, more better, or less bigger, more better? What's better in the loss, a big number or a small number? Let me know in the chat. Give me a 1 in the chat if you think a big number is better. Give me a 0 in the chat if you think a lower number is better. What do you guys think? How's our loss value here? Sudip says, I am a high school graduate and currently learning EDA. Thank you for your stream and time. Yeah, you're welcome, Sudip. Welcome to hang out. You're on the right track if you're studying EDA in high school. You got plenty of time to learn ahead of you. So welcome. The loss is 1/4. So for each 4 tries, 1 is wrong. That is way too much. Okay. So Fabrizio, do we want a bigger number or a lower number? Give me a 1 in the chat if you want your loss to be high. Give me a 0 in the chat if you want your loss to be low. Okay, so Starry Vibes is voting low. Anybody else? Anybody else want to vote? What are we looking for in our loss? A high number or a low number? Fabrizio kind of gave us a clue, right? Initial weights are far from finishing weights, taking too long to reach desired ones. The variability indicates a bad starting point. Yep. Michael's also voting 0. Yassine says a low loss is better. Yep. Fabrizio says 0.05 is good if you are testing hypothesis testing, which is more, I think you meant rigorous in academics, but yes, 0 is better. Okay. Starry Vibe says there is a big difference between the input weight and the output weight. Yeah, guys, look at that. Look at our starting weights versus our ending weights. Huge difference, right? Huge difference. And as Yassine says, look at our loss variability. On the first pass, before any weights were adjusted, look how terrible the loss did. Right? That's a terrible loss rate. Now, if you're starting from a terrible loss rate and you're limited on time or you're limited on what you can do with your neural network, isn't it possible that you'd never converge to an answer? Yeah, right? It's very possible. It's very possible that your loss isn't going to drop. And look at this. It really didn't drop a whole lot after the fourth epoch, right? It only went from 25.5 to 25.1 in like 6 epochs. Is that great? Probably not. Does that give us a hope that it's headed in a good direction, that this model's going to converge? Probably not. Right? I mean, we can try it, don't get me wrong, we should still experiment, but on a probability basis, this is low probability to improve, right? So I hope you guys are starting to see where these random weights can sometimes be detrimental. Right? So keep that in mind, guys. Very important. We should always be tracking kind of where our weights are, how our loss is going. Are we headed to like a converging direction? How does our confusion matrix look, right? Like are we encouraged by this? Like, no, this is terrible. And I shouldn't say confusion matrix. These are just our results, right? Our sample results. Like, are we happy with this? No, this is terrible, right? Okay. So let's go back to our code. Let's make some adjustments. I want to adjust here. What did I just do, guys? Look at the adjustment I made. What is the expected result here, guys? Give me all the possible results that are going to happen from me switching our hidden nodes from 2 to 200. What do you guys think? Write out a list of the expected results. Right? Because remember, this is kind of us applying the scientific method within the scientific method, right? What's your hypothesis of what I just did? What's going to happen here? What do you guys think? There's multiple things that could happen here, right? What are they? Fabrizio says, it depends. It can maybe move from local minima and go into global minima if the other parameters are already optimized. Maybe, Fabrizio, but it's not guaranteed to do that, right? And the concept of early stopping exists because time is a factor, right? You may be under a deadline. So, yeah, it could converge, but if that's only a 5% probability of converging, wouldn't you rather just stop and go try another experiment instead? Right? That's probably a better use of your time, right? Yassine is commenting on the change I made. Better results, slower performance. Yep. Those are reasonable expectations. Is it Muff over on Instagram? Welcome. I think it's your first time. They say it could possibly overfit. Yep. Adding more nodes definitely increases our probability of an overfit. That's absolutely true. Anybody else? There's one more thing you guys haven't hit on. What's going to happen here, guys? Denelson says, since we have more layers, we could have a problem with the Granishing gradient, and now the model will be slower. So no, Denelson, these are not layers, these are the nodes. So we haven't changed the architecture. There's still going to be only one hidden layer, but we've gone from 2 nodes to 200 nodes. So what's going to happen here, guys? One last thing that we need to hit upon, right? You guys have done pretty good so far. We increased our probability of an overfit. We increased our probability of getting better results, and we're almost certainly going to get slower performance, right? You guys have come up with that, but there's one more thing. One more thing that could happen here, guys. What's going to happen to our hidden weights? More weights, that's right. Yassine says more weights starting with 200 random weights, that's right. So now our neural network has gotten bigger, right? There may be times when you say, well, we can't have that because it's going to make our file too big for the hardware we have, right? But we've 100x the size of our file now. We're not going to be tracking 2 weights, we're going to be tracking 200 weights. We 100x our weight size, right? Fabrizio says it will increase the time it takes to train the hidden weights. You can suffer multicollinearity, and it will prefer to regulate the features with lasso or elastic net. Maybe. Maybe. Let's stay focused on a high level, and it will increase the time. It will definitely do that, right? We know that we are now going to take more time to process. So let's run this. So that was interesting. What happened here, guys? What's all this? What's all this junk? Why did my screen just fill up with junk? What do you guys think? Why is my screen like this all of a sudden? And then, what's all this junk down here? And then, let's also look here. What do you guys think here? Hmm. Okay, guys. Tell me what you think about this. What do you guys think there? Yassine says the 200 initial weights. Starry Vibe says weights. Yeah, that's exactly right. Before the weights were easy to read. There were only 2 of them, right? But now we got to assign 200 weights for each of our nodes. All of a sudden, that file is bigger, right? There's a lot more to track, a lot more to calculate, right? All right, so what about the results? What do you guys think about the results? I want you to look at everything the output gave us. Are you happy with this model? Are we ready to deploy? Brandon says, is this overfit now? Maybe. Maybe you're on the right track, Brandon. Give me a rationale. Give me a rationale, guys. Starry Vibe says it's still wrong with one class. Is she right? Is Starry Vibes right? Is not overfit until you test with test data. But we are testing with test data, right? That's what this is down here. Yassine says the model is bad, loss is not good, and not improving over time, and results are very bad. Are they very bad, though? They look better than our previous model, don't they? Are these not better than our previous model? Michael says the loss is too high. Yeah, that's a valid observation. So Brandon said, is this overfit now? I want you to think about Michael's answer. Brandon says nearly perfect, 1 for 3 features and 1 non-related. Brandon, you're on the right track, but remember what these answers should be. In an XOR table, a 0, 0 is a 0 and a 1, 1 is also a 0. So a 1 is not necessarily a good score. It depends on the output, right? Yassine says, well, to be honest, it's only missing 1 case. That's one problem, Yassine. Are there other problems? So let's combine everything that we've talked about. There is clearly a problem in this case. And I agree with Michael that the loss is too high. And Brandon was on the right track. I would call this an overfit model. It's overfit for these classes, which in turn is having a negative effect on the 4th class. But this is basically a horrible model, even though some of these numbers, without any other context, look okay. But this is, to me, is a model that hasn't learned. It hasn't learned because these are overfit cases. And that overfitting is causing this down here. Do you guys see that? If not, let me know. But this model is 100% a problem. And actually, now that I look at it again, I think well, never mind. Fabrizio says, but the overfitting happened when you can capture too well the model that you cannot use to generalize, right? That's why I ask about the test data. I don't get, where is the test experiment? The test experiment is down here. Oops, sorry. What did I just do? The test experiment is down here, Fabrizio. This is where the code fits in the inputs into the model and tells us what the output would be. And this is the output from the model. So that's the test case. Yassine says, wait, how can it be overfit if the case was already existing in the training data? Because it learned it so many other times, right? I mean, the case it's mistaking was also in the training data, but this wasn't in the training data. A 1-1 in the training data is 0, Yassine. So let me go make another modification. What happens if I do this? I think we all know that that's going to do more epochs, right? Yassine says it will be better. That's the goal, right? So guys, what are we seeing right now? What is happening at this very moment? Dari Vibe says we can expect better results. Okay. Do you guys see what's happening? What is happening in front of our very eyes? Yassine says no improvement. Yeah. But what else is happening, Yassine? The dream for better results has vanished. Okay. But what else is happening? Something very obvious. What else happened, guys? Fabrizio says it's stupid. Yes. Loss is stable. Yes. Still not good. Not improving. Yes. Yassine says a local minima. Yes. But what else happened, guys? There's something else. What else happened? What else happened? What else did we just observe? Something else just happened. That's exactly right. It took a long time. That took a long time. What the heck? Right? We were getting results in a flash before. Now we were sitting there watching each 1,000 or 2,000 epoch, each 1,000 epoch go up. That took a long time. Why is that important? Because this is where project planning comes into place. This is why you don't run a couple of experiments and tell your boss, oh, I'll have that neural network for you in 2 days. No, some training cycles are going to take a long time. Right? This is why project planning is so tricky in data science. Some experiments are going to happen in a flash, some experiments are going to take you 3 days to run. That took a long time just now. Like, comparatively speaking to the other experiments we ran, that took like 10 times longer, maybe more. Right? Never, ever, ever tell somebody you're going to have results in a flash. Because you don't know how long those experiments are going to take. That's just the nature of data science. Right? And again, these are those things that the idiot influencers don't know, right? They show you in these tutorials, oh, look how quick this runs. Well, that's not real life data science. Right? Denelson says it completely disregards the 3 other cases. No, I wouldn't say that, Denelson. What makes you say that? Because really, you could argue it's only wrong in one case, right? This case is horribly wrong. Now, I'm not saying this is a good model, obviously. But if you were just to take it just by the results, you would say, hey, this is okay, this is okay, this is okay, this is terrible. So help me understand your rationale, Denelson. Because I don't think it disregarded the other 3. If anything, it's one of them that's bad. Lawman, so good to see you, my friend. Our good friend from Nepal, I believe. So how you doing, Lawman? Good to see you. Lawman says the learning rate is small. We haven't adjusted the learning rate yet, Lawman. We haven't adjusted the learning rate. Fabrizio says, I have a question for you, Dennis. It's a little different, but once you build the model, is it convenient to store results in the database? You can retrieve from there instead of run the whole net. You can. It depends on the problem and the framework that you're working in and things along those lines. But yeah, let's use what Fabrizio says, because this is another part that I kind of wanted to touch upon. We know that these are our finishing weights, right? What could we be doing with these finishing weights? Anybody have any ideas? Look at all this data. And we know that the finishing weights are completely different than the initial weights, right? Because we saw that in the previous model. What could we be doing with all of this? I want you to think about Fabrizio's comment, and then I want you to think about this data here. What could we be doing with this? Anybody want to take a guess? I can't believe we're coming up on 2 hours. You guys are crazy. What could we be doing with this data? Yassine says, put them as initial weights for another training cycle, but I think no, we shouldn't. Yassine, you had me at initial weights for another cycle, and you lost me at shouldn't. Starry Vibe says we can use it like an input. Okay, you know what, Starry Vibes, you and I can be friends again, because before you hurt my feelings, but now we can be friends again. Yeah, we can use it, right? We can use this data. Why have random weights? We can now use these as our initial weights, right? They may not be very good because we know that we're kind of stuck in a local minima, which is correct. But why not reuse these weight files? And kind of building on Fabrizio's earlier question, you could be saving these, right? You could be saving these in some sort of database or some sort of archive structure. Now, personally, I don't always do that. What I do create is every time I run an experiment, I will output it to a log, and I will output the parameters that I'm using, and then I'll save my results. Just like a simple log, like a simple CSV file. And that way, if I ever need to recreate something, I can always go back and say, oh, wait, let me go run this experiment with these inputs, right? Like I have a history of what I've done. And then that also helps you because when you do reach a finished model, you can say, yes, this is my finished model. And by the way, I ran 700 experiments to get here, right? And that's the stuff you share with your stakeholders, right? So we can be doing that. Yassine says it's just as increasing epochs as we see the loss. It's not improving over epochs, but we can add more epochs, right, Yassine? And wouldn't this give us a different starting point than initial weights did? It would, right? Michael says use it as data for retraining. Michael, you're so close. Not to nitpick, but we're not going to use it as data. We're going to use it as weights for retraining. There is a difference between data and weights, guys. In this case, our data never changes. And in most cases you have going forward for training cycles, your data never changes. But your weights can change. So Michael, I agree with you if you had written it as use it as weights for retraining, because we can definitely be doing that. We could be saving these weights and say, hey, don't use random, use this instead. Totally valid approach. Nice. How do you insert that on the model initial weights? I never did that, but sounds interesting. Okay. So guys, how would you do that? You know what? I won't open that up to chat. That's probably too complex of an answer. I probably wouldn't expect many of you to get that answer. But Fabrizio, the answer is that remember that right now we're working with raw Python code. We haven't gone to a framework. Most frameworks have built-in functions to help you save the state of your models. So the answer is that you'll be using whatever the framework supports, right? But for something like this, it's a pickle file. Take this list, right? Because we know that this weight is a list. It's a list collection. Save it as a pickle file. And that's it. Right? Save it as a pickle file. And now, when we go back to our code, and we go back to line 27, this file, we would say, hey, hidden weights, instead of going from a random input, go get the weights from this pickle file. That's it. Doesn't have to be complex. Just save it as a pickle file. Nothing more complex than that. And you're just changing the initialization of hidden weights, right? Because here, hidden weights is initialized randomly. Go initialize it and go initialize it. Go initialize it from your pickle file. No need to get fancy. It gets easy. So Yassine says, for this case, adding more epochs did not help improving for so much time. So why would we favorite them unless we change something to help us get out of the local minima? We could just rerun it again, Yassine. We can just rerun it again with random inputs. Denelson says, since we are using these weights for the new cycle, will we have it focus on the second output to help with overfitting? No, Denelson, you don't want to do that. You want to kind of just let it learn on its own, right? But look, I mean, to Yassine's point, we can save these. That doesn't mean that these are the ideal ones to save, right? But look, if we're not happy with this, guess what? Here, we just rerun it, right? Just start all over. We know that they're going to be random weights, so we know that there's going to be likely to be different results on every run, right? So why not just rerun it? Like that's valid, right? It's also possible that we can adjust the nodes. Maybe 200 nodes is a step too far. or only 2 inputs, right? Because it is only a 2-input model. Maybe that's a step too far. That's another thing to consider. And would 200 node would less than 200 nodes help us with our performance problem? Yeah, it would. Because now you're not performing 200 calculations during every epoch. Or a permutation of 200 calculations for every epoch, right? So let's see where we end up here. We're almost finished. What do you guys think here? Similar results, right? We still have one class that's horribly failing. So that's okay, right? We're data scientists. We've learned that that wasn't so great. So we come back here and we say, hey, let's adjust things. Right? We've learned, right? We ran experiments. They weren't the desired results. Well, let's build on that. What else can we be adjusting here? What else can we be adjusting here? Anybody else? Look at the code I have up on the screen. What else can we be adjusting? Okay. Yassine says learning rate. All right. I agree with that. So here's the challenge. I want you to explain to me what is a learning rate, but talk to me like I'm the CEO of a company. Don't be getting all technical on me now, because then I'll stop you and I'll never talk to you again, right? What's a learning rate? Denelson says learning rate. Fabrizio says learning rate. Starry Vibe says learning rate. Okay. So talk to me, guys. Don't be the math nerd. Don't be the data science nerd. I'm the CEO of a company. The second you get technical on me, I hang up the phone on you, right? So what's a learning rate? Why are you recommending this? Why are you taking up my GPU time, spending my money, telling me I got to adjust the learning rate? Why? Is it? We're gonna have to call you more. Sorry, I see you over on Instagram. I don't know your first name. Is it Manrun? We'll just call you more. More says number of epochs. Yeah, maybe. So more, thanks for being here. I think it's your first time. Thanks for being here over on Instagram. Number of epochs is not a bad idea, but I think the learning rate's the right track, right? But what's the learning rate, guys? Tell me what a learning rate is. Fabrizio says a small learning rate helps take small and precise steps and not running quickly on the wrong track. But what is it? Starry Vibe says it's speed that the model converges. Okay. Okay, Starry Vibes. I might need more than that, but at least you didn't get technical on me, right? But give me the CEO explanation of a learning rate, guys. You guys are close. Yassine says, let's say you're trying to reach a location based on my guidance. The learning rate is how big the steps you are taking towards a destination. If you are taking small steps, it can take you a long time to get there. If you use big steps, you can miss the destination. Okay, cool. Yeah. Really good explanation there, Yassine. Yeah. Osama making a powerful return back to the chat says, learning rate is like the pace or speed at which a machine learning model learns from data. Okay. Okay. All right, reasonable explanations. So learning rate, more bigger, more better, or less bigger, more better? What do you guys think? Lesser, right? Because if we use Yassine's example, if we're guiding somebody, we want them to go slow, right? Because otherwise they'll miss a turn, right? So why don't we do that? Oh boy. Oh boy. It's getting good now. Look at that loss, guys. Look at that loss. Oh boy. Now I'm excited. Ooh, we might reach 3 zeros here. I think we're going to hit 3 zeros. What do you guys think? Are we going faster or slower? Moore says, consider it as experimenting with numbers using the past data. More, I'm kind of on board with it, but isn't that all experiments? That's not just learning rate though, right? That's all experiments. Moore says less is better. Yeah, that's right. And we hit 3 zeros, guys, which by the way is not common. We hit 3 zeros. And we have about 10,000 more epochs to go. So what do you guys think? Are we running slower or faster here? What's your sense here? Okay. Now give me your analysis. Look at everything here. What do you guys think? Look at all that. Computation-wise, we are going the same speed. As for the race toward the minimum, we are going slower, but more carefully towards it. How can you tell me that we're going the same speed, but we're also going slower, Yassine? You confused the room of executives right now when you said that. You lost the room, Yassine. Starry Vibe says, better model. Do you agree? Do you guys agree with Starry Vibes? Fabrizio says, learning rate is the hyperparameter that multiplies the... Oh, Fabrizio, you already lost me, dude. The CEO hung up 3 seconds ago. It's got to be plain English, right? Yassine says, for executives, we are going faster. Are we going faster? Michael says, way better model, but it was slow. Yeah. Yeah, guys, wasn't there like a significant difference there? It was a lot slower. Same number of epochs, but definitely slower. Starry Vibe says, I think it's faster because the problem in the previous model missed the minimal global. You can miss the minima, but still be slower in getting there. Right? Starry Vibes, that's not mutually exclusive. In the previous model, we were slower to an overall answer because we never left the minima. You could say that. But I think that on a processing basis, we were definitely slower. Right? We missed the minima because we were more precise in the number of in the length of steps we took. You know, going with Yassine's example about if I'm guiding somebody, I want them to take smaller steps so that they don't miss a turn, right? But that's going to be slower. I mean, I still kind of agree with Michael here that it felt definitely slower, even though it was the same number of epochs. Yes, the slower, the more precise from Moore. Yeah, Moore, I think you're right. Okay, Moore, I think you switched over to YouTube. Thank you, Moore. I think you were our person on Instagram before. Thank you. Manoj says it controls the time of training the model. Yeah, but Manoj, is it slower or faster? Yassine says, I mean, for executives, to them we are going faster. First time it took us like 20 seconds with no improvements. Here we got a good loss, and the first time of 3,000 epochs in like 3 seconds. Yassine, that took a lot longer than 3 seconds, my friend, for the overall run. Remember, I'm talking about the overall run, not just getting out of that initial minima, right? Okay, so Starry Vibes was proposing that this is a better model. Do you agree? If so, why or why not? Or Starry Vibes, why do you say this is a better model? And also, coming back to our previous discussion, is this a weights file or a weights collection that you'd want to save? Do you want to save these weights? What do you guys think? Moore says yes. Yes, I believe you were agreeing with Starry Vibes. Yassine says yes, I want to save them. Why, Yassine? What's your assessment of the model here? What do you guys think? Yassine says it's a good model and results are good for all cases. Yeah, yeah. We have a pretty good loss. We actually have an excellent loss. You rarely get to 3 zeros in the real world, right? I mean, that's why I said that, because 3 zeros is pretty darn good loss. And we are getting reasonable results for all classes, right? We know that this should be a 0. We know that this should be a 0. We know that this should be a 1. And we know that this should be a 1. So, and then we also know that these two are equal classes, so they should be fairly strong, fairly close to each other, right? 983, 982. So yeah, this is a pretty darn good model, right? What the heck, man? Eel over on Instagram, bad form, my guy. What's wrong with you, dude? Bad form. Give me just a second, guys. Gotta do some cleanup. I'm gonna have to take care of that afterwards. Sorry about that, guys. Yeah, so Yassine says the weights give good results. They do. Michael says yes, they want to save it. Fabrizio says those weights recognize the right patterns in the hidden layers and reduce cross entropy or MSE, so it's good for prediction or classification. Yep, I agree with that. Moore says I would reduce learning rate a bit just to see what happens first. Maybe, right? What do you guys think about that? So Moore is proposing that they want to play around with the learning rate some more. Give me the reasons why you would do that, and give me the reasons why you wouldn't do that. What do you guys think? Why would you do that, and why wouldn't you do that? Fabrizio says you would do that if the results are not as expected. You should have knowledge domain and what you predict. Ooh. And you wouldn't if it already have what is expected and tested in different experiments. You had me at results is not expected. You lost me at knowledge of domain. Guys, domain knowledge is a bias in itself, right? So you were on the right track and then you went off a cliff, Fabrizio. Just kidding, my friend. I appreciate all your contributions. Domain bias is domain knowledge is a form of bias, guys. Don't forget that. So I'm always hesitant to accept answers where people focus on the bias side of it, or on the domain side of it, right? Be very, very careful with that. Um, but why would you want to experiment and why wouldn't you want to experiment? Think about some of the business implications behind some of those things, right? Yassine says, I wouldn't. We already have a very good results. Why would we take slower time just to experiment? Maybe we can. Lawman says, I'm lost but interesting. Hey, Lawman, that's totally okay, my friend. I know you're a smart guy. You've been attending my streams for a very long time. So it's totally okay to just sit back and say, hey, I'm just going to listen. I'm going to try to, do my best. So thanks for being here. Starry Vibe says, we don't need to because there's a chance it might not converge. Michael says that the model already solves your problem, then no need. If not, then yes. Yeah, two good comments. Let me focus on Starry Vibes. There is a chance it might not converge. Not necessarily. Not necessarily. If anything, it would improve. Right? But is there a risk of it not converging at a lower learning rate? I don't know if I'm on board with that. I think it'll do okay. If anything, it's likely to converge better. Not faster. It won't converge faster, but it can be better. Now, kind of combining what everybody else said, do we need to be better? We're already at a fantastic loss. These class numbers are pretty good. So I generally agree with that sentiment that maybe we don't need it. But Starry Vibes, I don't think we're at risk of losing anything. Like, if anything, it's just going to get better. But we're going to go from 983 to 987, right? Which is like whoop-de-doo, right? But I don't think there's a risk of like it breaking our model and all of a sudden not converging and going back to some ridiculous loss. I think we're okay on the lower learning rate. Fabrizio says, depends on the project. If the 003 loss is accurate, then keep it. I think you meant to say 006. Let's say it's an investment of 100,000 and you should relook at this. It's involving money, maybe. Okay. So I like where Fabrizio's going in the sense that, yeah, maybe there are some very specialized situations where you're going to need very, very, very high accuracy, very, very, very low loss. So there could be situations where that's part of the spec that you're given, right? That you have to have a loss of 3 zeros, or you have to have a loss of less than 0.005, and we're not quite there yet, right? So yes, in that situation, maybe we tune the learning rate a little bit more, or other things a little bit more, right? But here's another reason that I want to give you guys, because again, I can appreciate that Fabrizio's tying this to like a business case. Here's the other situation. What if you run out of time? Like, that's another thing they don't teach you in school, right? You don't have all the time in the world to come up with models in the real world. There's deadlines. And there's situations where you're going to hand over models that you know are not as good as they could be, but the project manager said, hey, time's up, hand over your work. Like, that happens, right? So that's another situation where you would say, hey, look, it's the night before this is due. I still got to write the documentation for this. I'm going with this model. That happens, right? So that's another reason why you'd say, hey, this is it. This is good enough, right? You can't let perfect be the enemy of good enough. I guarantee you're going to have those scenarios in the future where you have to ship something just because time's up. Nobody tells you that in school, right? Nobody tells you that in those competitions or on those tutorials. But I 100% guarantee you that happens, right? Starry Vibe says, it's not the case here, but if we have a very small learning rate and few epochs, there's a possibility it might not converge. Sure, but that's just a bad experiment, right? You move on to another experiment, right? You move on to more nodes or more layers or different activation functions, right? So yeah, Starry Vibes, I hear you on that, but that's just a bad experiment. That doesn't That doesn't like kill your project per se, right? Fabrizio says, I have a question for you, Dennis. It's pretty basic, but for fraud detection in the insurance industry, will you use XGBoost models or neural nets? Where can I find info about this? You don't know. Fabrizio, it comes back to the same comment I gave you before, right? You're introducing domain bias. Like, why did you mention insurance industry? Who cares? Who cares what you're working on? It's about the data that's in front of you, right? Some data will do better for XGBoost, some will do better in neural nets. You don't know, right? Like, you shouldn't really care where the data is coming from. Like, you shouldn't be saying, oh, this is insurance industry data, so I better be using XGBoost. Like, who cares? I mean, that's like when I'm working, that's something that doesn't even cross my mind. You still have to go and do your experiments, right? So I know that we're focusing on neural networks, but as I've given the example before, what you really want to do is you want to do a complete champion model process, right? So neural networks would only be one of those types of models that I'm asking my staff to run. So the numbers that I've stuck with before is usually 8. When one of my juniors or somebody that works for me comes to me and says, hey, Dennis, I have this solution for that problem you gave me, I want them to walk me through the 8 different models that they used to come up with their proposed solutions. Now, sometimes we adjust that. Sometimes it could be as low as 6, right? But you should never be like, oh, I've seen this problem before. We used XGBoost. Let me go use XGBoost on this. Bad, wrong, terrible, terrible data science to do that. That's not data science, right? So it just depends, Orbisio. What if I have less data? Yeah, sure. The amount of data might play into it, but not necessarily, but I don't mean that by the depth of the data, I mean by the number of features. So, for example, would you use a decision tree on something that has 500 features? Probably not, right? Decision trees tend to do poorly on things that have a lot of features, right? So I think of it in those terms. But look at all the work we just did. We did all this work on 4 inputs. Like, this is great, right? And it's 4 inputs. Again, common mistake. All the idiot influencers, all the tutorials you see out there on YouTube. Oh, you need neural networks for millions and millions of rows. No, you don't. We just did a series of tutorials on 4 rows. 4. So yeah, data can play into it, but I think of it as the width, not the depth. Like, if you show me something and you already have like more than like a handful of features, yes, I'm eliminating some models. Maybe I'm not going to make that a regression model, or maybe I wouldn't use a decision tree on something that's wide. But after that, every model is still valid, right? So I think of it more in those terms, okay? All right, guys, we went for more than 2 hours today. You guys are insane. So thanks so much for all of your work. Thanks so much for being here. I can't believe we went this long. Really good stuff today. Good job, guys. So thanks for being here. Thanks for all the participation. We'll pick up again next Sunday. We'll actually start to look at some of the frameworks. We're also going to reinforce some of the stuff we learned today, because we covered a lot of ground today, guys. But you guys did a great job. So anything else I can help you guys with, I'm available for one-on-one coaching. Also, please join my data science school. Brandon, I see the thank you. Brandon, no, thank you. Brandon is our latest member of our data science school. He signed up while we were on the stream. Thank you so much. The link is in the chat. It's a pinned comment in the chat. I'm really trying to get this off the ground, guys. I'm going to kill the idea if I don't get enough members. Everybody will get their money back. Nobody's going to lose anything. But if I can't get the members, I'm simply just not going to do it because the site just wouldn't be self-funding in that way. But Michael says thanks. Yeah, thank you too, Michael. Thanks for being here. I know you're such a great supporter on Sundays. So we'll pick up again next Sunday. All right, guys. So as always, we live in such a dynamic world. I worry about you guys. I got followers all over the world, so I worry about these world events. So please take care of yourselves, take care of your families, and I'll see you guys next time. So neural networks week 5. Wow, guys, we've gone 5 videos in this series. Great job for staying in there with me. Okay, so lightning round review is up on the screen. Only 3 questions this time. And just as before, you don't have to answer all 3. You don't have to answer in order. Just give me your thoughts. Just tell me what question you're going after and put your answer in the chat. What is the effect of adding more epochs to our training cycle? What is the effect of adding more nodes to our layers? And what is a learning rate? Just pick one or pick all 3, whatever you want. And if somebody puts an answer and you're too shy, you can always just say, I agree with so-and-so, or I agree with that answer. But give you guys a few seconds here to think about it. Give me some answers to what is the effect of adding more epochs to our training cycle? What is the effect of adding more nodes to our layers? And what is a learning rate? What do you guys think? Some of these should be easier than others, but let me know. Parth says, for the first one, I guess the accuracy improves. Is that true? Is that true, guys? Let me know in the chat. You can just say, hey, I agree with Parth, or you can give up your own answer, right? But let's see if there's any other answers out there or people that want to attend try to attempt other questions. But for what is the effect of adding more epochs to our training cycle? Parth says, I'm guessing the accuracy improves. That's a perfectly reasonable answer, right? Let me know what you guys think in the chat here. Khalid says, more epochs means more chance to learn patterns. Yeah. Yeah, I mean, Parth and Khalid, you're giving up very similar answers, right? And yeah, that is the case, right? The longer you have epochs, or excuse me, the more epochs you have, the more there's an opportunity for your algorithm to train, right? Does that guarantee you reaching a good accuracy level or improving your algorithm? What do you guys think about that? Like, is it basically like gonna improve your accuracy like in all scenarios? Parth says, I mean, training accuracy keeps going up, but validation test accuracy might drop, so that's why I'm not 100% sure. Okay. Osama for saying, overfitting, the model starts to memorize the training data rather than generalizing it. Okay, so Osama's presenting a little bit of a contrasting view, maybe? Or maybe not a contrasting view, but he's presenting the other side of the coin, right? So yeah, overfitting could also be part of epochs, right? But what do you guys think? Are you guaranteed to improve? More epochs equals more better? What do you guys think? Or what do you guys think about the other questions? Everybody's answered question 1 so far, but what about 2 or 3? What about learning rate? We kind of learned that last week, right? We came up with some very reasonable explanations for learning rate, and we used learning rate, right? Learning rate benefited us a lot last week. What do you guys think? Give you guys another few seconds here. Michael, our good friend Michael from Nigeria. How are you, Michael? So good to see you. For number 3, what is a learning rate? Michael says, how fast or slow the network learns from the mistakes it makes during training in order to improve its accuracy. Michael also says, happy Sunday, Sir Dennis, and everyone. Happy Sunday to you too, Michael. Excuse me. So how fast or slow the network learns from the mistakes it makes during training in order to improve its accuracy. Okay, that sounds like a perfectly reasonable explanation, right? So Michael, so learning rate, if that's the speed at which it learns, like your definition says, right? How fast or slow? So that means a higher learning rate is better? Is that what I'm understanding? So more learning rate, more better, right? Let me know, Michael. Art says the learning rate is the pace at which your model learns. Too fast and it goes haywire, too slow and it wastes time. The magic is in finding the right balance. At least that's what I learned in classes. Okay. Help me understand what you mean by pace. Because remember, this is all, all data science or neural networks in particular, it's all just a mathematical representation, right? So what do you mean by pace when it comes to math? Vibov, welcome back. How are you, my friend? For question 1, Vibov says, but wouldn't it lead to overtraining at some point? Might need some restriction on epochs. Maybe. Vibov, I don't know if you've attended our previous sessions in this neural network series, but is that what we saw in our experiments? What do you guys think? If you guys have been here during our previous sessions, did we see that in our previous code runs? Did we see that we needed to restrict epochs because of overtraining? Khalid says the learning rates control the weights that updates during the training. Low rate makes the training slow. Okay. Okay, well slow sounds bad. So more learning rate, more better? Is that what you're telling me? I think it's Naaman, right? Or yeah, I think it's Naaman. Naaman says over on Instagram says learning rate is used to determine by a factor of what our gradients or weights will be changed per epoch. Okay. Okay. Parth says, when I said pace, I meant how big or small the changes are in the model's weights during the training after each learning step, or simply the iteration. Okay. Okay, cool. So Naren says, hi, I'm Naren. I'm thinking out loud. How does training loss and validation loss relate to those questions? Sorry, this is not an answer. Well, it can be in a lot of ways, right? Fabricio says, hi, Dennis. Hey, Fabricio, nice to see you again. Hope you're doing well out there, my friend. Let us know how you're doing. Vibob says, hi, Dennis. This is my first neural network class, but yes, I used to attend your ISLP classes last year. Yeah, I remember Vibob. How are you? Good to see you again. Yeah, if you guys want to know what he's referring to, that's the Introduction to Statistical Learning book. That was my first full series that I did. That was a lot of fun, so you can definitely find that on my YouTube channel if you'd like to see that. I have a whole playlist for that one. So Bach says, my book said that learning rate is a hyperparameter that controls how much the model's weights are adjusted in response to the estimated error. During training, please correct me. Yeah, no, I'm generally on board with that definition, but you got to have a sense for the scale, right? Like, is it more, a higher number is better or a lower number is better? Right? Michael says too high or too low can cause problems, so it's important to pick a good learning rate that help in training and efficiently, accurately. Okay. All right, Michael, that's pretty reasonable. over on Instagram, I'm sorry that your chat didn't come through for some reason, but I think it's Luann or Luana says it depends on the batch size and many other hyperparameters. Okay. Care to explain what a hyperparameter is? Because you're hitting on some of the topics we're going to talk about today. So Naaman says more means our weight will jump faster. It can lead to problems like jumping gradients. If it's too small, we can get vanishing gradients. So we need to select an appropriate learning rate. Will that lead to vanishing gradients? You had me all the way up to too small can get vanishing gradients. I don't know. I don't know if I'm on board with that part of it. What do you guys think? Does learning rate contribute? Does a lower learning rate contribute to vanishing gradients? I don't know. I'm going to say no. Change my mind. Let me know, guys. More epochs, yes, make it better a learning pattern, but at a point it will be overfitting to use validation loss. Okay. When data is limited, more epochs help the model learn robust features by revisiting the sample repeatedly. Okay. Yep. I'm sorry, I don't know. Your name is showing up as Arabic in my chat, so if you want to give me a name to use, I'd appreciate it. So they're saying lower. I'm assuming they mean the learning rate lower. Fabricio says lower learning rate is better. It helps move the gradient step by step instead of jumping fast and goes in the wrong direction and never converges or worse, stuck in a local minimum. Okay. Yeah, so let's talk about that. I'm going to go ahead and remind you guys that not every neural network results in a positive result, right? Not every neural network converges. So more epochs is not always more better. You know, as I was asking in some of my earlier replies, right? Just because you add more epochs doesn't mean that you're going to get a better result. And I'm stopping to say that now because Fabrizio and at least one other answer was talking about the local minimas, right? And your training can get stuck in local minimas that epochs won't help you. They won't help you at all. So be careful about equating more epochs to improvement. That's not always the case. So we won't be learning it this week, we'll probably be learning it next week, is that within neural networks, there's the concept of early stopping. Why do you use early stopping? Exactly for reasons like that. Because there are times where you're just not getting better. So it's perfectly okay to stop a run of epochs because you're just not going to improve, right? So just be careful with that. Don't think that more epochs is the automatic road to better accuracy, lower loss, things like that. If you do believe that, or if that was part of your answer, I'm not going to call out anybody, but if that was part of your answer or part of your thinking, maybe you didn't give the answer, look at question number 2. What is the effect of adding more nodes to our layers? And if you want to think about that even harder, what is more likely to reduce or to improve your accuracy, improve your overall model? Is it more nodes or is it more epochs? Think about that one. What's the, nothing's guaranteed, right? But what is the higher probability approach that you could be using? Is it more epochs or more nodes? Think about that. Okay, so it's Abdalaziz. Okay, yeah, I remember you. You've been here before. I think you were from Pakistan, if I remember right. Let me know. But thanks for being here. Welcome back. Welcome back, Abdelaziz. Michael says lower learning rate might take a very long time to get good results or get stuck before reaching the best solution. Michael, but they can all get stuck, right? They can all get stuck. You're right that it takes a longer time to get good results. But again, lower learning rate is not always a guarantee of a better result. Khalid says a high learning rate may also skip a minima. Yes, that's true, but that's still no guarantee of a better result because there could be multiple minimas, right? So I can appreciate where you're going with that, Khalid, but again, more epochs is not always more better, right? Okay, Abdulaziz says they're from Sudan. Sorry about that, but welcome back. Glad to see you here, my friend. So while you guys think about my other question, right? What is more likely to lead you to better results? More epochs or more nodes, right? Think about that. We're by proxy, we're hitting on a very, very important topic here. Do not assume that you're always going to get to a good answer with a neural network. Neural networks are very powerful. They're used quite a bit. They can be used on all types of data, but people take all of that and they assume that, oh, there has to be an answer we can get to. That's not always the case. That's not always the case. You are not guaranteed results. You can get pretty good results, but you are not guaranteed perfect results. And the reason I bring that up is because for those of you that have seen my content before, you guys know that there are some things in data science that I don't always agree with, right? And I don't always agree with some of the approaches and technology out there around automated self-driving vehicles. You know, Tesla and the FSD, Waymo and the Driver One or whatever they call it, OneDrive. Do not fall into the fallacy that machine learning and neural networks can solve everything. There is no guarantee that you're going to get good results that fit your use case. You can try different things. You can experiment with different things. That's part of being a data scientist. But to me, people who are working on self-driving cars are all working under the fundamental assumption that there's nothing that machine learning and neural networks can't solve. Who said that? Why does that have to be true? That doesn't have to be true at all. There can be plenty of unsolvable problems in data science, right? Now, for most of us, we're going to work on problems that can reach a conclusion, or at least maybe not perfect results, but acceptable results, because they don't kill anybody. They're not going to have any physical effect on somebody, right? You know, if you take a neural network and you misclassify a document, you know, nobody's going to die over that, right? But definitely have a healthy sense for the understanding that you are not guaranteed great results. There are going to be times where you're going to have to say, hey, we spent some time on this. We did our proper experimentation, and this is the best we could come up with. That's totally okay. Michael says, I would say more nodes. Okay. Fabrizio says, I will say more nodes. Nodes act as neurons and may capture global patterns and get this in the first layers. But if you had more layers, you may get deep learning. More nodes might help, but is not enough. I think you meant to say more epochs, but might help, but it's not enough. Let me know, Fabrizio. Vibab says, depends on the current state of the model, but if performance, you mean making our model smarter, then it'd be increasing the number of nodes. Yeah. Yeah, so the three of you are kind of hitting on that, and I think you're right. It's the number of nodes is much more likely to improve your accuracy, right? But as question 2 indicates, adding nodes does not come without costs, right? So what is the effect of adding more nodes to our layers? So let me know in the chat. What is the effect of that, right? So Fabrizio says Waymo uses convolutional neural nets for perception and reinforcement learning for planning movement. He studied mechanical engineer, and they are using both mechanical engineering and machine learning. Yeah, okay, that's all fine and good, Fabrizio, but there's still no guarantee that something good's going to happen, right? I mean, there are still some unsolvable problems in machine learning and data science, right? Vibob says complexity increases. Yeah, yeah, absolutely. Adding more nodes to our layers absolutely increases the complexity, which also means increased processing time. It's a bigger neural network overall, like literally in file size. It's going to affect your runtime times, right? In most scenarios, you won't need something that needs like microsecond level response times, but in some cases you might, right? But yeah, the complexity increases, but a it's more probable that you're going to get a refined neural network by adding more nodes to our layers and even adding layers than it is to say, well, I'll just run more epochs, right? So yeah, I think you guys are on the right track there. Okay. So if you want to think about this slide a little bit more, go ahead. That's totally fine. But let's think about this next slide. I posted this on my Instagram earlier this week, and it kind of got crickets, and that kind of disappointed me, guys. Because to me, everybody's asking me like, oh, Dennis, how can I improve my data science? How can give me a project idea? But like data science is all around you guys. Like you should be able to have a critical eye to so many things around you. So I saw this post on X, and I saw this last line caught my eye as a fun little exercise to think about. So this person is quoting, I guess this is like a Tesla press release or something. The neural nets for Optimus are larger than what Tesla uses for Auto. Okay, so just so we're clear, Optimus is their humanoid robot that they want to deploy. And Tesla obviously is using the full self-driving, right, the FSD. Neural nets for Optimus are larger than what Tesla uses for Auto. So this is a great opportunity for you to apply your own critical thinking. We have learned enough in the last 4 weeks here where we should be able to make an intelligent decision on this. Okay? So we're going to role play like we're Wall Street analysts, and we want to evaluate, this statement. Your boss asks you, as you're a business analyst, you're a financial analyst, and your boss asks you to evaluate this statement. Neural nets for Optimus are larger than what Tesla uses for Auto. I want you to think about that. And if you're having trouble with that, I'm going to give you a hint in about 30 seconds. But I want you to think about that because you should be smart enough, right? Well, first of all, this is the kind of stuff you should be doing as a data scientist anyways. I always have a critical eye. But right now, you should be able to make an intelligent conclusion on this. Whether it's right or wrong, we'll put that aside for now. But it's more about, can you draw a conclusion and what's your rationale, right? So guys, in the chat, give me your best, hey, I'm a data scientist, I'm a data analyst, here's my thought and here's my rationale. So think about that and put it in the chat. So Osama says, more nodes allow the network to learn more complexity, but too many nodes can cause overfitting or vanishing gradient. Yep, I'd agree with that. I think you're on the right track there, Osama. Michael says, increases computation, can improve accuracy, increase the network's capabilities for complex patterns, and may also cause overfitting. Yeah. Michael, I love how you put a plus and a minus for each point you made, right? It can improve accuracy, but it does increase the network's capabilities for complex patterns, but it may also cause overfitting. So yeah, I like that. All right, guys. So neural nets for Optimus are larger than what Tesla uses for Auto. What do you guys think? And guys, if you're over on Instagram, feel free to say hello. Feel free to join us over on YouTube. It's up to you, okay? I'll give you guys another bit of time. Think about this. The neural nets for Optimus are larger than what Tesla uses for Auto. Um, Yassine says, hello, sir. A late Yassine from Tangier, Morocco. Yassine, don't worry about it. Good to see you, my friend. Glad you're doing, hope you're doing well out there. Glad to see you. Yassine says, what is Optimus? Yeah, so for those of you guys that aren't familiar, Optimus is the humanoid robot from Tesla, right? That personally I think is going to be vaporware for a long time. But reasonable expectation that it uses a neural network. So they're saying that the neural networks for Optimus are larger than what Tesla uses for Auto. Fabrizio says, what does it mean? I think increasing neural nets doesn't change anything. It has to do with the quality of data and research expertise, not neural networks. The big problem has always been data. Yeah, Fabrizio, but your boss doesn't care about that, right? Your boss is looking at this statement and wants you to make a decision on it, right? So let's focus on the task at hand, right? So let me give you guys a hint. When I think about this, I think to myself, what does the output layer look like? So that's your hint. Start thinking about the output layer. What does the output layer for each one of these look like? Yassine says, I don't know what to do. I intend to do by saying that, but for me, it makes it worse. Yassine, I'm not sure I fully understand your question. But so Yassine, just to be clear here, right? The task in front of the chat right now is to evaluate this statement, right? This is part of a Tesla press release that was out earlier this week, and they're claiming that they have these two products, right? Optimus is the humanoid robot, and the Tesla, FSD full self-driving car, right? Both of them is reasonable to expect they use neural networks. And they're saying that the neural networks for Optimus, the robot, are larger than what Tesla uses for Auto. Vibob says, I think Auto is still a fairly narrow task compared to a machine that is supposed to imitate us. Okay. Define narrow, Vibob. Fabrizio says, output for Tesla might be object detection using CNN, and for Optimus might be reinforcement learning. Both of them are different. One is predicting, the other is generative unsupervised learning. I'm trying to fully understand your answer. Why would the Optimus be reinforcement learning? What makes you say that? And if it is reinforcement learning, wouldn't the Optimus neural network be smaller? I think it'd be smaller, right? Because a reinforcement learning neural network you can grow over time, right? Yassine says, to tell me that a humanoid robot has a bigger neural network than self-driving car, meaning they are more efficient, is completely irrational. What do you mean something can make an error? Make an error can end me is less efficient than something that has more tolerable errors. Okay. All right. So Yassine is looking at this from the error side, right? Because as we've talked about, more layers, more nodes should lead to better accuracy, but it does lead to a bigger neural network, right? So yeah, so okay, so Yassine is saying, well, look, Optimus has a much bigger margin of error, right? Whereas the Tesla, the car, has like zero margin of error. So Yassine, stop me if I'm misunderstanding you, but Yassine is saying, well, if the car has a lower margin of error, like zero margin of error, that means it's more nodes, more layers, all of that, right? And we know more nodes, more layers, more computation means more hardware, means bigger files. So Yassine, if I understand you right, Yassine would disagree with this statement, right? In a way, Fabrizio's previous one would also disagree with this statement because if Optimus is reinforcement learning, then it would presumably start off smaller, right? So Parth says, Elon once said during an AI day that a humanoid robot essentially needs to run FSD for legs and arms, meaning control of its entire body with real-time decision making. Okay. Which is even more complex than controlling a car with a fixed set of inputs and outputs. Ooh. Parth, you had me in your first statement, you lost me in your second one. A fixed set of inputs and outputs. I don't know about that. Is the world a fixed place? I don't know, Parth. I think that, and I don't want to be putting any words in anybody's mouth, but I think Yassine would disagree with you, right? Yeah, Parth, you kind of lost me in your second statement, my friend. Fabrizio says Optimus is human in the loop. It's used to optimize reward and loss policy with each correct movement of the robot. You are not predicting, but improving movement. Yeah. Put that aside, though. Answer the question, right? You're making your boss fall asleep, right? You got to answer the question, right? So, I like that, a lot of you guys are putting some rationale behind your answers. So remember that I gave you the clue of think about the output layer, right? So when I say thinking about the output layer, I'm kind of referring to the different objects that have to be recognized by each one of these, right? If I'm in FSD, I have to recognize every possible object that's coming at me in a driving situation. Versus an Optimus that has to recognize every possible situation. But is that a home? Is that a factory? Is that outdoors? Is that indoors? Now, Tesla is obviously going to tell you, oh, we're going to be able to hit all of those use cases for the Optimus. But can they really? But let's stick with the cars, right? How many objects does a car have to recognize? Like a neural network in a car have to recognize? And if you think about each one of those being an output layer, right? Or an output node within the output layer, Is that likely to be a short list or a long list? And I think about that because there's no requirements or no restrictions on it, but there's likely to be a correlation between the size of your output layer and all the other layers, right? You're not going to have 1,000 output layers and, excuse me, 1,000 output nodes, and your hidden layer is only going to have 3 nodes, right? Like that's usually not considered a good neural network design pattern, right? Vibob says narrow for self-driving cars is just an advanced cognitive problem, but for Optimus, the world is more physical, more varied interactions. Um, maybe. Yeah, maybe. Leo, so good to see you, my friend. Leo says, "Hi, everyone. Hope you're having a great weekend so far." Yeah, I think we are, Leo. Thanks for being here. Good to see you. Let us know how you're doing. Parth says, "What I meant by fixed was inputs, camera feeds, radar, lidar, GPS, speed sensor, etc. Outputs, steering, angle, acceleration, braking commands." Parth, but that's only one part of the potential outputs. You got to recognize what's around you first, right? So, what about just like object detection, Parth? There's almost certainly an object detection neural network, right? Yassine says, "It's true that the humanoid robot requires real-time decision making, but so is a self-driving car. However, for the latter one, the span of possible scenarios is much larger." Okay. So Yassine is arguing, hey, there's more situations in a car than there is for the Optimus. Right? You know, and coming back, I think it was, I'm not trying to call anybody out here, but somebody mentioned how you also got to control the arms and legs of the Optimus, right? So I think the counter argument to that is that yes, those are algorithms, but are they neural networks? Because not every algorithm is a neural network, guys, right? To me, that would strike me as more of a traditional like mechanical algorithm. I don't need a full-on neural network to tell me that I got to turn a mechanical leg, 30 degrees and take a step forward. That's probably not a neural network, right? That's probably like, it's probably just like math, right? Like engineering math. So are they using neural networks for that? Maybe, but it seems unlikely, seems inefficient, right? So that's got to be part of the rationale too, right? So Parth says, in a humanoid robot like Optimus, the robot has many more degrees of freedom, way more outputs to control. The sensory inputs can be more varied and complex. Parth says, kind of forgot about object detection. Yeah, Parth. So that's why I gave you guys the hint. Start with the output layer, because the output layer is what is the prediction of the neural network, right? And if I'm an FSD car and you're giving me all these images, right? Because FSD is camera based, I gotta know, is that a cyclist? Is that a pedestrian? Is that a stop sign? Or is that just a red light? Am I in between the lanes? Is there a car next to me? Like you got a lot of objects coming at you, right? So is that likely to be a small output layer or a large output layer? Fabrizio says 30% machine learning, 70% mechanical engineering. Yeah, I'd agree with that, Fabrizio. Yeah. Not everything's a neural network, guys, right? We can't rush to always go to a neural network solution. Let's bring it back to our friend Parth. Because if you guys remember, Parth was asking about neural networks in a video game. And I think that there's a lot of ways you could be using neural networks in a video game, right? But think about everything we just talked about. Is there a danger to using a lot of neural networks? Because you can use a neural network for object detection in a game, for the NPC control that Parth talked about, for some of the scoring elements, for some of the rendering elements, as far as how different worlds or different screens or whatever are created. But is there a downside to that? What's the downside to that? You guys should know the answer given everything we've talked about, right? Starry Vibes. Starry Vibes says, hello, sir. Hope you're well. I'm doing well, Starry Vibes. You're late. Just kidding, Starry Vibes. Hope you're doing well. Hope your studies are going well. Glad you could join us. Delio, what are your thoughts in Strata Scratch? Hey, Delio, I usually don't take individual questions on Sundays. It's more about the series. So if you want to join me on other days, you're welcome to stay for neural networks, but I don't really take individual questions on days like today. But Delio, if you do want to participate, the answer right now, the question in front of the chat right now is, why not just use neural networks for everything? As I said earlier, I think that some of the elements in Optimus are probably more just like mechanical engineering math. Like they're probably not using a neural network to move the arms and legs. I'm guessing that's low probability. Why? Why? And then also, guys, we haven't really reached a consensus on the screen, right? Neural networks for Optimus are larger than what Tesla uses for Auto. That should stop you in your tracks if you're a data scientist of any level, right? Like you should be able to apply critical thinking to that. So I think that Yassine is one of the few that's given, Yassine has basically given an answer. He's planted his flag, and I love that. I love for the data scientists that work for me to plant a flag and say, hey, I think this is the answer right here, and this is why, and this is what I'm sticking to. So come on, guys, give me your final answer. Talk to me like I'm the CEO. Don't give me that data science nonsense. Plant a flag. What's your answer here? Parth says, I once asked my professor regarding an idea I had, which was that what if we use neural networking to increase storylines possible? Like different endings operate about what the player does in game. Okay. Why wouldn't you do that? What is the case against that? Is there a case against that? Maybe there is, maybe there isn't. Though that idea was rejected by saying it'll be way more complex to handle, and the possibilities inside the game will be infinite, and sooner or later I'll be facing a game crash. Okay, why would you be facing a game crash? Like everybody should basically know this, right? Like why wouldn't you just put everything in a neural network? Right? All right, so I'll give you guys another 30 seconds here to plant a flag here and let me know what you're deciding on in terms of what you're seeing up on the screen. That is what I want to know, since my professor kept dodging that question by saying just try it out. Okay, well, that's not bad advice, right? Sometimes you learn more by getting burned, right? So guys, I mean, come on, the answer is performance, right? We just finished talking about how some of these neural networks, you got to be careful with the size of the nodes, right? It increases your footprint. It can potentially, well, it definitely will slow down your training time. It can have an effect on your runtime predictions, performance, right? Okay, so Michael is saying, given the challenges and complex requirements of developing a general purpose humanoid robot, I think it's reasonable to agree that the neural network powering Optimus would be larger and maybe more complex. Okay, Michael, so I see your conclusion, but help me understand your rationale a little bit more. So your rationale is because it's a general purpose robot. But I mean, couldn't I just tell you that a Tesla is a general purpose car? Right? I mean, I can put a Tesla in a lot more varied situations than I can an Optimus, can't I? Like like it's very unlikely that an Optimus would ever have to deal with rain, right? Or low light conditions. Like, because does anybody have a use case for for when an Optimus will be operating at night, like in low lights, right? Like, obviously, at night inside a well lit factory is no big deal, but like at night in low light conditions, like what's the use case for that? You're gonna have the Optimus mowing your lawn at night, like. But I can think of a lot of situations where I'll be using my car at night in the rain, in the snow, right? So I personally tend to side a little bit more with Yassine, right? Because I think about that output layer and all the different things that a car has to recognize. And I'm thinking, wait a minute, that's a lot. Fabrizio says, I think neural nets for Optimus are not larger than for cars. Mechanical engineering can help fix some problems without large computing. Second, reinforcement learning doesn't involve large neural network process, assuming this is used for robotics. Okay. So Fabrizio, you're sticking with the reinforcement learning side of it, and that's okay. I guess I really can't comment on that because I hadn't heard that they would be deployed in a reinforcement learning state. Now, obviously, they're using reinforcement learning now during training, during like the pre-purchase or the preparation of Optimus. But I didn't think that would apply when you actually buy one, right? They should already come trained for the majority of tasks, right? But I can appreciate that you did provide a rationale. So yeah, so Fabrizio, Yassine, and I are kind of like going against the statement here. Right? We're probably saying, hey, we disagree with this. This doesn't smell right. Right? We're getting there via different rationales, and that's completely okay. But yeah, so we have at least three of us disagreeing. Michael, so far, is the only one I can see that is agreeing with the statement. He can see a path to why Optimus would be larger than what Tesla uses, right? So I think is it Naren? Let me look, because I know you said your name earlier. Was it Naren? Yeah, it's Naren. So Naren says, I think you'd need a bigger, better neural network for the car than the robot, keeping in mind that a mistake in the car will cost lives, robot less chance of a life getting affected. Yeah, okay. Okay, Naren. So Naren is also on team disagree here, right? Where because the auto neural network needs higher accuracy, higher recall, higher precision, higher everything, it's going to be a larger, more layers, more nodes, all of that, right? So yeah, I'd agree with that. So that's four of us disagreeing with the statement with three completely different rationales. So that's great, guys. This is exactly the type of conversation that you should expect to have in a data science team room, right? That's kind of like what we're simulating here, right? So this is good, guys. This is good. Um, whoa. Michael's saying, I also agree with the points you raised as well. Now, Michael, come on. You can't back away from what you said before, buddy. When you plant a flag, you got to be willing to fight for that, right? Discourse is a healthy thing on a team, right? So don't back away on me now, buddy. Come on. You got to stick with what you said. Michael says, what do you think about the demands of embodied AI in the future being fundamentally different and arguably more encompassing than those of autonomous driving? Help me understand what you mean by embodied AI. Because you're giving a very specific example of autonomous driving, but you're not giving us an example of the embodied AI. Because also one thing we should remember, guys, autonomous driving isn't necessarily AI. It's much more on the machine learning side than it is AI, right? But keep that in mind, Michael. Give me a better summary, if you can, on what you mean by embodied AI. So Leo says, the idea of EVs performing in a safe, functional way, from my perspective, can't be achieved without considering a whole integrated road system that can optimize the mixed algorithms performance. Same with Optimus. I don't like the idea of a humanoid robot built for general purpose. Okay. All right, Leo, I can appreciate that. But Leo, where do you stand on this section, on this statement, though? Because you're right, you're describing like the utopian scenario, right? Like the ideal use case. But we most likely won't achieve that, right? Like, Elon Musk isn't sitting around waiting for road improvements or road sensor improvements or whatever, right? And obviously that'd be a large scale project anyways. So we can only really take what's in front of us, right? So what's your take on this actual statement? What do you guys think? Last call for statements on this, and then we're going to move on. The last call for planting a flag. Michael, don't back up on me now, man. You gotta stand by your guns. You end up respecting somebody who can say, hey, you know what? I hear you guys, but I got my position. I'm happy with my rationale. This is what I believe, and that's what I'm gonna stand with. Don't be quick to bend, Michael. Don't lose on me now, man. All right, guys. So last call for answers. Last call for answers on the highlighted section. But most of us are on team disagree, right? Most of us do think that the car would have the larger neural network. Or if you're shy, you can just say, hey, I'm on team disagree also. Or you're on team Michael, right? I guess team Michael would be team agree, right? But it's healthy to have a rationale. It's healthy for us to have this discussion. Again, I'm using this as an example for different things that you guys could be picking up in your daily readings, in your, articles, your social media or white papers. You should be picking this up and saying, hey, I'm a data scientist. I know enough to answer this. Let me form my own opinion. Let me, exercise my data science skills here. Okay, so Leo is on team agree. I agree with Optimus having the larger one. Optimus was designed to have general purpose and handle much more than cars. Okay. So Leo thinks, so Leo and Michael are on the same team there for team agree. Manoj is joining team disagree. I agree with you, Sir Dennis. Yeah, thanks, Manoj. So we have a little bit of a split room, guys, and that's okay. But again, I think this was a fun exercise to go through because this is the stuff that I stop and do, right? When you guys tell me, oh, I want to do what you do, Dennis, I want to be a data scientist. This is what I do, right? This is something that just came up on my Twitter, like, for you. You can see I don't even follow this account. It's just something that came up. And you should have a critical eye for this to be able to catch up and say, "Oh, well, wait a minute. Whoa. What's this say? What's this say? Oh, I don't know if that's true or not. Let me think about that." I want you guys to have that thinking, okay? So Michael says, embodied AI is like giving that AI brain a body, a robot, for example. So instead of just existing as code in a computer, AI can actually move around, see, touch, and interact with the real world. Okay, I understand that as a concept, but is that what's being promised from Optimus? I'm not claiming to be an Optimus expert, but I haven't seen anybody out there who's like promising that as part of the output or part of the goal, right? Let me know. I'm happy to be wrong on that. But to me, I still view it as a a mechanical use of machine learning, right? I don't even view it as AI. Remember, guys, there's a difference between AI and machine learning, and machine learning is not AI. So keep that in mind when you think about these things. Leo says the generalization function requires a larger and complex neural network. Yeah. But I mean, I'm sure there's ways for us to quantify this. It just feels like a car has more objects to detect or more situations to make a conclusion on than an Optimus would. And I have nothing quantitative to back that up. It's more of just a professional opinion, right? But who knows? You might be right. Maybe there is a larger generalization function for a robot. Fabrizio says robotics are also using GANs to replicate right movements of the robotics compares to humans. It's a type of generative ML. This one requires more stops of a gradient, less computation, less nets. I've never heard anyone use the word GANs and less computation in the same sentence. If anything, it's more computation. So yes, GANs are being used. But I think that those GANs are probably heavier on the training side than they are the runtime side, is my guess. We need to understand the type of machine learning model they use better to make informed decisions, but I will say it uses less neural networks. Yeah, I think it's probably... Oh, wait, Fabricius, you're still proposing this as an answer. Yeah, I agree with your conclusion, but I'm still not sure if I understand the path that you used to get there. Right? Because you could also say that the FSDs use GANs, right? Yeah, so I'd still like a little bit of a clear rationale and a little bit more of an understandable rationale, right? Because remember, sometimes when we're doing this, we're also practicing for the non-technical audience. So keep that in mind. Okay, guys, so I want to move on to the next slide. But this has been great discussion, right? And this is exactly what you should be having. And if you don't, you should be encouraging it among your data science team, right? You can have difficult questions and you can take reasonable answers to them, but you got to be able to back them up with your rationale and be able to explain your rationale, right? So good job on doing that, guys. All right. So this is not quite a lightning round review, because this is a little bit kind of like a looking forward to some of the topics that I want to cover today. So, two questions up on the screen. Feel free to answer either one. Let me know in the chat. One, are there different kinds of neural networks? Two, what are hyperparameters and how can we adjust these? What do you guys think? Some of you have already mentioned, like somebody mentioned hyperparameters before in the chat. So what are they? How do you adjust them? Give me some examples or whatever you'd like. What do you guys think? So feel free to answer one of these, two of these. If you don't know these, that's okay. Like I said, these are a little bit of a looking forward type of questions. But are there different kinds of neural networks? And what are hyperparameters? How can you adjust those? What do you guys think? Give you guys another few seconds to think about these. So Leo says the cars would work more with classification problem algorithm levels today instead of clustering, anomaly detection, or either ranking problems. Just finishing the thoughts. Okay. Yeah, Leo, but that's part of the problem though, right? Because if you're saying classification problem, which I agree with, how many things do you have to classify? Isn't each classification class an output in your neural network? It's an output node, right? So that's why I said the hint previously was think about what your output layer looks like. Is that a small output layer or a big output layer? Right? So take what you just said about it being a classification problem. How many items are you classifying? Is that likely to be a small list or a large list? So Yassine and Manoj are saying yes. Yeah. Well, yeah. Okay. Yes. Give me more. Give me more than just the yes or no. Okay. All right. Starry Vibes coming in strong with an answer for hyperparameters. Hyperparameters are external configurations of a neural network, like a learning rate, batch size, epochs. Okay. All right. Manoj says CNN, RNN, FNN. Okay. Give me some definitions there. Give me some definitions. What's a CNN? What's an RNN? What's an FNN? Leo says it's a big one, but smaller than Optimus. Well, Leo, I guess that's where the crux of the question lies, right? I don't know if it's smaller than Optimus. I'm tempted to say that the car is bigger. There's so many things to consider in a car, right? And it's not just enough for me to say, oh, that's a speed limit sign. I have to be able to read and understand the speed limit sign, right? And then there's just so many variations. Like, is that a cyclist or a motorcyclist? Is that one cyclist or two cyclists? And then there's like road markings, right? Am I in a turn lane? Am I in between the two markers? Is there a crosswalk coming up, right? Like a pedestrian crosswalk? I don't know, Leo. It just seems like in a car, there's a million different images coming at you, right? Starry Vibe says they're set before training and adjusted to optimize performance using techniques like grid search. Ah, okay. What's a grid search? What is a grid search, Starry Vibes? I like where you're going with this, but give me some more details. Fabrizio says yes. Give me some more details, my friend. Khalid says yes, like CNN, RNN, FNN. So Khalid, a good answer, but give me definitions for those. Hyperparameters are the configuration settings before training a machine learning model. Okay. Hyperparameters are parameters that can't be optimized mathematically with some predefined rule and have different optimal values for different problems. Okay. Can't be optimized mathematically, but that's everything in the world, right? Feed forward and then simple basic structure of input, hidden, and output layers. Okay, keep going, Manoj, keep going. Fabrizio says hyperparameters are fixed values used to initiate the feed forward backward propagation on neural networks. Ooh. Is that all they do though? Is that all they do, Fabrizio? Feels like they do a lot more than that. Let's see what Starry Vibes come up with, because Starry Vibes is on the right track. Starry Vibe says it's a method to find the best hyperparameters by trying all possible combinations from a predefined list. Okay, so that's Starry Vibes answering to what is a grid search. Manoj says CNN's image and spatial data convolution neural networks to detect patterns like edges, textures, and objects. Okay. Okay. All right. So let's think about what Starry Vibe said. So Starry Vibes was answering the question of what are hyperparameters, right? Hyperparameters are external configurations of a neural network like learning rate, batch size, and epochs. They are set before training and adjusted to optimize performance using techniques like grid search. They are set before training and adjusted to optimize performance. Okay. And then I asked, what is a grid search? And grid search is a method to find the best hyperparameters by trying all possible combinations from a predefined list. Okay. So hyperparameters are variables that we can set, a collection of variables that we can set and try them before, set them and try them during training. And we are adjusting them to optimize performance. In addition to that, we are coming up with a predefined list of values for all of those. And then we're trying the different combinations via what Starry Vibes is telling us is called the grid search. Okay. So I agree with that definition, with all of those definitions. Doesn't that sound like something, guys? Let me know in the chat. Doesn't that remind you of something? It's a bunch of predefined variables that we can set, and we can try different values during training for model optimization. That just feels like something, doesn't it? Doesn't like remind you of something? What do you guys think? Let me know in the chat. What is that? Like what are we doing? Like why does that even exist? I'm thinking of a word, guys. It sounds like something, doesn't it? Fabrizio is CNN as image recognition, RNN word by word prediction. Maybe. Let's make sure that we're not jumping to the uses, guys. we got to think about the underlying um reasons why these things exist. Like, why do we even need different ways of neural networks? Like, why? Um, Fabrizio says you can do grid search or random search to adjust the configuration of hyperparameters to improve. Yes, that can be done too. Okay. Naren says weights. Naren says choose the weights to reduce loss. The best weights to reduce loss. Yeah, okay. But Naren, doesn't it feel like it's something? Kunal over on Instagram. Hi, how are you? Welcome. I think you've been here before, so welcome back. Hope you're doing well. Let us know how you're doing. But guys, this feels like something, right? Ooh. Ooh, um Fabrizio, I'm not sure if I'm feeling this answer. Um aren't you doing this during any training cycle though? I'm encouraging guys to think about this on a meta level. Like, why would grid search even exist? I'm thinking of a word here, guys. Oh, starry vibes, you're so close. Because different problems need different architecture. Oh, Yassine, you're so close. Like a Monte Carlo simulation. Okay. Oh, Khalid. Khalid got it right on the nose. We need different kinds of neural networks because we have different data types. Aha. Khalid, I love that explanation. We're going to come back to that, Khalid. We're going to come back to that. But Khalid, you're coming up with a great answer. So Khalid, if you want to go 2 for 2, what is the answer on, everything that Starry Vibes told us and everything everybody understands about grid search and hyperparameters? What is that? Why does this even exist? Starry Vibes, you're so close because different problems need different architectures. And Yassine, it's like a Monte Carlo simulation. Both of you are super close, super close. But think about it on a higher level. Like, what are we doing here? Like, why? What is this? So why are we even bothering with grid searches? What do you guys think? Why are we even bothering with any of this? Give you guys another 30 seconds. Yassine says optimizing the model. Yeah, that's the goal. But why? Like, what's the purpose of that? What do you guys think? Another 30 seconds here, and we'll get going with this one. Khalid says grid search is like a tuning technique to find the best combination. Yeah, okay, but why? Search tries all combinations in the grid to see which one gives the best performance. Yeah, but why? Like, what are we doing? What are we doing? So guys, to capture all the possibilities. Yeah, but why? Why? So guys, here's the answer. Very important. Write this one down. The reason why we focus so much on grid searches and what it means and the process of it is because this is where it's the experimentation of data science. Grid searches essentially represent the experiment side of the scientific process. What do I always tell you guys? When in doubt with data science, you always return back to the scientific method, right? In the scientific method, you make an observation, you form a hypothesis, you collect your data, and then you run experiments on your data, right? So this is us in the lab doing the experimentation side of data science. That's why you do this, right? So we're not chemists, who sit there and mix beakers and Bunsen burners and all that. We work with data. So grid searches is the experimentation side of being a scientist. That's really the big takeaway here, right? Very important for you to view it that way because it should change your perspective on how broad and how frequent you want to do your grid searches, because your grid searches is basically the core of everything that we do as data scientists. Now, we're focusing on neural networks for now, but part of that experimentation is also trying it across different models. But even within those models, you're going to be doing grid searches because you don't know what version of that model performs best. But that's you being in the lab with your white lab coat and all that, running your experiments. So it's very important for you to view it that way, to say, hey, wait a minute, I'm a scientist. I run experiments on my data. It just so happens I do it with code and I call it grid searching, but these are my experiments. So every time you run these, every time you run a training cycle, every time you run a series of epochs, that's an experiment. So when I tell you guys data science is a science, we should be following the scientific method. You should be constantly experimenting with your data, asking questions of your data. This is it. This is where the rubber hits the road when it comes to the experimentation side of data science. So keep that in mind, because that is really what's this is where the work is, right? This is where you're separated from everything else. You can even think of it this way, right? When people say, oh, well, data scientists are also just coders, or I'm a coder, I can also be a data scientist. Grid search is unique to data science. You don't do grid searching, or if you're a software engineer, right? Because software engineers don't run experiments, data scientists do. Data science requires experimentation. Software engineering doesn't really do that, right? So keep that in mind, because this is where you're running experiments. This is your lab. You should be keeping track of these experiments. Just like a chemist would write down and say, oh, this time I'm going to use 10 milliliters, but last time I used 5 milliliters or whatever. We're doing the same thing. Oh, this time I use this learning rate. Now this time I'm going to use this other learning rate. This is where data science is running experiments. Super important for you guys to see it that way, because then you start to understand the importance of it. You guys with me on that? But just keep that in mind. Like you should have a permanent connection in your brain. When I'm talking about grid searching, when I'm talking about trying different hyperparameters, those are my experiments. That's me working in my lab, in my, hey, I don't know what the answer is, but I'm going to find out by running experiments. That's that phase, right? Your grid search phase. You guys with me on that? Super, super important concept. And we see this, I think you can see it more clearly than you can in other models. Like you can get a sense of this from other models like regression methods, right? But you really kind of understand it the most here in neural networks because grid searching is such a defined portion of what we do in our code. Okay? Khalid says it automates the trial and error process. Yeah, sure. Instead of checking every possible combination like grid search, random search picks random combination of hyperparameters from your given ranges. Yeah, yeah, sure, but like, why would you need to do that? I mean, if you're pressed for time, maybe you would do the random searching, but that's part of the advantages of using code, right? That you can try every permutation in a relatively short amount of time, right? Or a reasonable amount of time. Fabrizio says data comes in different forms, can be x squared. So it distributes different ways and you can capture those patterns better with those techniques. Okay. I could see that. Salient, I think it's your first time, so welcome. Grid is like iterating from beginning to end with every possible parameter. So large data sets means slow process. Random is more advantageous. Maybe, but that's only if you need it, right? If you're pressed for time or if you have bad hardware or whatever, okay. But there's going to be situations where you're going to have plenty of time and plenty of hardware. So I don't think that holds to say that random is more advantageous, right? Parth says, I mean, it's faster. Faster for what? Like you can't always say that, especially if you have a large number of hyperparameters, right? Because you're going to have interaction factors, right? Interactivity factors. So just because you hit on one random combination that kind of sort of works doesn't mean that like doesn't mean that you're any closer, right? Doesn't mean like the next combination up is going to be better, right? So I don't know if I'm buying that, Parth. Okay, so here's what I want to do. I want to go back to some of our code. We are going to continue working with our little toy example that we had before. Do you guys remember, if you were here last week, you can remember that we were getting some pretty good results with something like this, right? We were using hidden layers, some output layers. We know that we're doing an XOR table. This is our training data and our expected outputs. And we were messing around with the learning rate, with the epochs, and the hidden layers, right? So think about everything we just said. When we were messing around with our learning rate and we were messing around with this number here and messing around with the epochs, what were we doing? What's that called? Let me know in the chat. What in retrospect, right? Because we didn't talk about hyperparameter tuning this last week or grid search last week. What were we doing what were we doing then? What was that called? What were we doing? Michael, you're the man. Yeah, we were experimenting. Yassine will that's right. That was us wearing our white lab coats. We were trying different mixtures and all that. That was us running experiments. That was us doing a portion of hyperparameter tuning. It was a manual way of doing it. We didn't really adjust code, we adjusted variables. But guess what? There's no requirement on what you have to do that, or on how you have to do it. The point is that we were applying the scientific method. Hey, let's try this. Oh, gee, that didn't work so well. Oh, that was terrible. Let me go in the other direction. That's still experiments. That's still hyperparameter tuning. That's still maybe not quite grid searching because we weren't going about it in orderly fashion. We were just kind of guessing. But we were experimenting. I mean, this is the scientific method for data science. Right? Like, that's the beauty of what we were doing. Okay, Yassine says lesson taught. Yeah, so I think you guys will see where I'm going with that, right? And this also ties back to something, what I told you guys before, where for me, when I learned neural networks, that's where data science like really took off in my mind. Like I was already into it, and I was already like I already taken a few classes and all that. But like when I saw like the neural networks and the architecture and the activation functions, and then seeing the grid search, that's where it was like, oh man, I understand why they're so powerful. Because now you can run like 1,000 experiments in like 10 minutes. Like that's part of the power of neural networks and grid searching in general, right? All right, so I'm trying to think about what this looked like for us before we did adjustments. I want to say that was 20. I think I want to say it was 2. And I know this was 10,000. So I want to tie, give me a second here, guys, to experiment. Because I want to tie this back to the last thing I want to teach today. Okay. Is that what I wanted? Yeah. Okay. So I made some modifications. If you guys remember, last week, we got to some really good results, right? We got to a neural network that was viable. This is kind of where we started. I think I got most of the parameters correct. So first of all, real quick, is this a good neural network or is this a bad neural network? Just give me a 1 if you think this is a good one. Give me a 0 if you think it's a bad neural network. Give me your answers real quick in the chat, and then we'll get to talking about where I'm going with this. There is a method to my madness, guys. Okay, so Yassine is voting 0, 0 for Michael. Starry Vibes also a 0. Ooh, Salient. Guys, somebody go check on Salient. They got a bad keyboard. They meant to write a 0, but they wrote a 1. Okay. So yeah, I'm seeing a lot of 0s in the chat, and I think that's right? The loss is not great, and most of you are probably already keying in on here, right? This is not great, right? And we know that because we know what our input data looks like, right? Let me go back to that. We know that we are just training on a simple XOR table. So if you guys aren't familiar, this is from the world of Boolean logic, right? Boolean logic and XOR would tell you that you only need one or the other to be a 1. If both are on or both are off, it's a 0, right? This is our training data. Just Watch, I think it's your first time here, so welcome, glad to see you. Just Watcher did not say anything. They just voted, so username checks out. Okay, so we know that this is our output, right? Or our desired output in our training data, right? Okay. And if you guys have been here before, you remember that I told you guys that my eye brought me to these two results. To me, this is a sign of a terrible neural network. So let me know in the chat, why should that catch your eye? Why am I saying that that's a really bad sign of a bad neural network? Just Watcher says, yes, sir. Well, glad to have you here, Just Watcher. If you want to just hang out, that's totally cool. A lot of people do that. Alien says, I heard it wrong. Sorry. No worries, my friend. No worries. We were going to send a search party out there. Make sure you were wrong. Make sure you were okay. Salient just created an off by 1 error. Yeah, but here's the thing, Khalid, that on most keyboards, the 1 and the 0 are really far apart, right? So, I don't know. Being the outlier. Okay, I can get that. I can be down with that. Okay, guys, so what's wrong here? Why did I tell you guys that these two lines caught my eye? What catches your eye that tells you that, ooh, this may not be such a good neural network? Michael says too far apart. Give me more information on that, Michael. You're implying they should be close together. Why should they be close together? Right? Or anybody else. Why would these two lines catch my eye? I'm saying that, as I'm a trained professional here, guys, right? So to my professional eye, this catches my attention. Why is that? Why should it catch your attention too? What do you guys think? We're going to go over 2 hours again, guys. Guys, we need to talk, guys. I'm an old man, guys. You're making me go for 2 hours on a Sunday morning? On a Sunday morning, on 1 cup of coffee. You guys are making me talk for 2 hours? You guys are so mean to me. Why should this catch your attention, guys? Okay, so Fabrizio says different problem, same class. Actually meant to say different probability, same class. Oh, yeah, and that's exactly right, guys, right? Huge red flag. We know that these two resolve to the same output of 1 in an XOR table, right? But yet we're so far off on those classifications. So Fabrizio's right? It's different probabilities for what's essentially the same class, the same output. So that's a huge red flag, right? Okay. The second reason why it's such a huge red flag is over here. Look at those inputs, guys. So even just like not from a data science, just from a general perspective, like you're telling me that 0, 1 gets me a 0.5, but 1, 0 gets me a 0.97? Same number of inputs, same input, same value of inputs, but I just reversed them. And you're telling me that that gives me completely different results? What? What does that tell you guys? And keep in mind, I just asked you guys, are there different types of neural networks? And I think the most reasonable answer somebody said was, Well, because there's different types of data. So think about that, and then think about what I just told you here. 0 and 1, and 1 and 0, same number of inputs, same value of inputs, but reversed. What does that tell you? What conclusions are you able to draw from that? Right? If we put on our scientist thinking caps, what is the conclusion we're drawing from this experiment? Because we just ran an experiment, right? And you don't have to think about it from a like a neural network expert. Just think about it as a data science student. What does that tell you? Same class, same class. They should give same probabilities. Yeah, Fabrizio, I'm with you on that. But let's focus on the 0, 1, 1, 0. What does that tell you guys? What is, and you can start by thinking, well, what is the only difference there? You can clearly see it's the same number of inputs, 2 inputs, same value, 0 and 1, but they're reversed. So what does that tell you? What do you guys think? Okay. Yassine. Yassine says, the conclusion I got is that order matters to that network. Yeah. Just Watcher says, yeah, order matters. Leo says data pre-processing failed. Maybe, Leo. But yeah, Just Watcher and Yassine, I think you're on the right track. Because that's the only difference, right? The only difference is 1001. If you guys want to sound all like data science professional about it, that's known as a sequence. Sequence matters. Right? That's basically what we've concluded here, right? That's what this shows us. Give me just a second here, guys. Sequence matters. That's what we've learned. So, we're 1 for 1 here, guys. Let's go 2 for 2. Sequence matters. And we just said that there's different types of neural networks, right? What should our next experiment be? This is only one type of neural network, guys. It's a very simplistic one. We're not using any frameworks. We're not using a lot of data, right? It's a very small data set, right? We're not using, anything fancy, really, right? I mean, the whole thing is like what, a couple hundred lines of code, right? It's 86 lines of code. So I should have said a couple dozen lines of code. But what should our next experiment be? Okay, Yassine says we need to try a more sequence compatible architecture like an RNN. Yeah. Perfectly reasonable conclusion, right? So I'm walking you guys through this so that we can understand the thinking process that we should be exercising as data scientists, right? Because we're not changing the data. The data is what it is. But we can change our experiments. We can run experiments, draw reasonable conclusions to shape our next experiments. Right? Nothing wrong with that. So yeah, we can do that. So let's take a quick second here to calibrate our understanding. Why would Yassine have suggested specifically an RNN? So there's CNNs and there's RNNs. Does somebody want to give me the most basic explanation possible that they can of what a CNN is versus an RNN? And why would RNN fit this need? Hint, if you wanted to, you could also make the argument that a CNN fits this need. If you wanted to. But what do you guys think? Because I'm in agreement that an RNN makes sense here. But you could also make an argument for a CNN. Why am I saying that? Some of you guys already had the answers in the previous section. So just think about your previous answers. Okay, so Salient says CNN is for unstructured data, images, RNN for sequential data. Khalid says, because can process sequences and remember order. Okay. Anybody else? Okay, I'm sorry. Maybe I didn't read Part's answer. CNN says best for images, spatial patterns. RNN best for sequences, time-based patterns. Okay. Anybody else? Sorry guys, I moved my console off the screen. Didn't mean to do that. Fabrizio says, use an MLP multi-layer perceptron. Maybe. Isn't that a little bit of a overkill for 4 different inputs? Maybe a little bit of an overkill. Okay, but most of you guys are on the right track there, right? Where you want to use something that's more for sequential data, right? CNN is more suitable for images. It can also be used in variation. CNN for one-dimensional data as the input we have. Okay, so Yassine, I think you're hitting on you're the one closest hitting to the point I'm trying to make here. So remember that I referred to it as sequences, right? But sequences can be, one-dimensional or multi-dimensional, right? So for those of you that are recommending the RNN, it hits upon what Yassine is talking about where RNNs are good for single dimension, right? Like a time series would be, right? This happened period 1, period 2, period 3. It's one dimension, but it's sequential, but it's one dimension, right? But images are not like that. Images can have multiple dimensions. Still sequential, right? You still have to have your pixels in a certain order. But now you have what are referred to as the edges to deal with. And say, well, wait a minute. Yes, there's a sequence this way, but there's a sequence this way too. So if I have a piece of data, a pixel in the center, well, I got other pieces of data, other pixels around those edges, right? So feel free to go and look it up in Wikipedia and you'll get the nerd explanation. But when you think about these, I want you to think about those in that scenario, because it's all sequencing. but is it single dimensional or multi-dimensional sequencing? Right? So here's the trick to this, guys. Remember that at this point, we're still kind of using this as a really good toy model that we're getting a lot of power from, but we're not using a framework just yet. So I don't know if it's possible for ChatGPT to work out this simple of a model and be able to show us an RNN example, right? So let's find out. We're going to go back here. If you remember, this is the same prompt we had before. And we are going to go ahead and we are going to say, hey, can you modify this and show us an RNN example, right? And I think we can basically keep the same code. We made our own modifications, but I think we can generally keep the same code and we'll just start a new file. And actually, maybe I need to make that a little bigger. Let me see. Let me know if that's big enough on the screen for you guys to see, okay? So again, we're going to ask to do it only with Python code, right? No frameworks. Just show me the raw code, right? I don't even know if it's possible, but we'll see. And by the way, just as a reminder, we're using ChatGPT o3. That's a little bit of a departure for us. If you've attended my Sunday series before, you guys know that I'm a big fan of 4.0 for coding. 4.0 served us really well for multiple series, right? But we have made the switch to o3, and so far it's done a pretty good job. But just quickly pointing that out for you guys, because I know I've stated how much I believe in 4.0 previously. All right, so it's giving us the code. It's still going to be using an XOR demo. Okay, no, it's gonna be changing it up a little bit. You know what? Let me copy this over into VS Code, and that way we can all take a look at it in a little bit of a better way. Oh no. All right. So a little bit of a bigger code file. Is this going to be more of a script? Okay, I mean, I guess that's not terrible. All right, let me take a quick look at this, guys. So that's going to be our text. It's going to do it with text, which I guess makes sense. Um, let's see what this code runs with. I don't know how excited I am about this code, guys. I don't know if I'm excited about this. I was hoping that it would still keep the XOR example. And we actually got an error. Okay. What was that? Line 90? That is not good. Um, let's go back to ChatGPT, guys. And by the way, just as I was talking about how great O3 is, it gave us an error, right? I mean, we're gonna have to go back and look at that code because that is that's a little discouraging that that would give us an error right on the first run. I'm trying to still figure out where the T came from. The T is in reverse range of the inputs. Wait, where is reversed? Reversed is one of the native functions, right? That doesn't make sense. Does that make sense? For the range of the length of inputs, give me the reverse of that. Okay. Returns a reverse iterator on the values of the given sequence. But doesn't this resolve to an integer? Am I seeing, guys, let me know in the chat. Am I reading that wrong? I think our problems lie here, right? Because we know that it fails. It fails here because it's telling us it can't find row T, right? But here, am I reading that right? Doesn't that return an integer? But how can you reverse an integer? What do you guys think? Am I seeing that right? Let me know. So let me go back to ChatGPT. Okay, so this time it can't. It is going to go ahead and use an XOR. So if you guys don't mind, I'd rather try this one. And we'll just call this NN3 because I kind of want to take a look at NN2, if only just to see if there's a legitimate error made by O3. Okay. So here we go. All right, guys. So this looks a little bit more reasonable. So let's step through this real quick. Ayush says Can't see the whole code. Ayush, thanks for joining us over on Instagram. Feel free to come over to YouTube where you can see it in widescreen, okay? Instagram just doesn't show the widescreen. Fabrizio is doing the, yeah, I get why you need to do that, Fabrizio, but how are you reversing an integer though? That doesn't make sense to me. All right, but let's focus on this example here. So there's a couple of different things that we should already be recognizing, right? We should already be recognizing the sigmoid function, which is something that we saw in our previous examples. We should be noticing this, right? This is the same XOR table that we were learning on in our previous one, right? Here's the hyperparameters. So that's going to be 3 nodes in our hidden layer, a learning rate of 0.4 and 10,000 epochs, which seems like pretty normal hyperparameters to start with, at least reasonable hyperparameters to start with, right? Down here, we're going to have our training loop, which is basically running through our epochs, right? And then here, we are doing our backwards propagation, right? We know that by the, right, here's the backwards propagation. And then here is where we're taking the sequencing into account, right? The RNN function of our neural network. So this is basically kind of where this code is what didn't exist in our previous example. Our previous example was not an RNN network, whereas this one is. So this is where kind of like that magic happens, right? All right. So I want to do something very, very quickly. And again, I'm asking you guys to think about this in terms of our data science knowledge, right? So let's go back here. We know that this was 200. We know that this was 0.5. And we know that this was 60,000. Okay. And just to prove that out, let me go run this. All right. So remember that this is the neural network that we were running to get some really good results using our previous non-RNN approach, right? So here we were getting a pretty good loss. We got down to 3 zeros, I believe. And we got down to some pretty good accuracy numbers for all 4 of the classes, right? We're going to 60,000 epochs. So you can see here that it's not fast. It's also not fast because we have 200 200 nodes in our hidden layer, right? So that's a lot of calculations, right? So really good loss, really good accuracy, not a lot of speed, right? And it's also going to be a larger neural network because we're doing more calculations. There's more weights to keep track of, right? You can see here we now have to keep track of all these weights, right? These were our starting weights, right? That's a lot of weights that we want to keep track of, right? A lot of weights that are changing during every pass, right? So now here we're done. Very, very low loss. Very, very reasonable answers for all of the input classes, right? So we can get there with this neural network. Now, knowing what we know about RNNs and knowing that we're going to try this example, in the chat, give me your hypothesis. What are you expecting the results of this experiment to be? Are we going to have more nodes or less nodes? Are we going to have a higher learning rate or a lower learning rate? Is it going to take us more epochs to get there or fewer epochs to get there? Let me know in the chat. Remember, this is us putting all the elements together. This is us using our critical thinking skills as data scientists, right? It's totally okay to go into these experiments and think about, well, what am I expecting here? Why am I doing this step? And then when you finish, did this experiment meet my expectations? Sometimes it does, sometimes it doesn't, right? Okay, so Yasina saying, I think better results with less epochs. Yep. That's a reasonable conclusion. Fabrizio says, fewer epochs, less nodes to get there. The RNN architecture helps capture better patterns. Yep. Yeah. Yeah, I agree with that, right? So less epochs means less training time. Because remember, epochs don't affect our runtime, right? But it does affect our training time. And then less nodes, yeah, that's a reasonable expectation. And that does affect our footprint, right? The number of weights we need to track. And it also affects our runtime, right? So yeah, perfectly reasonable expectations. So let's run it. So this is NN3. Now we're going to start with these hyperparameters, which are reasonable starting points, maybe not great values, or at least, we don't think they're great values, but there's nothing wrong with starting here. So let's go and run NN3. Okay. So we only ran 10,000 epochs, very small neural network. We got answers almost instantly, right? What do you guys think? What do you guys think of these results? Is it Ali? I think I see Ali over on Instagram. If you want a different name, let me know. But Ali, thanks for being here. I think it's your first time. Ali says less nodes. Yeah, perfectly reasonable to think that we're going to have less nodes, right? Perfectly reasonable. But what do you guys think about these results that are up on the screen now? What do you guys think? Let me know what you guys think. Let me know in the chat. What are these results telling you? So I'm seeing a loss of 0.12, and you can see the results for each class there. What do you guys think? Fabrizio says the 01 and 10 with different probabilities is not good, but the fact that the loss starts with 0.19 with just 2,000 epochs is good. 01 and 10 with different probabilities. Oh. Okay, yeah, Fabrizio says 00 and 11. Yeah, 00 and 11 is probably not great, right? So Fabrizio's talking about this one down here and this one down here. They both should result in 0. So those are off, right? They are, as you said earlier from Ali. Yeah, that's right. So it's not great, but for a first pass, it's not terrible. And it's not terrible given the size of what we're working with, right? Because Fabrizio says with just 2,000 epochs is good. Well, actually, it was 10,000 epochs, Fabrizio. But yeah, but with the number of epochs, it's actually pretty good, right? Yassine says generally good, even if it's not very sure for the first case. It can confidently identify second class, generally better than the other architecture. In some epochs, we can easily define decision bounds. Yeah, yeah. Yeah, it's not a finished state, but it's not terrible, right? What if? Well, there's a lot of things we could change here, right? We could change the hidden layers, the size of the hidden layer, the learning rate, and the epoch. So let's be smart about this, right? What do you guys think, given all that we know, what is the most effective experiment we could try next? Because remember, we're experimenting, right? We're in the lab right now. This is the thick of things. We are doing the data science work. What do you think is the most reasonable item to change here? What do you guys think? All right, guys, I'm out of coffee. So either one of you needs to order me coffee and have coffee show up here, or two, we're going to finish earlier. Where did RNN retain the data again? It's down here in the code. It's basically down here, starting at line 64. We know that we're starting back propagation here, and then here is where it's tracking the sequence of the inputs. Yassine says, can we show the results back? Okay, sure. So those are your results, Yassine. The loss is not terrible, right? Fabrizio says, change layers to get deeper learning. One layer just gives you global patterns, also number of epochs. Hold on a second there, Fabrizio. Hold on a second. There's a big difference between adding layers versus adding epochs, right? Completely different implications of both of those. So we can't just, try both of them just randomly, right? We got to be smart about this. So guys, I mean, look, let's take another look at the code here. Look at this learning rate. What did we say about learning rate? More high, more better, or more low, more better? Right? Okay, so Yassine says loss is not terrible, but not improving over time. So number of epochs might not be the best choice. Adding nodes can affect runtime and training time, by the way. So learning rate is the best one. Yeah, I think the learning rate, right? What happens if we were to make that like 0.05, right? Because, I think it was Yassine that said it, or somebody said it last time, where, the analogy they used was if you were guiding someone like on a map, you were telling them like, where to turn and all that. You want them to take small steps, not big steps, right? Because if they take too big of steps, they're going to miss turns. Oh, no, go back. You should have turned right. You should have turned. But if they take small steps, it's really easy to guide somebody, right? Almost impossible to miss a turn if they're taking small steps, right? So, excuse me, why not the learning rate? That's the quickest hyperparameter, the quickest experiment we could run right now, right? Michael, hidden layers, I think. Michael, but hidden layers come with a cost, right? Why add more computational costs when we can just adjust the learning rate, right? Fabrizio says, oh, that learning rate is awful. Yeah, it's not a great learning rate, right? So let's try 0.5. Did I save that? I think I did. Sure, I did. Okay. What do you guys think? The loss didn't really improve, did it? So what are we seeing here? Anybody take a guess at what we're seeing here? Navin, nice to see you again. How are you? Loss didn't really get lower with more epochs. Yeah. Let's change those epochs. Let's go to let's go to 20,000. We'll double it. Not great, right? As you seen posted earlier or observed earlier, this hasn't really changed a lot, right? The loss kind of sort of stayed the same, right? Yeah, for BTO size, it's not learning. Yeah. So now that we've done other things, we've explored other options. Yeah. Now I think it's completely okay to say, hey, wait a minute. Let's 5x our nodes. Are we any better here? Did anybody else notice something? Did that run faster or run slower? Michael says not much difference. Yeah, that's right. Stuck in a local minima? Maybe. Maybe. Let's make it a little bigger. What if is anybody happy with this performance? Now remember, we're also doing back propagation with this RNN, right? So that means we've essentially increased the number of calculations that we're having to do, right? So was anybody happy with that performance just now? That was terrible, right? Took a long time to get there. All right. So Fabrizio is saying change initial seed weights, maybe? Maybe. So remember how we talked about experimentation, right? Part of experimentation is knowing what to adjust and kind of have like some sort of target of what you're aiming for, right? So, can't we do that? In proper data science terms, don't we have a baseline to work against? We do, right? Because guess what? We have a model that we know works, right? Um, we know that these hyperparameters work. on the same data, right? The same XOR table. So is it reasonable for us to be able to use this, at least as an initial guideline? And I think it is, right? So what happens if we come over here and we say the hidden size is going to be 200 and the epochs are going to be 60,000? So we're going to closely mimic over here, right? What happens if we run this? Let's let that go. So Fabrizio says, I think the problem is how the features are being injected. Can we visualize data, do some EDA? There's 4 rows, Fabrizio, right? We can't lose sight of that. It's a toy example with an XOR table. Can't really do EDA on 4 items. And remember that we already have a model that works. We're just trying to see if this is a better way to go about it. Right? Because that's part of the experimentation process. Just because you find a model that works doesn't mean you stop. You keep going. And that's part of the champion model process. And that's essentially what I'm starting to show you guys here. Right? You have a baseline and you're trying to beat that baseline. We have a model that works. It's just a very simple model. Salient says, is it because of the activation function being tanh? Maybe. But I think it's more about the number of calculations that we're doing. Because remember, before we were in what's known as a feed-forward neural network. It just goes through once, finds the weights, and you're done. But now that we've introduced the RNN portion of it, you're also introducing the backpropagation. So now you're going through the network, but then you're also going backwards and saying, oh, wait a minute, let me adjust this, this, and this, and this, and then you're going through it again, right? So I don't think it's the individual activation functions. I think it's just that we're doing a lot more calculations. And we can see that here, right? Because look, now we've gotten up to 200 hidden nodes, 200 nodes in our hidden layer. And look how long it's taking just to get to that first epoch result. So this raises an interesting question while we're waiting for this, right? We're using different hyperparameters, completely valid. We're potentially going to get similar results to the ones we got before. And let's assume we even get better results than we got before from our baseline, right? Our simple feed-forward model. Have we won? Yassine says, are you sure your Mac is okay? Yeah, well, you got to ask that question, right? Like, have you won? Like, maybe this does get to a better model. Like, you can say that quantitatively. Oh, look, the loss is better. The classification is better. But have you won if the model is slower? Maybe, maybe not, right? Yassine says it's fighting for its life. You know what, Yassine? I am due for a new Mac. I run everything on a Mac Mini. I love the Mac Mini platform. That's just me. But I am overdue for a new Mac Mini. I want to get one of those. I've been pricing some out, and I don't know. We'll see if that's in my budget for this year. But I'd love to get a new Mac Mini. But I mean, look how slow it is, guys. And we're going to 60,000 epochs here. So let's assume we're going to get to a better model. But if the performance stinks, have you won? Yassine says absolutely not winning. Yeah. I mean, this performance stinks right now, right? So I hope you guys can see that, fancier is not better. Sometimes a simple model gets you to a better answer, right? And maybe we can say, hey, look, maybe RNN isn't the best solution here. Is it feed forward? Maybe, but we have to try other experiments. So far, it's the champion model, but maybe we want to try CNN next, right? But this performance right now is terrible. In a way, it makes sense though, because remember, if we're going from just doing the forward propagation to doing the forward and backwards propagation, we've massively increased the number of calculations we're doing, right? So maybe the win is in just doing that forward pass. Maybe you don't need back propagation. I mean, look at that. Our second result of epochs came up. And we sat here and we waited for an additional 2,000 epochs and we gained 0.0002 in our loss. That's a slow day, guys. That's a slow walk. So we have to think about that, right? Just because you run an experiment doesn't mean, or just because you're running what you think should be the latest and greatest experiment, latest and greatest architecture, doesn't mean it's always going to have a positive result. Something to think about, guys. All right. Anybody have any additional thoughts while we're waiting? I think we're going to be waiting a while, guys. Jeez, this is slow. This is slow. And we went to 60,000 epochs. Good lordy. I'm looking here. 1253, 1252, 1254, 1259, 12.7. So we're getting slightly better loss. We got a better loss here. But this is not good, guys. Should our experiment be based on looking for optimal solutions? So starting from the minimum resource consuming hyperparameters and then increase based on that while choosing the one with less impact on resources. Hard to say, Yassine. Hard to say. You can choose whatever you'd like. You know, there's no laws to it. But in my experience, the biggest determinant of what you need is going to be like the due date, right? Because remember, in everything we've talked about, this experimentation, the hyperparameters, the number of calculations we're doing, we've completely ignored the element of deadlines and time, right? There's going to be times when you have to ship a model that you wish you had more time to work on, but you have to ship it because the project manager said so. Like that's just a real world reality, right? So keep that in mind. Yes, I mean, that's how I would answer you. See, there's many ways to go about it. Just pick one. But most of the time, it'll just be time. Salient says, better architecture comes with computational cost. You know, that sounds suspiciously like, what is that called? An oxymoron, right? Is it better if you have a more computational cost? Like, is it better? You know, like I said, have we won here? I don't think we've won, right? So that's better in quotation marks. This doesn't feel any better, right? So yeah, Salen, I'd say that you're posing an oxymoron there, right? Sure doesn't feel like we're doing any better. Man, this is going to take a while. And we're basically at the same loss as before. So this is also a good time to kind of illustrate what I mentioned to you guys about early stopping, right? If we know that we can get to a model that gets us to this loss, why would you accept this loss at 6,000 epochs? Like, yes, maybe that could improve, But if that's going to take you another 3 hours to get there, I could run a lot of experiments in 3 hours, right? So this is where you might say, okay, you know what? Let's stop this. Let's move on to something else. Let's stop here. We've reached the best we can do with RNNs. Let's try CNNs. Like that would be a valid conclusion at this point, right? We would exercise our early stopping decisions and we keep the results, right? Because we want to document all experiments. But we move on to something else. This is a really good example of that. We're at 8,000 epochs. And granted, that is the lowest loss we've seen so far, right? We've never hit 1251. So kind of, sort of headed in a good direction, but not very fast, right? So something to think about there too, guys. All right, so we covered a lot of ground today, guys. I hope that this has been beneficial in understanding all of the different approaches that we could be possibly using, right? Because there's a lot to it, right? There's a lot of different variations, a lot of different things that can be tried, right? Yeah. So I'm going to let this run in the background, see where it ends up. But I think I want to wrap up here because we've gone for almost 3 hours. But I want you guys to think about all the different things that we've covered today, because that means that next week's lightning round review is going to be very interesting, right? Lots of things to talk about in the review. Feel free to look up the definitions for CNNs and RNNs in the nerd explanations. But the bottom line is that sequence matters. We're going to see that in NLP. You're going to see that in image processing, right? But sequence does matter. Maybe it didn't matter for us in this example because the XOR table is only 4 inputs, right? Four rows. 4 rows, 2 different classes, right? But you can kind of get a feel for how you experiment your way to a solution, right? Let me know if you have questions in the meantime. But really happy you guys attended. Hopefully you guys get something out of this session. We're also going to be gravitating more towards using some frameworks because we haven't looked at frameworks yet, right? So next week, I promise that we're going to do at least one of these examples with a framework. It's time that we do that, right? It's time for us to leave the raw code and go to the frameworks. And who knows, maybe we'll see better performance, right? In theory, the framework should help you see better performance. So guys, thank you so much. Really appreciate all the participation. Really happy to be spending Sunday with you. In the chats, there is a link to sign up for my data science school. Guys, I'm trying to get to 1,000 signups prior to opening. At this point, it's in danger of me having to kill the project because I'm not seeing the number of signups I'd like to see to have the school be self-sustaining. But if you haven't signed up, please sign up for my data science school. I want to open it by August 1st, but I'll never get to an opening phase if I don't get enough signups, okay? So thanks for being here. Thanks for all the feedback. As always, we live in a very dynamic world. I worry about all of you. So please, take care of yourselves, take care of your families, and I'll see you guys next time. All right, let's get started with our lightning round review for our latest installment on neural networks. I have some questions up on the screen. Now, some of these might look familiar because we did have some of them last week. But there's also a lot of new people in the chat. So why don't we start with these 4 questions? What is a learning rate? Are there different types of neural networks? When would you use each one? What is a grid search? And is every grid search successful? What are some of the frameworks that are used for neural networks? And why do we never use PyTorch? All right. So, excuse me, those are the 4 questions in front of the group right now. Feel free to put your answers in the chat below. But what do you think? Why do we have, what are the answers that we can put with some of these 4 questions? I'll give you guys a minute to think about it. You don't have to answer all of them. You don't have to answer in order. Just pick one that you feel most comfortable with and go for it. I'm going to have to figure out why the Instagram is still acting up, just like it was last weekend. But we've had a lot of growth on Instagram recently, so I'm going to do a special stream just for them after this. But until then, let's think about these 4 questions. What is a learning rate? Are there different types of neural networks? What is a grid search? And what are some of the frameworks used for neural networks? And by the way, that last one's important because today I do want to focus on using frameworks. We've been using raw code, which is great, right? I'm a fan of that. But let's get a little bit more modern today. We're going to start using some frameworks. So let's see how comfortable you guys are with these 4 questions. What do you guys think? Feel free to put them in the chat. Okay, Starry Vibe says learning rate controls how much the model's weights are updated during training. Okay, yep. That's a pretty reasonable answer. Starry Vibe says, are there different types of neural networks? Yes. Okay, Starry Vibes, give me at least one if you don't mind. Give me at least one. And if you're too shy or don't know the answer, you can just say, I agree with Starry Vibes, I disagree with Starry Vibes, whatever you guys want here. Okay, Manoj says, grid search, tuning hyperparameters by exhaustively trying combinations from a predefined set of values. Grid search is tuning hyperparameters by exhaustively, yeah, that's a pretty good definition. What do you guys think? Yassine says, yes, for number 2, he says, yes, there are many types of neural networks. Like RNNs, CNNs, we use each one depending on the data and the problem at hand, and more specifically, data dimensions. Okay. I like that, Yassine. I like your answer. We're going to come back to it because I like the way you closed out the answer there. Denelson says, a learning rate is how fast or slow a model learns from its epochs. It can either take big steps or small steps after each epoch to find a minimum. Okay, Denelson, Denelson, is it more desirable to take smaller steps or bigger steps? Because you say what it can do, big steps or small steps, but that doesn't tell me which one is more desirable. What do you think? Okay, Starry Vibe says, for the different types of neural networks, CNN, FNN, and GANs. FNN. Did you mean to do FFN, maybe? I don't know of an FNN, but, maybe I'm just wrong. But I think you meant FFN. And then also, Starry Vibes mentions GANs. So that's an interesting mention. So if anybody in the chat, what does GAN stand for? We haven't seen that one yet before, right? We haven't seen that one. So if somebody wants to give me the definition for GAN, G-A-N, go ahead and put it in the chat, okay? Michael says, happy Sunday, Dennis and Eric. Michael, so good to see you. How are you, our good friend? Michael, I believe that you are from Nigeria, so welcome back. Glad you're here, my friend. Yassine says, grid search is a method to experiment with different combinations of hyperparameter values. Yeah, I like that. Yeah. Okay, Starry Vibes is a feed forward neural net. Okay, yeah, so I guess it would be FFNN, wouldn't it? Because I said FNN. No, I said FFN. But yeah, okay. Started up. So you were, I got what you were saying. I just, the acronym FNN, I don't think I've ever come across. But thank you for that. So for the definition of GAN, Yassine is posting generative adversarial networks. Okay, cool. So I'm going to take a small diversion here, guys, because we are not going to learn about GANs today. I have that planned for next weekend, or next Sunday, I should say. And the reason I say that is because I'm not sure if GANs are its own neural network as much as they are a neural network architecture. And I think that distinction is important. I would argue that it is an architecture, not a type of neural network. If you guys have done a little bit of work with GANs, you might understand what I mean by that. If you don't understand what I mean by that, that's okay. We're going to cover that much more in depth next week. But for today, for those of you that do know what GANs are, I would propose to you that they are not a type of neural network. So we actually won't be focusing on it today. Okay? And hey, I'm happy to be wrong on this. If you guys, I'm open to debate. If you guys want to tell me otherwise, feel free to do so in the chat, okay? So Ayush, our new friend Ayush says neural network frameworks is TensorFlow, PyTorch, Keras, and JAX. Okay. I'm familiar with the first three, obviously, but not JAX. So somebody wants to fill me in on JAX. Give me the elevator pitch on JAX, sir. I'd appreciate it. Denelson says, yes, there are different types of neural networks. There are models like CNN, RNN, LSTM, so on, can be most effective with data that are close to a time series, where CNN can work best with images. Okay, Denelson. So remember how I said that Yassine had a very interesting way of closing out his definition of these neural networks, right? So last week we talked a little bit about this, about how people say, oh, RNN, that's for time series. Well, no, it's for data that's it's 4-dimensional data, right? It just so happens that time series is data in a single dimension, right? Because you can say that the series matters and the ordering and the previous inputs can have an effect on future inputs, so on and so forth, right? So I'm encouraging you to think about it in terms of the dimensionality of the data rather than, oh, it's time series. Because the same thing for CNNs, right? CNNs, people always say, oh, that's what I use for my image processing. It's good for images. Well, no, it's good for dimensional data, but that's multiple dimensional data, right? Because it's not a single pixel in a picture, it's a pixel that's surrounded by other pixels, right? So, like, in layman's terms, those edges and those connections count, right? It's important that this pixel is above this pixel, but to the right of this pixel, and then also below this one, right? But that's not an image, that's multidimensional data, right? So that's where I'd like for you to think about it, Denelson. So again, look back at Yassine's answer, because we need to kind of keep that in mind, that all of the YouTube tutorials, the fake influencers, all the idiot influencers, they always say, "Oh, use this for time series." Well, but that's kind of an ignorant statement, right? It's not that it's time series; it's that it's single dimensional data or multidimensional data, right? That's really kind of what we want to know. Because remember, the neural network, the algorithm, it doesn't know it's dealing with time series. It doesn't know it's dealing with an image, right? It's all math to that, right? So keep that in mind, guys. Single dimensional data versus multidimensional. Ayush, we're going to come back to your question, okay? Manoj says generative adversarial network is the workflow or architecture. Yeah, Manoj, I would agree with that. And again, guys, if you don't understand what Manoj means by that, that's okay. That's okay. You can still stay. But next week, we're going to talk a little bit more about that. Let me read ahead here a little bit. Okay, so Starry Vibes says 3. 3, is every grid search successful? No, it can get stuck in local minima. That's right. The local minima is one of the many problems a grid search can have. But what we really should remember is that not every grid search is successful. Not every set of experiments is successful. So if we go to our terminal window, some of you guys might remember this, right? We worked on this a couple of weeks ago, right? Hold on a second. That's not refreshing. Give me just a second. There we go. You guys might remember this. Who remembers this, right? Remember this terminal output? Remember how slow it was? We actually had to cut the session short because this was so long, and this didn't finish by the time we finished our session. And this is a terrible model, right? But it was a grid search. It was a lot of epochs. It was supposed to be a better architecture. I believe this is an RNN that we did, if I remember right. But wasn't successful, right? And not to get on a tangent here, but this is one of those things that I kind of have trouble with machine learning in general, or AI in the public eye and things like that, right? Everybody assumes that machine learning can solve everything, but that's not always the case. Machine learning models at the end of the day are still math formulas, right? It's all still numbers based. So that doesn't mean that every single attempt you do is going to be successful. So going back to Starry Vibes' answer, it can get stuck in a local minima, right? There can be other problems with it too. But not every grid search is successful, guys. Just because you run 1,000 experiments doesn't mean like you have to get a positive result. You have to be willing to say, we ran the experiments and we couldn't get there. Lots of companies are unwilling to do that. All right, let me go back to my deck here. All right, so Denelson says, when it comes to learning rate, there is no learning rate that will be effective. DS experiments to determine if their model needs to take big steps or small steps to find the minimum, nitty gritty. Yeah, Denelson. I like the way you put that. Thanks for that. And I think you're on the right track there. Thanks a lot for that. Yes. Yassine says, yes, I can see the argument for that. It's not manipulating the node calculations and processing method. It's just structuring existing types of neural networks in a way to achieve a certain objective. Yeah, Yassine, I think you're talking about the multidimensionality of it all. But yeah, I mean, I like how you mentioned the node calculation, because again, guys, remember the neural networks are math representations of the brain. That doesn't mean it's thinking. It doesn't mean that like it's, sentient or making decisions on its own. It's just picking the best result from what the math says, right? And we're going to see a little bit of that today. So remember, the model doesn't know what it's working on. The model just knows the numbers. That's it, right? Denelson says, grid search is a way for us to automate experiments with different configurations for hyperparameters so we can find a good enough model and then retrain the model and further tune it. Yeah, I like that, Denelson. That's a pretty good definition there. Denelson says, there are frameworks that we can use for neural networks. The two most popular are Keras and PyTorch. We use Keras and not PyTorch because we have families that love Okay, so Ayush, our new friend Ayush, says, why do we never use PyTorch? Because of production challenges it has. Not sure about it, but curious to know more about why. So Ayush, I would encourage you to read Dennelson's answer. PyTorch is only for people who didn't grow up with a father in the home. So if your father went out for cigarettes one day and never came back, Ayush, you're welcome to use PyTorch. No, that didn't happen to us, so we're going to choose to use Keras and other frameworks that make sense. But Ayush, the decision is ultimately up to you. But Denelson, thank you so much for showing that it's not your first rodeo. Denelson understood the assignment there. Yassine says that he was referring to GANs. Okay. Yeah. Okay, Yassine, sorry about that. Yeah, I see it now. And Yassine, you're 100% right. That the argument that I was making is that it's not a type of neural network, it's an architecture. And yeah, you're modifying the structure of it all to get to a desired result, right? And really to say a desired generated result, right? But yeah, Yassine, we're on the same page there with the GANs. Okay, cool. Are there any last answers or any last questions on this deck before we move on? Oh, excuse me, on this slide before we move on? Ayush says, what an analogy. Ayush, I do my best to teach you guys serious, right? But at the same time, we can always have a little fun. And like I've always said, for full disclosure, I am one of the moderators on the Keras mailing list, so I am a little biased. I fully recognize my bias. But my parents aren't divorced. I didn't grow up in a broken home. What can I say? I like Keras. Yush says I love it. Well, thank you, Yush. If you love that, then you're gonna fit right in. So just keep on coming back. All right, let's go to the next one. So we already had Starry Vibes mention feed-forward neural networks. And by the way, guys, I assume that most of you are already going to know what's on these slides. But for some reason, I just felt like I needed something where we actually state it so that we as the group can have a collective understanding of what we're talking about when we're talking about these feed forwards or these RNNs, CNNs, and all that, right? So these are the general definitions or general guidelines that I'd like for you to keep in mind. So feed forward starts from your input layers and makes a pass through your output layers, and that's it, right? It doesn't go back and try to make changes and adjust and take information that it's learned and make adjustments to previous layers and all that. It just goes in one direction, feed forward, right? Pretty easy. All right, recurrent neural networks. It maintains a memory of previous inputs so that you can create a context for itself. You'll notice that I said, and I chose my words carefully here, tends to do well with time series data. But as I prefer to say, it's also sequential data with a single dimension, right? We're basically saying that order matters. The order in which I'm giving you the inputs matter. That's basically what you're saying with an RNN. It just so happens that time series also shares that quality that the order matters. But remember, the model doesn't know you're giving it time series data, right? So we got to think about it is that RNNs do well with sequential data in a single dimension. Right? So keep that in mind, okay? And if you want to actually think about this a little bit further, what else is data where the order or the sequence matters? What else? Think about that. Let me know in the chat. What else is out there where sequence matters? And also keep in mind, I chose the tends to because again, there's no rule that says you have to do this. Too many of the idiot influencers out there are, oh, it's time series. Oh, we must use an RNN. You don't have to do anything. That's part of the experimentation of life, right? Experimentation of data science. maybe a feed-forward neural network will work just fine. Or if we go back to our previous example, right? We did do an RNN on this data and it performed horribly. What are you going to do then? Just stop because, oh, well, it's time series. We have to use RNN. No, you don't. You can do whatever you want. Right? So keep that in mind. So for my previous question of what else is sequential data with a single dimension, Yassine says NLP. That's right. Text data, right? Text data is sequential. It matters where you put the words, right? You can't just output all the words of a sentence, even though every single word is correct and fits the sentence. The order in which they're in matters, right? So yeah, Yassine's right. Text data is sequential, arguably single-dimensional data, right? So I'm using that again to reinforce that sample. Don't get stuck on RNNs for a time series. It can be for anything you want it to be. It tends to do well on time series. It's best with single-dimensional data, but you never know, right? Manoj says, agree with Yassine. Yeah, Yassine was right on that, right? And by the way, guys, you know, if you're feeling shy or don't always know the answer, feel free to do just as Manoj did and say, hey, I agree with so and so, or I disagree with so and so. That's okay. You don't have to give a long answer everything. But again, right? It's not that it does well for time series, it's that it does well on sequential single-dimensional data. And there's a lot of other sequential single-dimension data that you can come up with out there besides time series. Okay? All right, next one. Convolutional neural networks, or CNNs. So this also tries to create context, but it just does it with more inputs. So it assumes that whatever data you're giving it is part of a grid. So it wants to take all the edges into account. Right? So if single dimensional sequential data is just on one plane, CNN says, well, wait a minute, you could have multiple planes. So I want to know not just what's beside it, but what's on top of it, what's the diagonals, what's on those edges. And it just so happens that that's also convenient for pixels, right? Pixels have edges. You can't just have a jumble of pixels. It matters that this pixel is above this one, below this one, to the left of this one, diagonal of that one. It's this color, whereas the one next to it is another, right? Like, it matters. So CNN takes that into account. But again, the neural network does not know any of that, so it does well with sequential data with multiple dimensions. That's really the takeaway there. And again, I'm sure that there are other examples for sequential data with multiple dimensions that go beyond pictures, right? There could be other things out there. All right. Let's go to the next slide. I thought I'd bring this up because I thought this was kind of funny. But what is this trying to capture, guys? What makes this meme funny? Let me know what your takeaway is on this one. I'll give you guys a minute to think about it. Go ahead and tell me in the chat. Yassine says, if I can share an example we worked on to emphasize the idea that it's essentially about the dimensions. One time we used CNN to classify the problem type behind missing data in tables. Okay. Yeah, I could see that, Yassine. I could definitely see that. There could definitely be reasons why you'd want to do that, right? If you're trying to fill in or classify why you had missing data in a sequence, yeah, that would be very good, right? So thank you, Yassine. Appreciate that example. Fabrizio, welcome back. How are you, Fabrizio? Hope you're doing well. Um, Fabrizio says, I think you need to feature engineer data before sending. If not, we cannot explore fully the patterns on the net. I think you need to feature engineer data before sending. If not, we can explore fully the patterns on the net. I'm going to assume you mean the patterns on the neural network. Fabrizio, I'm going to say that your statement doesn't hold for a lot of scenarios. Today we're going to focus on image data, and I would say that image data is one of those, right? You don't tend to have too much feature engineering on image data. You would also say the same for like audio data, right? Or signal processing. You actually kind of don't want to have a lot on those types of scenarios, right? So in some scenarios, I would agree with you, but you can still do a lot of learning and a lot of exploration without any feature engineering. I actually had this conversation with one of my clients recently. I'm giving him private NLP lessons, like private tutoring lessons. And one of the beauties about NLP is that like there's a lot of pre-processing that exists for NLP, but there's no rules that you have to use it. There's no rules whatsoever that you have to use it. You can do whatever you want with the pre-processing. I don't want to talk too much about the project, but I worked on a project where I wanted to keep emojis. Like I treated emojis as like text or as communication, right? Like you wouldn't say that for every project, but like there's no rule around that, right? So I understand the spirit of your point, Fabrizio, but that's not always the case. You can do a lot without any engineering. And in some cases, you don't want to do any data engineering, or excuse me, feature engineering, right? So keep that in mind. Keep that in mind, guys. There's no rules when it comes to that. You can make that part of your experimentation. Like I've done NLP projects where you can say, I got these results by using this stemming approach, but I got these other results by using a different stemming approach, right? You can do that, but you can also do none of it if you wanted to, right? So it's all part of the flexibility of data science. Okay, so coming back to the meme that's on the screen, Michael says overfitting, I believe. Osama says overfitting. Denelson says, I believe that it will just remember the data and not train properly. I was a bit confused when it was posted. Yeah, so all of you are on the right track, right? And I think it's basically making fun of a lot of the AI companies where, they're claiming these ridiculous accuracy numbers and, test scores and things like that, because they're just, you're basically almost not inferring anything anymore, right? It's not an inference if it was part of your training data, right? So I thought this was funny because that's kind of like the approach a lot of the AI companies are doing, right? Where, well, we don't want to guess. We'll just try to get every single document out there and put it in there. Well, I mean, that kind of sort of can work until it doesn't, right? But I thought this was funny, so I thought I'd put that out there. All right, guys. So here's what I want to cover today. This is my coming up screen because this is what I want to work on today. We are going to work on an exercise for image recognition. We're going to use a modern framework, right? Up till now, we've been asking ChatGPT to give us raw code for our neural networks, and that's been a lot of fun. That's been very effective in helping us kind of take things apart and understand how they're working. But that's not how you'll be doing it in real life, right? In real life, you'll be adopting whatever neural network framework your team is already using, right? Most teams tend to adopt a single framework. We're going to use a CNN because we are going to be working with multidimensional data, not images. We are working with multidimensional data. We're also going to conduct a grid search. We're going to run some experiments, right? Basically with our grid search. We're also going to utilize a dropout rate. We haven't talked about a dropout rate. So in the chat, for extra credit, if you guys want, let me know. What's a dropout rate? What's a dropout rate? Let me know. We haven't discussed it at all. It just hasn't come up, but that's okay. It's going to come up today. The dropout rate is a really good example of something that is made easy by the modern frameworks. And we're also going to get away from like these binary type of decisions. You know, because basically we've been like 1 or 0 has been our output, right? And we're going to see what it looks like to have multiple nodes in the output layer. Because most neural networks that you'll work on, or a large number of them, aren't going to be binary yes or no, true, false decisions. You're going to need multiple nodes in the output layer. And in some cases, you're going to have a lot of nodes in the output layer, right? So yeah, what do you guys think? Let me know if you know what a dropout rate is. Put that in the chat. And yeah, while you're thinking about that, let me focus on the dropout rate. So, because Starry Vibes has already given an answer. Starry Vibes says, I think it's used to reduce the complexity of the model. What do you guys think? Does anybody agree with Starry Vibes? Yassine says, what percentage of nodes to turn off in each layer? Okay, why would you want to do that? Why would you want to do that, Yassine? Denelson says, I have defined dropout rate as the proportion of nodes that my model will sleep to help with the complexity of the model. Okay. Denelson and Starry Vibes, maybe you guys can give me a definition for what you mean by complexity of the model, because that's where I'm stuck. I think you guys are generally on the right track, but you're losing me at complexity of the model. Osama says it's a regularization technique used in neural networks to prevent overfitting. Aha. Overfitting, right? I mean, that's pretty important, right? You know, just as we talked about on our previous meme, right? You don't want to get everything because then you're just overfitting, right? So how do we account for overfitting in our models? Like how are we going to prevent that ourselves? Right? Kind of an important discussion. Manoj says used to prevent overfitting. Yeah. See, so Starry Vibes and Denelson, that's kind of where you lost me, because I don't view it as complexity. I view it as the overfitting. Right? So Manoj says agree with Osama. Yeah, and Manoj, I think Osama would also agree with you. Yassine says, I want to do that to make sure the model does not unnecessarily focus on the very small details. Oh, Yassine, but what is small? What is small? The neural network doesn't know that, right? The neural network doesn't care. Yassine, buddy, I love you, but I'm not on board with that answer. Starry Vibe says high complexity is more flexible but risks overfitting. I'm not sure if I associate complexity with overfitting though, Starry Vibes. Complexity is going to affect your speed, the size, like the physical size of the neural networks, but overfitting, I don't know about that, Starry Vibes. Denelson says we use dropout rates so that we can help our model nodes don't grab all the information. Not information can be best that can help us with reducing overfitting. Okay, so Denelson, I think you're putting forth a very reasonable definition there. So here's how I like to think about it, guys. Remember how we've talked about that the a neural network is a mathematical representation of the human brain, right? That's the base definition we've established. So when I think of a dropout rate, I think of those times when you're just like, oh, well, wait, what was that? What was that person's name? Oh, wait, where did I go on vacation that one time? You forget things, right? We talked about those synapses and all the links in your brain. Sometimes those links don't work, right? Sometimes things just kind of get lost, right? So a dropout rate simulates that in training, right? Because it's a training hyperparameter, right? You really wouldn't need it at runtime. And that's where you simulate nodes dropping out, because that kind of simulates a little bit of a memory loss, a little bit of just like times when like your brain has to think about other, oh yeah, now I remember it, right? Has to find other patterns or other connections in your brain and in those connecting synapses to be able to say, oh yeah, now I know the answer, right? That's basically what a dropout rate is. It simulates that. It says, okay, this training round, I want to shut off X number of nodes, or proportion of nodes. And that way the network has to kind of retrain itself and say, oh, here's what I need to do to get to an answer, right? So that's really how I think about it. The benefit is that it prevents overfitting, right? Why? Well, because it has to find other ways to an answer, right? You're forcing it to adjust. You're forcing it to say, okay, yeah, well, in times when you don't know this, or in times when you get a bad answer here, make sure you find an answer by going over here, here, and here, right? So that's basically how I think about a dropout rate and the benefit of it. Because you are preventing that overfitting, because now when you present data, it's kind of sorted to a different neural network every time, because different nodes will be shut off, right? Same proportion of nodes, but that's kind of the point, to help you have different neural networks answering the same answer on the same data. Manoj says, I feel complexity can be addressed as high dimensionality, open to being wrong. Manoj, I want to credit you for saying open to being wrong. I think that's a very healthy attitude for a data scientist to have. So good for you, my friend. Complexity can be addressed as high dimensionality. Sure. High dimensional models tend to be complex. So I agree with that. But it's not the only source of complexity. Remember how we talked about the neural network architecture can be whatever you want it to be, right? There's different implications of your choices, right? If you need it to be a fast neural network, or it can be a little slower, or you're going to have a lot of hardware, you're going to have a little bit of hardware. There's implications to those choices. But complexity can also be addressed or created by the architecture that you choose, right? So I think you're on the right track overall there, Manoj. Fabrizio says the model becomes more resilient and flexible. The dropout rate is the fraction of neurons randomly set to 0 during each training step. Yeah, that's reasonable. Yeah, guys, and if it's very important how we express ourselves, right? So one of the things I always tell my clients or my beginners is always, it's not fractions, it's not percentage, it's proportion, right? If you want to sound like a professional statistician or professional data scientist, we use proportion. So keep that in mind, guys. It's just one of those things that when I learned that and when I adopted it, it felt like it elevated your career, your status, right? We don't say fractions, we say proportion. Osama says turning off parts of neurons during each training iteration. Yeah, Osama. I think you're on the right track there, in line with all the other items. But again, guys, just remember, it's just another extension of simulating the human brain. The human brain is not perfect. You're going to forget things, right? But your brain doesn't say, oh, I forgot that, I'm never going to think about it again. Your brain finds other ways, other connections, right? Same thing. All right, guys. So number 4, I want to talk about real briefly. We're going to have multiple nodes in the output layer. Because if you remember before, we were using our XOR, right? We were using our XOR table as our data to be able to say, hey, this is the input and this is the desired output, right? 0, 1, 1, or 0. So that's basically a binary output. And we were only getting one probability, right? This probability here that tells you whether it was 0 or 1. So here, this is telling you it's 998. That means it's closer to 0, closer to 1, excuse me. So the likely answer is 1. Here it's 0.004, which is close to 0, which means that the likely answer is 0, right? But what happens when we go beyond ones and zeros? It's kind of important, right? So when would we need to do that? We are going to work on what is known. You know, by the way, guys, I'm sorry if I'm mispronouncing this, but I've always referred to this as the MINCE data set. Maybe I'm wrong on that. If somebody wants to correct me on that, but I've always referred to it as MINCE. If you've never heard of this data set, it's basically a collection. Oh, actually, no, let me increase this. Sorry, guys. It's basically a collection of images. And those images are handwritten numbers. So what we're going to do is we're going to take, this is going to be our data, and we are going to create a neural network to determine an input picture and say, what number is this? Right? So, taking everything we know about neural networks and all that, how many nodes are going to be in our output layer? We want to keep an open mind to what our architecture is going to be and all that. But one of the first things you should establish in a neural network design is your output layer, right? Because that gives you an idea of the complexity and the time it's going to take you, all that stuff. Put it in the chat. How many nodes are in our output layer? All right. So Yassine, Starry Vibes, Denelson, Michael, everybody's coming up with 10. Okay, why? Denelson says 1 for each type of number. That's exactly right. Thank you, Denelson. That's exactly right, guys. So if that's not clear to you, we're basically saying we're going to have a neural network. And these are the possible results from that neural network. Or as Yassine says, we have 10 classes, right? Each one of these numbers represents a class, right? So we have to assign a probability to each one of these classes based on what our neural network knows. So speaking of complexity, right? You as the data scientist should immediately be aware that, hey, this is going to be a little bit more complex than your average model, right? Because if you're going to have 10 outputs, that means you're going to have a fairly sizable model, right? Because, 10 outputs, you're unlikely to reach a good answer with only just a couple of layers. You're probably going to need multiple hidden layers. Each one of those layers, you generally want them to be bigger than the number of outputs. Maybe just as a starting point, we'll use 30 nodes. I mean, I'm making that up because any answer is valid, right? So right away, you should be knowing, oh, wait a minute, this is going to be a serious effort, right? Some of the biggest models that I've worked on, I think, have been up to like 46 or 48 different classes, right? Which is a lot, right? You know that you're going to be investing into a serious model when you're doing that. But I'm bringing this up because these are the types of like mental calculations that you can make just by talking to stakeholders, just by sitting in general meetings, right? You don't need to code everything out. You don't need to, run experiments. This is more about like just kind of like the experience side that you develop as a data scientist to say, wait a minute, there's a big difference between me developing something that has 3 or 4 classes versus 15 classes, right? I mean, think about what this looks like for the American, or rather the English alphabet. English alphabet has 26 letters. So now you're going to have 26 classes, right? So what does that look like? Well, that's a big network, right? So I'm encouraging you to kind of think about it in those terms, because this is how you can come up with like ballpark figures to know like, okay, wait a minute, that's going to be a pretty significant effort. I need to be careful here on the questions I'm asking and make sure I have enough data, because the more classes you have, generally speaking, the more data you need, so on and so forth, right? So keeping that in mind, we're going to be working on a neural network that most likely will be image data, which most likely, or we'll start with CNN. We're going to use a modern framework instead of raw code, and we know that our output layer needs 10 nodes. Okay? Are you guys with me so far? If anybody's lost, that's okay. Let me know in the chat. But otherwise, let's go ahead and start going into ChatGPT and start building out this sucker. All right. So give me just a second, guys. Let me bring up I guess we're ready for the web. Oh wait, we are in the web interface. Okay. I think we are gonna stay with O4 Mini. O4 Mini has given us pretty reasonable results so far. And I point that out, guys, because we've been using 4.0 a lot for our coding, but 4.04 Mini is not too bad. So let's just keep going. In this scenario, we're going to assume that ChatGPT knows about the MINS data set. It's a fairly standard data set that's used by, a lot of people, a lot of training. So we'll just kind of start building our prompt from there, okay? So you know what? Let me increase that. Sorry, guys. So we're going to specify that we want it in Python. We're going to specify that we want to use the data set, and that we want to start with a fairly simple example, and then we'll build it up. I believe that Mince is already built into Keras, because Keras does have some sample data built in. So we're going to go ahead and ask it to use it, use the Mince data as available in Keras. Mince data set. So yeah, let's start here. I'm tempted to prompt it a little bit more, but we can make adjustments later on. But let's see what it gives us as a first pass. I was thinking, because I wanted it to kind of maybe break out the training versus the prediction cycles, but let's see what it gives us. All right, so here's a simple Keras example. Okay, yeah, so it does have it. If you notice, it's making a call to Keras dataset minced. It's giving us our training and our testing data. Yep. It's going to use it's going to use accuracy as the main metric. It's going to do 10 epochs. Okay. So this looks like a reasonable example. Let me go over here. We're going to start a brand new new sheet or new code, and we're going to call this NN4. We're going to put it in here. 54 lines. Wow, 54 lines is pretty good, guys. So this is a fairly simple example. I think ChatGPT did a good job of keeping things easy for us. So we're going to go this line by line just in case anybody is lost. But basically, here we are breaking out our training and our test set, right? You always want to have something that you're training on, and then you want to have your test that you're testing against, right? Here, it's going to go ahead and take and make those images flattened out into 28 pixels by 28 pixels. And that way it gives you a vector length of 784. And then it's going to go ahead and normalize the pixel values to 0 or 1. In other words, it's going to turn it into a black and white image, right? That's essentially what you're doing when you're saying, don't give me the color, just tell me if it's black or white. Or, you know, shading light or shading dark, and then turn it white or turn it dark. And then here we are going to go ahead and we're turning it to one hot encoded vectors. At line 20 is where the magic begins, right? Because in line 20 is actually where like the work happens. This is our input layer, and then these are our 3 hidden layers. That's what it's recommending. It's recommending 3 hidden layers. One of them is going to be 256, one of them is going to be 228, and then here in the output, I meant to say 2 hidden layers. The last one is the output layer. And the output layer, it knows that the number of classes it needs is 10. Yep, it established that up here. I don't know why it hard coded that. That's weird. It could have found that in via other ways. And then it's gonna assign an activation function to those final nodes, right? And with softmax, if you guys remember, softmax is what? Is softmax a step function, or is it more of a gradient function, like a sigmoid function? Let me know in the chat. What do you guys remember about softmax? Is softmax a step function or a sigmoid function? Excuse me. Let me know in the chat. And then the compile is what actually puts the entire neural network together. The compile is a Keras call, if you guys haven't seen that one before. And then these are our training parameters. The fit is the Keras method that actually does the training. Here's where we're putting in our epochs. We're putting in our validation split, where we're saying withhold 10% of our records for validation. And then here is where it actually gives us the results. Right? So I think this is pretty good code ready for us to run. We don't have these though. We don't have NumPy or TensorFlow or Keras. So let me go back to ChatGPT and figure out the imports that we need. Or the pip installs, I should say. Pip install TensorFlow, that should be it. Okay, so that's pretty good. All right, let's go ahead and do that. What the heck? It couldn't find one. Okay, that was weird. Let me upgrade my pip just in case. What is going on? I think I could just probably do Keras instead. Let me just do that instead. ChatGPT might have made a mistake in telling us to install TensorFlow. Let me know what you guys think about that. That was a weird error. But let's go ahead and try to run this. So Python nn4.py. No module name TensorFlow. Okay. Okay, that's weird. Fabrizio says maybe the name is different. Yeah, I think you're right. So let me show ChatGPT the error. Oh, right. The Mac OS is might be part of it. Or not. Wow. I feel like we had this error before, chat. And I want to say it was related to the version numbers. Does anybody remember that? JR, I think you're new here. Welcome. JR says virtual environment. No, well, I mean, it is a virtual environment, but I'm using Conda. Guys, maybe some of you remember this because I know we've used Keras before. I think we had to downgrade our Python version, didn't we? Wasn't it something like that, guys? Does anybody remember that? I want to say it was related to our Python version. This is weird. Let me follow everything that ChatGPT says. Okay, setup tools wheels. Now we can try Mac OS again. Nope. Metal is also not gonna go. So let's show that to ChatGPT again. Yeah, it supports 3.11. Okay. Yeah, that was the answer last time, chat. I tend to lean towards the latest version of Python, which doesn't always agree with Keras, which is kind of weird, right? So we're gonna have to downgrade our our environments. So I just want to be reminded of what that command is. Yeah, conda create nn2. Yep, okay. So let's go ahead and fix that in the terminal. So we're going to say, we're going to deactivate this. We're going to create a new one with Python 311. We're going to name it nn2. So that looks good. All right, cool. So now we're going to go to conda, activate nn2, and we're going to go to the initial recommendation, which was pip install TensorFlow. Okay, so that's going to work. So guys, I'm not in agreement with it, but apparently, you know, the libraries don't always support the latest Python version. So if you're not aware of what just happened, I created my environment in Python 3.13, which I think is still the latest release. But that was causing problems with the latest versions of Keras and TensorFlow. So we had to downgrade our Python by creating a brand new environment, right? Separating that out from our other work, create a new version in Python 3.11. And now the TensorFlow install works just fine. So now, if we go back and we run that same Python file, the code that ChatGPT gave us, this should work here. So it looks like this is going to go. Okay, so there we go. So now we're running through our epochs. So if you guys have never seen it before, everything you're seeing right now with the epoch list and the steps and the accuracy and all that, that is all a function of Keras, right? This is kind of like the value add that you're getting from working with an environment, a modern neural network framework, where it will give it to you and say, okay, well here, now let me take over. You told me what architecture you wanted for your neural network. And now I'll take over and I'll do all the math, all the different changes and arrangements and all that. And it'll do it internally within the library, right? Because remember, if we go back here, we can see that our code is only like 50 lines. This was an optional one, right? But it was only like 46 lines for the entire, like the base of the code, right? So pretty reasonable, right? Pretty reasonable to bring in that framework and have to deal with a little bit of setup and a little bit of overhead, but it really just kind of helps you instantly get some more information and data out of it. Casual Economist says, I'm late. Can we start all over? Welcome, Casual Economist. Yes, of course we can start all over. So, Casual Economist, today we started our stream by everybody giving a 10-minute presentation about themselves. So, yeah, if we want to start over, go ahead and start, Casual Economist. The floor is yours. Yassine says, is it supposed to be showing the training cycle? I don't know if it's just me, but I can't see it. Yassine, yes, it is supposed to be showing a training cycle. Did it not do that? I think it did, right? Or wait a minute, did I? Gosh, oh man. You know, guys, I'm sorry. I don't know why it's doing that. My OBS keeps dropping my screen capture, right? Because I have like a second monitor that I use for all of my work. Yassine says now it does. Yeah, yeah. Sorry, guys. I don't know why that refresh rate is failing, but it doesn't seem to, restart the capture. So I have to do it manually, which is really annoying. But yeah, thank you for that, guys. But yeah, this is what it looks like, guys. So everything you're seeing on your screen right now is a convenience of working with Keras, right? Because this is all Keras output. We didn't program any of that. This is what's baked into the library, right? So the library is telling us, hey, I ran this epoch. I used 422 batches. Here's the accuracy. Here's how I improve, so on and so forth, right? So let me know if anything on this screen is catching your eye. I haven't looked at it yet. I'll take a quick look here. Osama says, if one framework is compatible with Python 3.11 and another requires 3.13, what approach should we take to manage both? It depends. It depends, Osama. Are you talking within the same project or within the same server or whatnot? Because virtual environments should be able to handle what you're talking about, assuming separate projects. Yeah. Otherwise, you'd have to get more into project-specific needs and figure out, what needs to actually talk to what, and go from there. But virtual environments, Conda, all of that should help you with that problem, Osama. Common problem, by the way. Casual Economist says, I was born on a farm. It was cold and rainy night from what I remember. Okay, keep going. You've taken up about 20 seconds. So you got a long way to get to 10 minutes there, my friend. All right. So let me take a quick look. Does anybody want to point out anything that they're seeing on here? What do you guys think? Is this a good model, bad model? Do we need to try again? What do you guys think? What is your general impression? If you're lost, that's okay too, right? Let me know. But what do you guys think? Give me your impressions. What's your interpretation, right? Result interpretation, super important part of being a data scientist, right? So I've already made my interpretation, but you guys tell me, what do you guys think? Yassine says loss is good, accuracy is good, both for training and validation test sets. Starry Vibe says, I think it's a good model. Starry Vibes, why do you say that? Yassine says, we didn't need that many epochs, that's for sure. Yep, 10 epochs, pretty fast, pretty fast. What else do you guys think? Anybody else? What do you guys think? Is good model, bad model? Are we on the right track, the wrong track? Do we need to redo everything? What do you guys think? Fabrizio says, how is accuracy and loss being calculated? How is validation, accuracy, and value loss being calculated? Is it using MSE or cross entropy? Is accuracy calculated as an F1 score? It is using cross entropy, right? We can see that in the code. And accuracy is not being calculated as an F1 score. I believe the default for Keras is just to do it straight up accuracy. Manoj agrees with Yassine. Osama says, I believe it's a good model. Michael says, please explain. Michael, which portion do you want to explain? I mean, if it's the whole output, that's okay, right? But let me know which portion you're referring to for the explanation, okay? Because to Michael's credit, there is a lot happening on this screen, right? So that's why I'm kind of challenging you, all of you guys who say it's a good model. Tell me why. What on this screen is kind of, making you conclude that, right? And like I said, guys, result interpretation, model interpretation is extremely important in your career, right? So I'm gonna kind of push you guys a little bit. Why are you guys saying that? Why is it a good model? Or if you're maybe just a little bit confused or whatnot, like Michael, feel free to say that too and say, hey, I need a little bit more in-depth explanation. What do you guys think? Starry Vibe says, I think Epoch 9 does better than 10. Look at the validation loss in line 9 and 10. Okay. Okay. I love that observation. Denelson says, it does look good. Could we get back to the recomposition scores and a confusion matrix? Okay. Okay. Michael says he wants to explain the whole output. Thanks. Okay. All right. Yeah. So all very reasonable comments here, guys. So let's try to address Michael. And in that process, I'm going to also try to address some of the other comments that people are making, okay? Give me, you know what, guys, just to make things a little bit easy. I'm going to rerun everything we just did. I want to clear out the screen just so that we're clear that everything on this screen right now is generated by Keras. And we're getting similar results, so I think we're going to be okay here. Although I might have just tanked Starry Vibe's previous observation, but it was still valid, so I'm still going to focus on it. Yeah, okay. Okay, so first of all, the first understanding we should all have is that everything here was generated by Keras. We did not write any of the code to generate, to explicitly generate this output. That is a function of the library. That is why you want to use a modern framework, because all of that is baked into the library itself, right? All we did was say, hey, we think this is an architecture of a neural network that we think will work. Why don't you go ahead and try that, right? That's all we did, right? Because our biggest contribution is this section right here, the build the model section, right? This is basically like the only part that's really not done for us, right? Everything else is kind of sort of like predefined, right? Because we know we can't change our data. We wanted to use the min set. We flattened out the data, fairly standard pre-processing. There's going to be 10 classes because there's 10 numbers. Like, we're not making any decisions here, right? Here we're making decisions. Here is where we're saying, okay, well, here we want this layer, we want this activation function, so on and so forth, right? And that's basically all we've defined, but and the number of epochs, right? We defined that, right? But that's it. Everything else here was created by Keras. Okay, so that's the first thing we want to understand. 10 epochs, we define that, right? And we've seen epochs in our other parts. And basically, as we've defined it, it's basically giving the algorithm a new chance to start all over again, right? An epoch is day one in school all over again. So we've given it 10 opportunities to train itself, essentially. Within each one of those epochs, it will go through the data set and try to come up with the best model, and then take that model forward into the next epoch and learn a little bit more, so on and so forth. So in theory, more epochs, more better, gives it more of an opportunity to learn from its past mistakes, right? All right, so that explains why we have these epochs, okay? This is telling us a little bit about the performance, right? How long each epoch took, which for these models is not critical because they train pretty quickly, but as you get into larger, more complex models, that's gonna matter, right? All right, so now we have 4 columns that look very similar, right? So Michael, I want you to think about these as this accuracy and loss is one conjoined column, and this accuracy and loss is another conjoined column. And what we're basically saying is that this accuracy and this loss applies to our test data. Okay? And then we're saying that this accuracy and this loss applies to our validation data. Because if you remember, we chose a certain proportion of our records should be held out for validation testing. Right? We designated that. We designated that as 10%. So this is what happens when we use our test data, and this is what happens when we use our validation data. And validation data, your validation numbers, are technically more important. I hesitate to say, but they should have more of an emphasis, because this is data that your training cycles never saw. They were intentionally held out so that this is brand new data to your model. So in theory, your validation data is kind of like your best reflection of your metrics, because it kind of simulates what you're going to do in the real world, right? When you actually go to use this. So that's basically what we're doing here, right? So think of these as two columns of two, right? This accuracy and loss is important, and then this accuracy and loss is important. So your eye should be drawn to this one, because this is your last epoch, and these are the validation numbers for accuracy and loss. And as we've discussed before, accuracy, more higher, more better. Validation loss, more lower, more better. Anytime you start crossing into the 0.0, you're on the right track. And if you remember, in some of our previous classes, we've gotten down to 4 zeros, right? Where it's like 0.0000 something, right? The lower you can get to the loss, the better, generally speaking. So Michael, I hope that helps break it out for you, but that's essentially what's happening here. This tells us how the model is doing. Now, if we look at this line here, this line is very similar to the comment that Starry Vibes made about the earlier model, where it is possible where you will have epochs that are actually better along the way. Because remember, guys, just because you give it more epochs, you're not guaranteed a better result. You know, that's a fundamental mistake that a lot of people make. Just because you try more in machine learning doesn't mean it's going to be better, right? So there are going to be models along the way, as Starry Vibes made the observation previously, where these numbers are actually not too bad. They're actually pretty good. I mean, that's a pretty high accuracy, right? 9788 is bigger than all but one of these, right? And the validation loss matches what our 10th epoch was, right? So those are the types of things that your eye should kind of be drawn to, okay? But overall, people are saying that this is a good model, and yeah, there's reasons to believe that this model can fit our needs, right? There's reasons to believe that this model is on the right track and will get us to an answer, right? Denelson wanted to see this more of in a traditional confusion matrix, which is what we've done in the past. So I agree with that. We're going to do that. But let me look at some of these comments. So Yassine says, I think it's a good model, good results, loss is small, validation loss as well. They are not so close, but not too far to worry, I guess. Yeah, I agree with that, Yassine. I mean, they are not equal, sure. Fabrizio says, the accuracy is being calculated, accuracy, number of correct predictions, predictions, that's not softmax front. Yeah, sure, Fabrizio, I'm on board with that. Michael says, okay, thanks, it's clear now. Okay, good, Michael, thanks for that. A good question, Michael. All right, so let's go back to our ChatGPT and let's get a confusion matrix. I think that's a good idea. And you know what? We'll ask for it as a plot, right? We'll ask it. We'll ask it to kind of show it to us in a graphical manner. Graphical manner? Yeah, yeah. You can say. As so, I expect that the general code it's going to show us is going to be basically the same. It's just going to have like additional outputs, right? Okay, so we're going to copy that. Let's bring it over. We're going to call this NN5 just in case it made too many weird changes, right? 52 lines. Okay, it gave the confusion matrix. Oh, shoot, I copied it too early. It was still going. Okay. Predicted label, true label. It's going to show us the plot. Okay. It looks to be the same code. But it looks like we're going to need another pip install. Let me get those real quick. scikit-learn, matplotlib. Let me just get this. We're going to install these real quick, guys. All right, that should be good. And now we are ready to run NN5. All right, so we're going to see the same output basically, slightly different numbers. And then we're going to see the plot appear on our screen. Okay. And here's the plot it gave us. What do you guys think? What's your interpretation now? Let me know what you guys think. Anybody have any thoughts on this one? Denelson says, I think it looks great. So yeah, I'm going to kind of keep that, and I'm still going to kind of, let me go this way. So we can see we can see the accuracy in the loss numbers. Give me just a second. Let me bring it down like this. So here's our accuracy and our loss numbers. So Michael, if you want to kind of narrow down your focus, this is a good way to think about just the last two columns, right? So yeah, I think Dennelson's right. It looks pretty good, right? The chart looks pretty good. It's telling us it's making very, very few errors, and the numbers say that, right? A 0.9815 accuracy is pretty high, right? That's like maybe on this size of a data set, that's like 1 error, 2 errors, right? The loss is also pretty good. We had a loss. This one caught my eye. We had a loss of 699, which we didn't have any sixes in our previous run, right? So this run is actually pretty good, right? To have that loss is pretty good. Yassine says, not one false prediction, I guess. First thought is bad confusion matrix because, well, it's confusing. Not showing numerical result. That's funny. That's funny. And you're right, Yassine. I think that ChatGPT could have picked a better way to do that, right? Like the color gradient, I'm not really on board with. It's kind of funny, right? But I totally agree. Class for digit 1 is being classified the best. Oh, yeah, that's a good observation, Dennelson. I'm on board with that. Fabrizio says, what does the colors mean on the confusion matrix? The diagonal is a perfect match. So the purple means that there were no mismatches there, Fabrizio, is what it means. That's the way you should be interpreting that, right? And Dennelson is making the observation about 1 because it's the brightest number, or brightest on that gradient scale, right? But yeah, I mean, to Yassine's point, it's not really it's not I don't want to call it a poor visualization, but ChatGPT could have done better on it. Yassine says, I don't think the class or digit 1 is being classified the best. Okay, why do you say that, Yassine? Because I can see how Dennelson drew that conclusion. It's just because it's the most existing case. Maybe. You know what? Let's ask ChatGPT to modify that, because I think we can all agree that this isn't the best visualization. It's an okay visualization, but not really ideal. Fabrizio says, so we don't have any colors like green, for example, on the purple side. It means it's not mislabeling, and the number 5 is the less accurate, let's say. Number 5, let's say. Yes, Fabrizio. Yeah, you're correct on both of those counts. I think you're drawing 2 valid conclusions there. That's right. But look, maybe most of us here are, we're not visual learners, right? Like the slow blinkers out there. Maybe we need something a little bit more quantitative. So let's ask ChatGPT to do that. But you know what, guys? I'm glad it kind of did that, because this is part of prompting, right? AI is not perfect. AI is only as good as you prompt it. Maybe we should have been more clear on the initial request, right? Maybe that's our fault, right? So we're gonna, you iterate just like anything else. You say, oh, that looks good, but let's do this. This is what I really meant when I said this, right? This is totally natural for us to go through this. All right. So we're going to copy that, and it says that each cell shows its raw count, which is maybe what we should have specified to begin with, right? So let me do that. And we're going to go ahead and replace this. I think we can replace this just fine. And let's go ahead and run it. Okay, so while we're waiting, Yassine says, if the color is based on the number of correct predictions, you can get a big number just by having it exist more in the validation data set, meaning it's unbalanced. Maybe, Yassine. I don't think that the validation set is that big to make that kind of difference. All right, guys. Okay, so technically speaking, ChatGPT did do what we wanted to, but the colors are awful. Oh my gosh. Okay, guys, that is terrible. We're not even going to try this. We're not even going to try this. What is the prompt we can fix here? We can say, okay, let's see if we can get rid of those purples. Purple on black is a terrible combination. But hey, you know what, guys? Another great example when people say, oh, AI thinks on its own and we're going to reach generalized intelligence.